So if you look at some of the problems I'll be talking about here, one of the optimization problem now. Okay. We have the monotone inclusion problem. We have the relational inequality problem, which is the bone of contention for today. And we also have what we call the convex minimization problem. A lot of people consider this problem. And we have more. We have the equilibrium problem also. Now, this problem were introduced by different set of researchers. Let me start with the monotone inclusion problem. We have, let's assume you have an operator, a single valued mapping, A mapping H to H. And we also have a set valued. Our H is a Rayleigh space. I'm just working on Rayleigh spaces. We also have B taking H. It's a set valued mapping, like I said. The monotone inclusion problem, or I can call it zeros of monotone operators. Zeros. Because if you look at it, A is a single valued mapping, B is also a set valued mapping. These two mappings are monotone mapping. So in a case whereby we have 0 of A plus B, sometimes, then we are talking about this problem, the monotone inclusion problem. That's why I said some people call it sum of two monotone operators. We have some generalization of this problem whereby we have another operators being added, A plus B plus C. But for now, we'll be sticking to these two. Now, I can just make my A to be an identity operator whereby we have just 0 of BX. And please, like I said, this A is a single valued mapping, monotone mapping. This B is also a monotone mapping, but B is a maximum monotone. So in this case, we have another problem, which is deduced from this problem. I can call it a variational inclusion problem. Now, if you look at this method, this problem, it has been solved by the well-known proximal point algorithm, whereby we try to represent this problem with what we call a resolvent operator. Let me define such operator. We have something like J lambda B equals I plus lambda B. This is our resolvent operator. So in this case, several methods have been used to solve this problem. Like I told you, the most used method is the proximal point algorithm. And something about this proximal point algorithm is that it can also solve other problems. But it is when we have what we call a monotone operator. Though there are advanced results when we get there. For variational inequality problem that was introduced by one of our master students yesterday, don't forget that we can also write our monotone operator like Prof asks something like this. But solving this problem also implies you solving something of this nature, PC I minus lambda A, where this A is also a monotone. Though, for proximal point to solve this problem, my A will be what we call the inverse strongly monotone. Inverse strongly monotone. What do I mean by saying inverse strongly monotone? It is, let's say AX minus AY, X minus Y is greater than or equals to alpha. Okay, I'm using, let me call it alpha inverse, the norm of AX minus AY squared. But this, like I said, this is a variational inequality problem which can be represented in this form. So solving this problem is like you have solved this. this variation inequality problem. Though there are different approaches. If I can find the fixed point of this problem, the fixed point of PC I minus lambda A, it shows that I've solved the variation inequality problem. VIC A. But like I said, it is true proximal point of error. Because once A is no more inverse strongly monotone, if A is, for instance, monotone, pseudo-monotone, quasi-monotone, then this method might fail, we fail to solve this problem. So that's where different methods came in. We also have the convex elimination problem. The convex elimination problem is similar to this problem because it's just you making your A to be a gradient function and your B be a sub-differential function. So what I'm trying to say is that if I'm having something like this, let me say grad of F plus sub-differential of G, you can see I've made this A to be a gradient function of F, and this is sub-differential of G. And one of the conditions here is that this gradient of F is Lipschitz continuous. We have to put that condition there to be able to play around it. Also, for the equilibrium problem, it's just you having your F of x star comma y greater than or equal to 0. This F can be monotone. If it is monotone, the proximal point can solve this also. And F, we have seen people solving a case whereby F is pseudo-monotone, quasi-monotone. So with that, we have different methods coming in. Now, for monotone operator, for zeros of monotone operator, which I call the monotone inclusion problem, there are other methods that can be solved, that can be used to solve this problem. Now, I'm looking at the sum now. Now, if you look at, apart from the proximal points method, where I said A is monotone, B is maximum monotone, we also have what we call the forward-backward method. The forward-backward method is just something simple. It's defined from this. Like I said, that my resolvent is J lambda B equals I plus lambda n. Is that right? Yeah. Now, for the forward-backward method, don't forget that this only captures this special case. What of when we have this A, then we have to add something like I plus lambda n P I minus lambda A. So he's saying that this is forward and this is backward. So we have the forward-backward method. We have been used to solve this method. I will show from my presentation how this can go. For the variation inequality problem, if A is not inverse strongly monotone, because I remember writing some papers, you see reviewers will come and tell you, okay, you have imposed an inverse strongly monotone, and we know that this condition might not allow you to consider some real-life application. Then, can you consider some other operators? And if you are considering those operators, can the same method solve that same? No. If A is monotone, if A is pseudo-monotone, if A is quasi-monotone, then other method needs to come. So one of those methods is what we call the extra gradient method. Extra gradient method. This is a nice method, but it has its own problem. It has its own limitation. In optimization, this PCA is what we call the metric projection. We are trying to avoid having a lot of projection map, this PC. But for extra gradient method, it has two projection maps. We have the PC. Let me define an algorithm. Let's say this is my algorithm where we have my YK to be PC I minus lambda n A of Sn of Sk, and I have my Zk to be is also PC of I minus lambda n Yk A Yk. You can see we have two projections, which is a problem for us. It affects it's computationally expensive. During our implementation of numerical examples, it gives problem. So that is why you see some researchers now came here and said, okay, if this is giving us problem, is there any other method that we can bring in that will at least solve the problem of this computationally expensive? Then another method that came in is what we called, is from extra-gradient method. This was introduced by Kopelevich some years ago. So this now, for this subgradient, extra-gradient, what they did is just to remove the PC here and just put what we call an half space. It's an half space onto a closed convex set. So in this case, this TK has replaced this set here, C. So this has helped at least to solve the problem. But you see, some people were still saying, okay, we still have something of that nature, though we know that it is quite different from this. Are there other methods? Then we have some other methods. From what the student presented yesterday, he was talking about the forward, backward, forward method, which is also known as the Zeng method. It was introduced by Zeng in maybe 2000. So this method will be, this projection will disappear, and there will be something new there to replace that. Then we have the projection and contraction method, which is what I will be looking into today. So all this method I've talked about can also solve this same thing. For this, because the extra-gradient method can also solve the equilibrium problem. We also have the subgradient extra-gradient method. We can solve this equilibrium problem. For the inclusion problem doesn't have a structure of a metric projection. You will see, it's just the resolvent. We don't have PC. So we don't need, that means extra-gradient doesn't need to come in. So extra-gradient method cannot solve this problem. But we have some other methods that can solve them. So what I'm trying to say is that there are some methods that can solve all these problems. Like the forward, backward, forward method can solve all these problems. Like the projection and contraction method can solve all these problems, which is something they just started. And that's what I will be discussing. Let me go back to my slide.
You are working on complex field, right?
What's it?
You are working on complex field, right?
Complex, yes. No. But this can be, some of them can be moved into complex field, but this is not a complex field.
But then your spectrum can be empty.
Why?
Spectrum can be empty.
Which of the spectrum?
Your lambdas?
No, lambda is just like a parameter here. It's a parameter. It's a positive parameter. Lambda is positive. Lambda is always positive, greater than 0. It's not talking about spectrum. You will see some of those things there. Spectrum is just, when we are computing the numerical example, you see, we can pick lambda to be any number as long as it satisfies that condition. Lambda is greater than 0. So these are some of the outline, the background and motivation, the extra-gradient method, the subgradient extra-gradient method, the projection and contraction method, and the results I will be presenting. So that's the division inequality problem that was defined yesterday. So we have Q coming from, I said, let omega be non-empty closed convex subset of a Hilbert space. Don't forget that yesterday I said this was defined in RNA. So, but I don't want to go into those history, so I'm just taking it to the space I'm working. So the division inequality problem is to find Q coming from that non-empty closed and convex subset such that this happens. Sorry, there is something here greater than or equal to 0. There's a typo there. So for the rest of this presentation, whenever you see gamma, that it shows that I use it to represent the solution set of this problem. The information inequality problem has wide range of application in areas such as network economy, traffic assignment, game theory, and mathematical programming. It has drawn significant interest, not only from the optimization community, but also from various applied disciplines. You can see one of those applications of racial inequality problem is our image restoration. One of my masters that graduated maybe 2 weeks ago, we tried to apply one of these problems to solve an image restoration problem through collaboration from one of our research associates in the UK. Also, we have the traffic network. This problem can solve all this problem. We can try to, because all we are doing is just to minimize costs and trying to maximize profits there. So all this variation inequality problem can solve traffic network. And what have we been doing? We have been meeting with experts in this field. I have people in machine learning. The one we did recently was from a colleague in China. In fact, yesterday we were talking about one of our results that just got accepted. So we are asked to put some real life application. So what we do is we do the theoretical parts. Then we consult and say, okay, this is what I have. Can we model this problem into something in your field? Okay, it's something we can do. Then we give it to them and they try to solve a real life problem. So this network, traffic network problem. So a major focus of research in this area has been the numerical approximation of solutions of VIP. That is the different methods that have been used to solve this problem. So over the past 4 decades, extensive effort have been devoted to developing and analyzing numerical methods for solving the variation and inequality problem. So numerous efficient iterative algorithms have been developed for solving these problems. So one of the methods here is the projection method and its various modifications. You see, another thing about iterative method now is, apart from this method that I mentioned, it also depends on what your aim, what do you want to achieve? Which type of convergence do you want to prove? You've seen people in other disciplines, they consider this type of problem, they solve the global convergence, different linear convergence. We solve weak convergence and strong convergence. So it depends on what you want to achieve. That's how you define your algorithm. You are trying to prove a strong convergence. You know some things you need to incorporate into your algorithm, like the Aphane iterative method, like the viscosity that yields a strong convergence. So we have the projection method and its various modifications, the linearized Jacobi method, the Newton type method, techniques involving Wenner-Hopf equation, the auxiliary principle, and method based on merit function. For comprehensive discussion, readers can check the book of Nagoni and Pang. Now, like I said, one of the popular methods for solving this problem is the projection method, which is what I was trying to define there. Look at this. This is the projection method. You can see from what I'm saying, this metric projection here, you have the 2 here. And that is what we are trying to avoid. This method is nice. It has been used to solve the variation inequality problem. Now, one of the problems, like I said earlier on, look at this researcher that introduced this by Kopelevich and Antipin. It was introduced in an Euclidean space where F is monotone and L Lipschitz continuous operator. That's the operator here. And if you see this, this tau k is depending on this Lipschitz constant. So one of the improvements we do, because we know that why are they making this depend on this Lipschitz constant? There are ways to dispense these conditions. So one of the ways is what we have here. Some people use what we call the line search technique. So the line search technique, we use it to dispense with this Lipschitz constant. So I can just, instead of making my tau k depend on this, I can give this, which is a line search technique, and it's solving my problem. Now, the algorithm I just showed you now, let's see the major setback of the algorithm. Number one is that it requires 2 evaluations of projection operator. I said it. And this implies solving a minimal distance problem twice by iteration. And this could affect the efficiency of this method and slow it down during implementation. So that's one of the problems of the extra-gradient method. It slows the efficiency of the iterative method during implementation. So, and also, how do we address that setback? How do we address the problem of two metric projection? So we have to address this drawback. Several modifications have been done. So we have the notable among is the subgradient extragradient method. A lot of people have considered that method. You can see there the forward backward method. Sorry, the forward backward forward method and the projection and contraction method. Now we are here. Look at the Zeng method. You can see the difference. The second metric projection is no more there, but we have replaced it with this. That's the Zeng method. Zeng method, this is our variation and equality problem, the problem we are solving, and also this is another method. Here, the second projection mapping has been deleted. So we have this. So this is the Zeng method. The Zeng method is very, in fact, a lot of researchers have considered this method and very efficient. And but one of the problems, like I said here, is that this my tau here is still depending on what we call the Lipschitz constant there. And if you look at these authors, they establish what we call the weak convergence. And again, when their F, this operator, is strongly monotone and continuous. So, like I said, what we are trying to do is that we also look at the operator the authors consider. Is there a way we can weaken the condition on that operator? This is a strongly monotone and continuous map. So we will see next what has been done. Another important extension of the extragradient method is the subgradient extragradient method, which I told you. Now, what happened here? This deviation and equality problem, this is the half space that has been defined here, which is also nice. It's also efficient. A lot of researchers have compared all these methods and see the one that are more efficient. And again, you can see that my tau here is still depending on what we call the Lipschitz constant. Now, I've done some work. Like I said earlier on, the subgradient extragradient method can also solve other problems. You can see here, what we did here is I was able to use that method to solve equilibrium problem. It's a paper published, I think, late last year, and something interesting. Also, I have shown you, we have seen some researchers trying to put some nice application. This is a paper by Professor Shelamjak from Thailand. They were able to use the subgradient extragradient method to solve a cardiovascular disease detection. I think they tried to use classification of this thing, all this machine learning, so they were able to give their paper and at least put something like a real-life application there. Now, for the this method now, so you can see that in the algorithm for that algorithm, the second projection onto the visible set is replaced by a projection onto an easy and constructible half space containing the visible set. So you can see that PTK, the half space, the projection that is there in extragradient method has been replaced by what we call the projection onto an half space. And since the projection onto a half space is explicit, the subgradient extragradient method similarly reduces the amount of computation comparing to the extragradient method. And also, among other various methods for solving this variation inequality problem, this presentation focuses on the projection and contraction method introduced by HE for solving monotone variation inequality. Now, if you look at this person that introduced the problem I will be talking about, he introduced it to solve a monotone variation inequality problem. What do we mean by monotone variation inequality problem? It's still the same variation inequality problem, just that its operator is monotone. So, is there a way? A lot of results have been done on this. This is the projection and contraction method. It's quite different from the Zeng method. This is the variation inequality problem. We have this. We have what we call this. Yeah, F here is monotone. Like I told you, F is monotone and L Lipschitz continuous. And this tau is still depending on Lipschitz constant. We have some of these parameters being defined, and our beta K here is a kind of a step size that was defined for it. So this is the projection and contraction method. It's quite different from the extragradient method that has two projections. is we have seen researchers that work on this, where they compare this method with the Zeng method, and they were able to see that this method is quite better than what we call the Zeng method. So another thing I would like to talk about is that apart from using this method to solve optimization problem, the beauty of iterative method not only depend on finding the convergence of iterative method, but also the rate at which they converge. How fast can your iterative method converge? Yes. So with that, a lot of extrapolation method has been introduced. The well-known one is what we call the inertial technique. The initial method is a method discovered from physics. They call it the heavy ball method. They use it for all this damping, all this oscillation motion. So it was used there before being brought into mathematics. So if you look at the inertial method, I won't be able to, but let me show you. Look at the first step here. This is the inertial method. This delta K is known as the extrapolation term. A lot of conditions are being placed on this delta K. And like I told you, apart from the normal well-known projection and contraction method, this step was added to speed up the rate of convergence of this iterative. So that's the beauty of the inertial method. We also have the golden ratio technique that has been used also with this extrapolation method. And you see, if you look at my delta K, that's its own step size here, and we have some condition being posted there. So this is our projection and contraction method and the inertial method. So we can call this the inertial projection and contraction method. So, and if you look at that algorithm I just showed you, I say it is worth noting that the implementation of algorithms 5 and 6 rely on the estimate of the Lipschitz constant of the operator. That how is depending on the Lipschitz constant. However, this requirement is often impractical as the Lipschitz constant of this operator is typically unknown in most real-valued applications. And in order to overcome that limitation of the Lipschitz constant, we have Xiu from China. What he did is, let me see, yeah. Now, he defined a self-adaptive step size. What is this doing? Is in this, if you look at this algorithm here, this lambda k here, in our previous algorithm, lambda k is depending on Lipschitz constant. You see lambda k 0.1 over head there. But Xiu said, okay, since this is impractical and is affecting the implementation of this algorithm, is there a way to dispense that condition of that problem? So in this case, we have what we call the self-adaptive step size. And I said, some researchers have used some other this thing. We have the line search technique also, which can also do this. But we have problem with the line search. It takes time for it to convert. This is W substrate K. So motivated by all these results I have said, what we are going to be doing is to bring in the projection and contraction method. We are going to be using a step size. We are going to be using what we call a relaxation parameter, an inertial term, and the correction terms. There are some new things we are adding to our algorithm. Let's see our own paper, our own algorithm now. I have some definitions there. Now look at this, my algorithm. This is the well-known inertial extrapolation term. We have added these things. These are the correction terms that also help in the robustness of the algorithm. So I'm adding these things. And also, if you look at our projection contraction method is not just like the other ones we have introduced. We have relaxed it. You can see 1 minus alpha k. These are what we call the relaxation parameters that are being introduced into this algorithm to just make our algorithm better than some of the results in the literature. And look at my step size. It's quite different. I'm adding some new parameters to my step size here to make it more efficient. So this is our algorithm, and this algorithm here can also solve what we call the monotone inclusion problem. I can just, since this VIP, variation inequality problem I'm solving, if I can replace this problem with a monotone inclusion problem, this problem will also solve it very well. In fact, if I can still replace this with a convex immersion problem, this our method can also solve, which means our method has a wider application. It can solve some of these optimization problems. So we have done that. In fact, this paper is something I just finished the computation, and is there with a colleague trying to implement a real life application to solve this problem. So, and let's look at some of the importance of that algorithm. So it is easy to see that we impose on our F in that assumption. A lot of researchers have been using the sequentially weak continuous. So we are using the weak to strong sequential continuity on pseudo-monotone operator. And don't forget, please, that this our operator here, F here, is not monotone, is pseudo-monotone, which is a weaker notion compared to the monotone operator. And again, we said if my beta equals to 0, this is this, and alpha k is 1, my algorithm reduces to the inertial projection method studied in this paper. Also, if my beta equals to 0, delta k is 0, alpha k is 1, this is this, and F is monotone, then our algorithm reduces to the projection and contraction method studied in all this paper. And we also like to emphasize that the implementation of the result of this involves having value on estimate of the Lipschitz constant of the cost operator, which is not practical since the Lipschitz constant of F is most time unavailable in real life application. So we're able to at least see how our algorithm generalizes some of the algorithms in the literature. So, and again, I think I decided to add this, the inertial projection and contraction method proposed in our paper integrate the classical projection and contraction framework with an inertial technique and 2 correction terms. The incorporation of this component enhances the numerical performance and accelerates the convergence of the standard projection and contraction method. Notably, the inertial parameter in algorithm 8 is not confined to, that's why I said, you see that theta k, there are a lot of conditions on it. So, but we try to make sure that our own theta k is not confined to some of these conditions there. So another thing I would like to say is that for the nonlinear spaces, one of the problems we have is that, for instance, the Adama manifold, that is the Riemannian manifold that is complete and has a non-negative coefficient. In our own case, some of this work have been done in those spaces. For instance, one of our work one of our recent work, which I published, was in Adama manifold. We tried to see, can some of this work be moved into some other, can they survive in those spaces? Though the geometry of that space is quite, we face a lot of difficulty because we are going into something new, and also the geometry is quite different from what we know. We are not playing with the norm, the inner product again. We are looking at, for instance, the Adama manifold, where we look at the exponential function now. We have to see, one of the problems I face is that, how do I write some of this algorithm in this? How do I write it in this space? So sometimes when you're able to write it, then we now look at it. How do I compute? So sometimes you have to bring in a new lemma that has not been proved. You have to prove them so that it will help you to at least bypass this. So in this paper, what we did was we considered 2-step inertia, because it is known that 1-step inertia sometimes might not guarantee convergence. So we tried to put a 2-step inertia there, and it is a problem I saw from one paper, and I said, okay, can I see if it's going to work here, which we're able to do. And also, this is another problem of variation inequality problem that was solved with some of my colleagues. We tried to solve this in Adama manifold. So what I'm trying to do is that we have considered this problem from linear to some nice non-linear space. This is another one of the paper we did with some of my friends, with Professor Tan and Professor Lee in China. This was published this year. We tried to consider that same variation inequality on Adama manifold, and be able to achieve something nice. This. And lastly, this is another paper I published early this year. Yeah, this is a paper I wrote a long time ago, so it was published this year at the Proceeding of the Edinburgh Mathematical Society, where we consider the linear convergence. Now, it's no more normal inertia, but an alternative inertia where we consider the even and odd of the Z method. Now, I use the Z method, not the projection and protraction method. I use the forward, backward, forward method. Now, what am I solving? I'm solving a new problem. That's the inclusion problem there, on Hadamard manifold. So this was one of our paper in nonlinear space, which means we are not all, I'm not just working in Abass space. I do Abass, I look at another structure, Banach spaces, then now we are now looking at nonlinear spaces because we see that we can easily find some real-life application in that space and say, okay, is it possible for us to now consider all these spaces and at least do our work there? But we are trying to bring in some new thing. And again, there is this thing I also like to look into. There is recently we see people doing stochastic optimization problem. I've seen some nice results there, but we still have very small result there. I would like to be considering that in nonlinear spaces, like I said, because we have done something like that in Abass spaces, but we want to see how possible we can take those things to nonlinear space and be able to bring out some nice result there. But for now, we are still there struggling with the geometry, learning the geometry because the geometry is wide, and see if those things are possible. So these are my references. Thank you very much.
Abass, this Hadamard manifold is a generalization of Hadamard space with respect to yesterday.
Okay, you will see Hadamard space. Hadamard space is bigger. Hadamard space is bigger. In fact, I've worked in Hadamard space also, but Hadamard space is not because of the geometry of that space. We are not able to bring in some of these optimization problems. If you see people that work on generalization of fixed point problem, like Professor Pant or Shukla, they work in Hadamard space. If I'm working in Hadamard space, the optimization problem I can solve I can solve those sum of operators. We have done Bayesian inequality problem in Hadamard space, but the problem is that the operator there is just non-expansive. Once the operator is non-expansive, we are putting the operator to be monotone, then we might not be able to survive in that space. So for now, that's why there's still room. There's a lot of work are still needed to be pushed into the Hadamard space. But Hadamard space is a bigger space.
This is a smooth manifold.
This is the Hadamard manifold. It's just your Riemannian manifold that is complete and has a non-positive power. So it's still nice in the sense that if you are moving a work from Abass space to manifold, there are still some. If you look at, let me give you an example. If you look at our Riemannian manifold, we have examples like the hyperbolic spaces. You see people that work in hyperbolic spaces too. It's just like the Hadamard space. What they do is there is just generalization of fixed point problem. They are not, all these optimization problems have not been done there. But Hadamard manifold, we are still exploring. It's something still new. People are working there, but we are trying to see how those problems can survive in those spaces, which also myself and some of my colleagues are still trying to. I remember one of my friends from Israel was going to say, Abass, we can do something in this space. Let's see if we can bring in some of this. So we are trying to go there. And one of my master's students is also working in Hadamard manifold. So we are still trying to survive in that space.
To ask a question about your very impressive publication record. We're all envious. Many of us are envious to you because you have more than 70 papers since last few years, right? And many of your papers are in extremely good journals, like some of the ones that you showed us. How does it work?
Okay, you see, one of those things that help me is collaborations, because In fact, sometimes I'll just be in my office or in my room. And again, like I do tell my students, we hardly sleep. I'm there sitting with a problem. You know, I told the prof yesterday, I was rushing to a meeting with some of my colleagues there. So what we do is, there are a lot of collaborations coming in. Say, Abass, I have a work I'm doing. Can we do this together? So what will be your contribution? So sometimes my contribution might just be solving some of these problems. Or in fact, sometimes in the course of discussion, we see some open problems and we try to see how we can solve. I told Professor Aphane yesterday that I've been taking a walk with me for the past, I was in Cape Town last week, for the past 2-3 weeks. I want to do it, but because there is no time, so I thought that maybe when I go home for holiday, I will be able to sit down and do. And we have piles of work. In fact, we have accepted papers in some big journals there, demonstrate mathematical and some other papers. But again, let me say, I'm happy because the department is giving room to do that collaboration, and also some of these papers, though the way I was trained by my supervisor, it doesn't like you publishing in journals that take money. They put it in a big paper journal that let it spend 2-3 years, then we know that we have done something nice. But see, the department is also helping. We try to consider some paid journals, though the big ones. One of my students, the one that graduated recently, we were able to publish in a journal of applied math. It's an Elsevier journal, which is something that will help also. So collaboration has been helping me. I have a lot of my friends that we did this thing together, like Professor Chinedu, I don't know if you know him. He's in the University of WITS. I have colleagues in China. I have colleagues in some European countries that they can just call me and say, see, there is this thing we want to do. Can you join the project? And we join the project and we contribute. We meet maybe every Saturday. There are a lot of meetings. So it has been helping. But I always say something. You see, when you work with students, sometimes it makes you calm down because it depends on how the student can do the work. Sometimes you have to publish in some small journals because you want to bring them into this thing. But as time goes on, you tell them, see, I'm publishing here because of you. Now we are not publishing this Q4, Q3, we want to go up there and do the thing. So I give them, go there for 3 months, go and bring something nice for me. And again, I'm also prognosing into some new fields. I want to see if it will help me. I was talking with somebody in Dubai last week. I saw some of his work. I said, no, this is nice. I can bring in my idea, and I said, okay, let's do something. So we said we are going to be meeting and bringing some nice results. So collaboration is the key, and also a conducive environment. You know, Professor Aphane has been trying with that, and I think it has really helped me because I think this year I got my NRF rating this year, and see, we are pushing, and we should really get there.
And if I could ask another question, so do you consider yourself as a fine mathematician or a pure mathematician?
Pure. We are pure, because what we are doing is kind of abstract. That's why I said myself, when it comes to the application part, we bring in people that are in that field and say, okay, please do this thing. Though I told Professor Aphane, which is one of those things we want to discuss here, said we need to get some of these mathematical tools like Python and this. Bring in experts, at least they should come and teach us some of this. We don't need to go there sometimes. Sometimes they are busy. They keep our work for months because they have a lot of. I told Professor Aphane, I have a friend that will tell you, before I can implement this thing, I'll take $100. You see, he's getting money from it. So he will tell you, I don't need to put my name, just pay me that money, I will do the implementation. But if we can train 2, 3, 4, 5 students that can do that job, I think we are fine. So.
Any other questions or comments? Well, thank you very much, and congratulations for your big achievements.
Thank you, Steve.
will be giving the next talk? I give you the time. So we have just two presentations this morning, right? Yes. Then we have. What I'm saying is that it's already 7:30. We have to crash because.
Yeah, I want to make it. Yeah. Let's see.
Okay. One next speaker is from Malose Mokonyama from Fatlane, and Kishan about comparative analysis on some calculated child topological indices on some properties of them.
Thank you, Prof. Good morning, everyone. I'm going to be giving a talk on comparative analysis of some Zagreb type topological indices on certain physical properties of thin isomers. So there were two presenters yesterday who sort of gave an idea of what I'm going to be talking about. And what I'm going to be talking about, there will be some actual data that will be actually putting life to what the two presenters yesterday they were talking about. Okay. So this is a way of, if we check experiments are expensive because you need to be considering the cost of chemicals and the time taken in the lab and all that. So here what we are trying to do is we are trying to bridge the gap in a way of trying to predict some of these physical properties. So here I'm going to be looking at octane and its isomers. And this is how my presentation, the outline of the presentation. And so we're just going to be diving into the presentation. Graph theory has been, there's some work that has been done in graph theory, and most of it was, or it is in terms of trying to reduce the cost of doing things, because I mean, we know that economy is not good sometimes, and we need to save as much as we can. So in order to do that, we try to come up with, we can call it some theoretical work, and try to see if that work, how does it can relate to the practical way of doing things. So a lot of researchers have done some work, introduced some topological indices. And the first one was introduced by Harold Wiener when he was trying to work on the boiling point of alkanes. Okay, so this is not much different. It's in line with what Harold Wiener did in his work. So one of the topological indices that was also introduced was the Zagreb index, and which was developed by Goodman and introduced by Goodman and Tristan, and they used it to examine the relationship between molecular structures, and the total energy of pi electrons. So I'm going to be looking at those Zagreb type topological indices in this work, right? And the first one is the first Zagreb topological index, which can be defined in terms of vertices or in terms of edges. But here I think I'll be looking at the one in terms of edges. So this is how and then we have the second Zagreb. Remember, it's a Zagreb type topological indices, right? So we have the second Zagreb, which is defined as M2 there. And then we have the neighborhood Zagreb. And then from there, we're going to have the first LIP Zagreb index, LM1. And then we have, we have the neighborhood Zagreb index, which is MN. And then we have the neighborhood second version of second Zagreb index. And then we have the first LIP Zagreb. Then we have the second LIP Zagreb, which is defined by equation 6. Okay. Now, as we try to do these predictions, we need to be looking at the standard error of estimate, which is defined there as the estimation of the accuracy of any prediction. Okay, looking at the main results, remember we're looking at octane and its isomers. So we are going to have that graph there, where we have the octane graph. And when we look at, sorry, I forgot to label the tables, but as we look at the first table, it says the degree-based vertex partitioning. So we are partitioning this graph here, this octane, in terms of vertices. So when we check here, when we look here, we have CI of degree 1, right? So we're looking at a vertex of degree 1. When we look C1 and C8, we'll have that degree 1. Okay, and then there are 2, so it's C1 and C8. Then this one, the vertex of degree 2 will have from C2 until C7. Okay, that's in terms of vertex partitioning. Now, in terms of edge partitioning, so I will look at a vertex that has degree 1 and 2. So if we check C1 and C2, C1 has degree 1, C2 has degree 2. So we have 1, 2. So the same will apply to C7, C8, which is there are 2 of them. Now we're looking at the one where we have 2 degree 2, 2, we'll have C2 to C7. Okay, and then we have 5 of those. Now, here what we're doing here is that from those topological indices defined above, we are doing some computations for the octane isomers for each graph. So this will be for the graph that was above there. So we are going to look at the first subgraph of that structure up there, right? Like in terms of edge partitioning. So if we checked there, we had where we have we're going to be using this table. So we have 1, 2, and then so we have 1 plus 2 degree of the first C and the degree of the second C, and then we have 2 of those. Remember at the end of the graphs. Okay, so this will be the first subgraph computation of that octane. So similarly, we're going to compute all of the topological indices for those octane isomers. Okay, and after we do that, we are going to use or we use some linear regression here, and then to come up with some regression models. Okay, and equation 8 is there, the model that we are following there, and we're going to model the physical properties of those octane isomers using that equation 8. And then, so this is the regression model for the first subgraph M1. So the physical properties we're looking for is the eccentric factor, entropy, and then there's the refractive index there. Okay. And then we're going to do that for all the I think there are 6 topological indices. The subgraph type topological indices that we have defined there. So we're going to do we're doing the models for each of them. Okay. So if we check there, that says the table should be say the physical properties of those octane isomers that we're looking for. So these are the experimental data, the ones that they did in the lab. So we are trying to use these topological indices and to see whether we can predict, if not all of them, some of them, of the results that we see there. And this table is the data from the computations of the topological indices. After computing all those topological indices for each of these are the results of the computation. If we remember in the previous slide, the first subgraph that we computed there was 26. So these are the data that is coming out of that. Okay. So on this table, we're having comparison of the actual and the computed values for, so this is for the eccentric factor. So if we look here, these are the values that are coming from the experimental data that we got from the literature, the sources there. So these are the experimental data. And then from here going there is the computed values coming from using the topological indices and the regression models that we have. So if we check for octane, they got 0.397. And for acentric factor for first Zagreb, we got this. But when we look at M2, we got 0.39. And as you go on, so the values you can see, they are not far apart from what they are getting into in the lab. So what if we have computed? We are not far from what we are trying to estimate. We are not far from what they got from the lab. Okay, so this will be in terms of the acentric factor. Now we're going to look at the entropy. The same thing applies. These are the values from the lab. These are the values that we computed and using also the regression models. So you see, say here the values are not much far apart from what they are getting in the lab, what we have computed and calculated there. So refractive index, same. We're getting some nice results there. And then this is the standard error of estimate, right? So if we look at M1, right? We look at M1, and then this will be the standard error for estimate for acentric factor, entropy, and refractive index. If we look at M1, so this will be the lowest error there. We look at LM2. Now we have this as the lowest value there. Okay, meaning that our standard error is very low. So meaning that we the predictions that we are making there are very good. Okay, and then the table there shows the correlation coefficients. And then we have some statistical parameter there, and then we have the R squared and the which have some nice values there, positive values. So we have for all of them. Now, what we can conclude from here is that the QSPR study of the second Zagreb reveals that LM2 with the second Lip Zagreb can be useful in predicting the refractive index. As seen in the standard error table, the estimate is very low. So what I'm talking about is this. So LM2 is good for refractive index, as this value is very low. Okay, and then the second Zagreb M2 predicts the entropy better as compared to the other topological indices. Okay, let's go back to the table. So when it comes to entropy, so we see in terms of entropy, the lowest is M2. Okay, and then again, in terms of acentric factor, the lowest will be M2 star. Okay, so those are the, meaning that the neighborhood second Zagreb index is useful for predicting or is better for predicting the acentric factor. Okay, and I think this would be the end of my presentation. Just a disclaimer, I haven't put the references, but I would put before sending the final. Thank you very much.
Thank you very much. Any questions? Yes, please.
Thank you, Mr. President, for that presentation. So, all I want to know that the first report you got from the lab, Python, MATLAB, or the previous articles.
Okay. I'll use this table. This is what has been done in the lab. This is the values that they found when they were doing the experiments. Now this one, I used SPSS. It's a software, statistical software that you use to do some analysis, data analysis, and yes.
I don't know if you take the SPSS, but I want to understand how you use the topological indices. Is there like an equation you use to equate like maybe those properties of entropy like using the value of the topological indices? So I just want to understand, we need to compute those properties using the topological indices. So the equation that was used in order to compute
Equation 8.
Oh,
So P there is the physical property that we are predicting. Yes. So equation 8, and this would be for the first diagram. So this is their physical property that we are trying to predict.
and then TI
Is the topological index.
Could you please go back to that table?
Right.
That one. No, not that one. The other one. Still the other one. That one. Yes.
Yes.
So, eccentric factor. This is a chemical property, right?
Yes.
What does it mean? Or maybe one of the other ones. Any one of them. It doesn't have to be eccentric factor. Maybe we can look at the other one.
Okay. Let's look at the entropy. Okay. Entropy in terms of chemistry is it deals with the change of the heat transfers on the molecule. So there's entropy, there's also enthalpy.
And how is it measured? Using some chemical tools or?
Okay, it's measured in the lab. There's some
It's something that chemists measure.
yes, in the lab.
Something that chemists
yes.
Now,
So all those physical properties are measured in the lab.
yeah.
So what we are doing, we're trying to see if without going to the lab, can we come
No,
up
I
with
understand that.
yes.
Now the other columns,
Mm.
you're using some topological properties of graphs to generate those values.
Yes.
How did you know where to begin? How did you know that for entropy, you should have, because these predictions seem to be quite accurate, right?
Yeah.
Which is fantastic. But how do you know? How did you know where to begin?
Okay. From the work of Harold Weiner, when he started introducing these topological indices, he started looking at he was trying to find the boiling points of alkanes, right? So what I did is following in those and in the idea. What we did here is we took other topological indices. In this case, only the Zagreb type topological indices, right? And then we computed the topological indices. For instance, you see, for this is the topological index for that, the graph on the other side, right? So we are trying to see if we can take these topological indices and predict those physical properties.
So in the beginning, you didn't know which index.
I didn't know
would
which one
match
is
with
going
which
to,
property.
no. I didn't know which one is going to.
So potentially, is it possible that maybe tomorrow we can come up with another index for graphs that might predict
Yes.
some other property?
Yes,
Thank you very much.
thank you.
But then how are you sure? As you mentioned that you use
SPR.
SPR, how are you sure it will give you accurate result from going that and from that?
First of all, I am not sure that is going to give me, when I start, I don't know what I'm going to get. But after doing the computations and the regressions, these values there tells me, the standard error of estimate tells me, if you check, this is a very low value, right? This is a very low value. So this also tells me how accurate the result for that is. So the lower the standard error of estimate, the higher the accuracy of what you're looking at.
So maybe if someone can take this result and go to the lab, will get the same result.
Already they have done this. I'm comparing what is being done in the lab. This is from the lab. This is what I computed.
I wanted to know if you use the word
SPSS.
So I'm saying if I use a different what
Software. Yes.
Why think why
The choice of SPSS is what I was available to me. You can use different softwares to do the analysis. So SPSS what was what was available to me at the time when I was reading.
Because to me this is my first time learning. And I wanted to understand.
No, you can use any software that is available to you.
Oh, my concept of
I think it's because you've not SPSS have been used. It's something that has
You pay for that.
for years. In fact,
SPSS.
most of the things SPSS can do, some people can use.
Well, the university used to have a license for this, but now I think they are moving from that. You know, when the license expires, it takes some time to do the renewal and whatnot. So the last time I checked, the license had expired, so they were busy with some renewal. I don't know how far they are now. I haven't checked.
Okay, so let's speaker, thanks once again.
Well, thank you very much for the presentations once again. It was very, very exciting presentations and your personalities. Yeah. The more we progress into the workshop, the more exciting it gets. So we have half an hour remaining in the presentations slot. And since we don't have any other presentations, I would suggest following Professor Aphane's suggestion yesterday, maybe we can take this half an hour to start talking about very broadly what we want to achieve with the workshop. Of course, we will talk much more about this later on as well, when we will be looking specifically at kind of mapping out the mathematical structures at SMU. We've already have a good idea of what these are. We can map them out and take them forward. So we can talk about concrete mathematical details later on, but maybe now in this half an hour, we can make a very broad, bigger picture plan of where we want to go with the workshop and also where we want to go after the workshop, which is even more important. What I'm going to do is I'm going to draw on the screen. I'm going to open something, and when you give input, I'm going to put it on the screen. Just give me a minute or two to prepare the screen.
Yes.
I should tell you. Okay.
Wow.
Okay, I'll tell you what I meant. But I was going to start with this question that what do you want from SMU? How SMU can help to study emotional units. So that is how I was going to start my presentation. But from SMU, what we will have to have, one is a scholarship for our postgraduate students. And then number two, to have this type of workshop, maybe 2 weeks, 3 weeks, crash course for our honors students, master's PhD students, if it's possible. And then number three will be, as you are aware that we don't have enough experts in the department, maybe in the form of postdoctoral, if we can have postdoctoral in the department, that will be lovely. Our students, they will perform better if they've got people on campus to hold them, and then the other one is, this one is just something that I wish we can have tomorrow, software, Professor, the overleaf software and the Python. Dr. Abass has just mentioned that colleagues, they even go to an extent of paying from their pockets. That's how SMU is surviving, that they run the result for you, such that you can have your different plan. So we are working, but there is a lot of desperation for us to make things happen. Then the other thing, Prof, you know this structure, when we came in here, we would love to have, you know, for our student one day, Prof, to work up and be in this type of a classroom for our postgrad student. I'm telling you, Prof, we don't have anything, but with the little that we have, we were able to be when we are. And what about if we can get things like this, if we can get postdoctoral from our side, if our students can get this opportunity of coming this side 2 weeks, 3 weeks, being grilled by you guys, you can foresee that we will be in a better position. I don't know if I've missed something. Crash courses, postdoc, overleaf, yes, and Python. You can maybe just say software.
Python is free. Spider.
Spider is free.
Yeah, Spider Python. Isn't it good? Spider Python.
Yeah, I think Spider is free, but I think some of our like Shafi is using on The one chapter is requires solution. But spider is free, I know spider is free. But at least overlay for now is to let's start from that.
Yeah.
Thank you very much for this input. I just want to make, before I also want to make input, but before I do that, I want to make comments on what you've said. So you said at some point that you would like to learn from us. Well, we also would like to learn from you. We have a lot to learn from you. I have a lot to learn from all of you. Like, for example, just one example, the amazing work that Dr. Abass does, the amazing network of collaborators that he has internationally. This is hard. Yes, it is very difficult to have such a lively network, especially for pure mathematicians in South Africa. We struggle with that.
Yeah.
If I can ask you, are you South African?
No.
You see, that's our problem. South Africans struggle, but then our colleagues from which country are you from? Nigeria. Our colleagues from other neighboring or not so neighboring African countries, they're so good at this. They come to South Africa, and we have so many academics in pure mathematics that are not South African, from other African countries, but not South. I'm not South African, not from Africa either. He's not South African. Eric, one of the lead researchers, is not South African. Cyrene is not South African.
No, Cyrene is South.
No, Cyrene is South African. Sorry, Cyrene is South African. When she's in South Africa, that's right. So there is something that there is some kind of transfer of knowledge that needs to happen.
Yes.
And the students here, you're South African, right?
Yes.
So please copy Dr. Abass, become like him, and like many others. There is something in South Africa that doesn't work, and also Professor Aphane is an amazing mathematician. So, but there are so few of South African amazing mathematicians that are born in South Africa. There are very few of them, and we want to grow that number. And guess what? The government is on our side. The South African government wants to grow mathematics in South Africa. They are keen to invest as much as it takes to grow mathematics in South Africa. So we have so much to learn also from you. At Stellenbosch University, for example, in pure mathematics, do you know how many honor students we have every year?
No, tell us.
2 or 3. There has been years when we had 0. There has been years when we had 1. You see, we have something to learn from you, Professor Aphane, who's managed to build this amazing group at SMU where students are inspired to do mathematics. We have a lot to learn. Now, coming to the specific topics. So one thing I want to add to this list is integration of everyone who is here. In the focus area.
Okay, we forgot the community engagement. Remember, we recorded that.
Let's add that as well. Community engagement. And I think for mathematics, community engagement should mean just one thing. This is to inspire young kids in mathematics. I think the passion is there, it needs to be unlocked. If you don't know mathematics exists, you won't be passionate about something you don't know exists. So we have to tell them that it exists. Inspiring school learners and undergraduate students in, let me call this mathematical exploration. one could ask, I mean, we know that in South Africa, we have a big challenge of pass rates in mathematics. Lots of kids do very poorly in mathematics. And I think this is something that needs to be addressed. But now, there is another gap as well. Not only we have that problem, but we also have the problem that very few kids in South Africa know that they can continue studying mathematics at university.
Yes.
Very few kids know that they can be very good at mathematics.
Yes.
So I think in the context of the institute, where the institute is kind of driven by research, I think our community engagement should be to create this pool of students from school and from undergraduate who would complete mathematics degrees. Some of them might become researchers, some of them might go into industry. But the point is that instead of kind of trying to think about the pass rate, let's think about those kids who are doing fine. They're passing mathematics, but they could have become excellent mathematicians if they knew that mathematics existed.
Okay.
What do you think of that?
Yes, Prof, community engagement is what we have incorporated on the mathematics
Mathematics
campaign.
campaign. Okay.
We campaign through celebrating mathematics days, Pi Day, Square Root Day, Pythagoras Day. We are and making the learners aware that there is a Square Root Day and is celebrated. How was it given birth? Then after that, we give them the exposure to the programs that are offered at tertiary and then the type of job that they will be getting after they complete it. So we are using those mathematics celebration days to campaign for mathematics.
But we already have that in place, right?
Yes,
yeah.
we do have that in place, and we are sponsoring that from the department's budget. So will we be able to sustain that? That's a question from the department side. If maybe there is a way under the community engagement where we can get some funding, then it will be glad to have that.
Okay.
What UP does, they print the t-shirt written ID, and then they distribute those t-shirts. Elena having that t-shirt, Prof, it will leave a mark.
I think that I would think that from the standpoint of NETHEX, I would think that we want to do something even more impactful.
Yes.
Than just that.
Okay.
Maybe a kind of club where students enroll in this club. It could be a national mathematics club.
Mm-hmm.
We actually already have such a club. It's called Future Mathematicians Program at the South African Mathematics Society. But it doesn't matter what the names are. So a kind of club where students enroll in this club, and then through this club, they have interactions with mathematicians. We visit the schools, we visit them. Sometimes we invite them, and there is a lot of mathematical activity that goes on through this club. Not just, I mean, what you're saying, this campaign is very important, I agree, and it has to be there.
Mm.
But my feeling is that anybody can do that.
Yes.
It doesn't take a researcher in mathematics to do something like that.
Yes.
But where we can put a value, where not everybody can do,
Okay.
is showing to kids the excitement of mathematical exploration, the process of mathematical discovery.
Yeah.
School teachers do not know how to discover mathematics. School teachers know how to teach mathematics that's already discovered and written in the book, but they don't know how to explore mathematics, and we know that. And isn't that what makes us passionate about the subject, the process of discovery, right? And so if we can communicate this to these school learner as well, then they will also see the same passion that we see. So that's what I meant by mathematical exploration. So maybe some kind of we can have, and you said that there is a school near to SMU, not,
Yes.
which is mathematics.
When system makes and science only. But when I is
Let me just.
yeah.
So by the way, this future mathematicians program I've been mentioning a lot of times, Sirin Ratilal is the chair of that. It actually originated from our focus area. It's actually a project of the focus area.
Wow.
So let's think in the direction of implementing this program at that school, which is I want to write the name of the school.
Yeah, it's there.
Yeah.
Very nice.
Yes, she's doing a lot. Yeah, absolutely, yeah. So this is, it will be nice to have a very concrete plan. And you see, like, for example, when we have a next workshop like this, maybe at SMU, when we come, right? Maybe you said 2 or 3 week thing, right? Out of that, 1 or 2 days we can dedicate to go to the school and interact with the kids there, all of us. So that's how we can start, you know. Okay, so let me highlight kind of the things we want to deliberate further as we move along in the during the workshop, and if there's anything we missed.
What else? Did I miss anything? Yes.
The next is Mapena.
Well, the name of the school is Mabena.
Abenadi.
Did I miss anything?
MAPE. PEMANE.
Yes.
And then that's yes, Science and ICT School of Specialization.
Fantastic. I didn't even know the school existed.
School of Specialization.
Do we know anyone who teaches there? Do you have any contacts?
Yes, I do have some contact. I think it's the principal or deputy principal.
Fantastic. So we can begin with those contacts, and then we make an official partnership with them, where they will be integrated in our meetings. Sometimes maybe a few of the kids can come with you when you come to Stellenbosch.
And the nice thing about the school is, initially they used to have maths literacy, but they are phasing it out. I think
That's good
grade
news.
10 of last year. From last year, they are phasing it out. I think next year will be the last metric with.
Yeah, that's great news. That's great news. Now, okay, so let's just go over one more time the things we pointed out, so we're sure that everything is there. Postgraduate student scholarships. Now, here we are referring to in the future as well, but specifically for the students who are here. Okay, so every single one of the students in this workshop, we all at the focus area, yourself, myself, Amartya, we will make sure that they have scholarships to move to the next level with master's PhD. And we will identify universities. We will engage with the university management. Tell them we have amazing students in mathematics, which is very rare, by the way. I don't think we will have any trouble finding faculty. I think it's very easy. So that's very concrete action item. Everyone who is here will have a postgraduate scholarship for the next for continuing their postgraduate studies in mathematics. Do you want to continue postgraduate studies in mathematics, by the way?
Before we find scholarship, they should
Yeah.
tell us that if they want to do the next level.
You ready?
You don't have to say yes. I mean, So because there's also jobs out there. I mean, that's where we actually struggle. That's why, you know, the reason I'm gonna give you a word now. The reason why we struggle to keep talent in pure mathematics, especially, but not only, also in applied math in South Africa, South African talent, is because South Africa is lots of opportunities. So as soon as there is somebody who is talented, a young person who is talented, they immediately get absorbed into industry. That's why we struggle. So when I'm asking you, do you want to continue? It's actually a serious question. It's not about, so you might get a job offer in industry, which will be even better with the scholarship. So that's the context in which I'm asking you. Do you want to continue with postgraduate studies? Yes.
If we continue, we will visit the talk for the iPad for.
Good one. I like that. I think you should. Yeah. So the scholarships should come with a laptop or iPad or both. Scholarships should come with
So can I ask?
with a high quality laptop or iPad.
So with the scholarships, how is it, you know, are you gonna fund us? Are you gonna do that size? Are you gonna tell me sometimes?
Anything is possible. So first of all, we'll have to have the mathematical structure realm in which you want to work. And then we'll identify who is keen to supervise those kinds of topics. For example, I personally, I'm keen to supervise anything that, or supervise or co-supervise anything that we've seen so far. I'm very keen. Of course, I'm not an expert in everything. So in some of the cases, I have to be a co-supervisor, not the main supervisor. And then wherever the supervisors are based, then we can choose, and the students can choose where do they want to be registered. And then wherever you want to be registered, then we approach that university's management and tell them, give us the bursary for our focus area, students in our focus area. That's how that's how I see it working. Yeah, now that's not for you. I mean, of course you can also benefit, but this is a big, because this is already kind of the crash course thing we're doing here. So you don't need this second item in order to be able to do masters or PhD in what we're discussing now. You're already ready for that. So, but now for the future students, we can talk about it. So if anybody wants to, for example, now I don't want to. So we have to be careful that, because you said earlier that you have so many students that you want to be able to keep all of them at SMU. Is that correct?
Yes, that's true.
Yeah.
Because the other thing was try to encourage them as well to come and enroll at SU.
Yeah, because definitely I can say that any one of you who wants to do masters or PhD at Stellenbosch, I'm very happy to supervise, and we also have postdocs who are co-supervisors. They help anybody who wants to come here. That's done deal, except that we still have to get confirmation of funding. But as I say, that's our commitment, and that's what I'm quite sure that we will success. There is also another path. Another path is through AIMS, African Institute of Mathematical Sciences. That is also a very exciting opportunity, extremely exciting opportunity, but that's a bit of a detour in the sense that you first have to do coursework there, a lot of coursework. And so you can still do that, but that kind of goes a bit on the tangent from our focus area. And this workshop is funded fully, not by AIMS, not by Stellenbosch University, by our focus area. So that's why we're kind of promoting the focus area. So anybody who wants to integrate in the focus area, the first option is to already start working with a supervisor that's in the focus area. But if you want to go to AIMS rather, if you want to, we have one of the people, not lead researcher, but one of the people in our focus area is actually director of mathematics at Ames, Mr. Karen Hobble, and she would love to consider your application with the Ames intake happens every start of every year, I think. So that's definitely another opportunity. But I think the priority is supervision under lead researchers of the focus area. Yes.
With the aims, our students they are already aware. Some they didn't apply directly. So we have students that are assigned.
Right.
So aims is not an issue.
Right.
They are aware of.
Fantastic. Yeah, fantastic.
So those who will want to aims, they will not even have and report to us. They know where to.
Fantastic. That's right. Yeah. So that's you're right. That's already there. So anybody can do that. So here we are creating something
That's right.
new and
Yes.
something special, something that didn't exist before.
Definitely.
Okay, so by the end of the workshop, we will have a very clear idea what is the next study plan for each of you here. And we will then start implementing it as soon as the workshop is finished.
Okay.
Does that sound like a good outcome?
It sounds like a good outcome. Can I ask on the issue of scholarship? The ones that you have, what does it entail? It cover the study fees and what and what and what. Talk to me as someone
yeah.
who doesn't know anything.
I'll do that. So, scholarship is supposed to cover living expenses. There's supposed to be sufficient money that accommodation is also covered. And also scholarship is supposed to cover registration fee. So your food, your accommodation, and registration is what the scholarship usually is supposed to cover. Now, the usual scholarships sometimes are not very big. Usual scholarships, especially if Stellenbosch is an expensive town. But we're not going to get a usual scholarship. We're going to get a scholarship that can really cover everything, including the laptop and iPhone. So, yeah. Of course, we will not be able to get a scholarship that's too high. I mean, there's some brackets, but we get to the close to the top of the bracket, it should be able to cover everything. Okay, so that's a very clear goal we're going to arrive to at the end of the workshop. Everybody is in on that? Yes. Fantastic. Now, for the future crash courses for honors courses for honors students, we've been having them. You didn't know about it. We didn't know that we should tell you because we didn't know about you too much. We have NITEX online courses. I've been giving category theory courses, for instance, for many years now, and all of them are uploaded on my YouTube channel. But I think what you want is also in person.
Yes.
Yeah. So how about the following? You do a NITEX course, but it will be intensive in a short period of time in person. So maybe someone will visit SMU, give a course from SMU, but also for the whole country.
Yes.
So we can use NITEX funding for that. But then there will be one-on-one interaction also. So that's something that's we're going to actively implement. So this is in-person SATAX refers to South African theory and something school. In-person NITEX SATAX courses. So there is already structured NITEX for giving courses, and we should use this structure. The question is, do you have a facility like this with a camera at SMU? No. Can't we get it?
If NITEX can come and spoil them.
But isn't there now? I have to be careful because this is everything is online. But isn't there isn't there some investment towards HDIs that can be used for this?
The deals for the rooms that is available, that is used by all the departments.
Okay,
So it might not be available for the entire week, but for certain days, we can do the bookings.
but what if we set up like this type of space? If we want to set up something like that
That's why I
and an
said,
HDI,
yeah, the structure that.
Yeah.
If we can have.
this will be useful for courses, for national courses from SMU.
Yes.
So if we have something like this set up, let's say, right? Does SMU have funds to invite the guest lecturer? Or it-
From the department side,
Yeah.
yes, we'll be able to, we are doing that actually. This year, we invited Professor Nayem for 3 weeks. Was it the open? Yeah, last year we invited 2, so we keep on inviting at least experts. Yeah, last year it was 2, and then that other year was 2 as well. Yes, so we do have funds to invite.
So the government often encourages, and not often, like always encourages, that the resources are accessed by colleagues from HDIs, because if you look at the competitive numbers and things like that, HDIs are not performing as well as, let's say, Stellenbosch University. So because of that, there is a lot of attention on HDI. The government wants HDIs to be very highly performing in science. And I mean, from this workshop, it's clear to me that SMU is already very highly performing in mathematics, but not necessarily in everything. Is it not easy to set up something like this with the intention to do what government wants us to do? Is it not easy? Not necessarily from the funds that are already allocated to SMU, but is it not easy to get funds to set up something like this at SMU?
Prof, let me answer this question with you. I wish I can invite you to the office. You come and see the items.
Okay.
Our offices is not even in this real structure. Is the Wendy, the mobile, whatever you call them, offices.
Really?
Preferred building, this preferred building.
They call them the prefect. Yes, it's not even in this real.
It's not a real building.
It's not a what? Our offices.
Really?
And in those offices, we have got 2 bathrooms, one for female, one for male. How many are we? There was a time where the men's bathroom was waiting for the entire 6 months.
How are you?
Everyone is sharing except.
How are you able to do so much things?
It's inside one office, you find it depends on. So if everyone is there.
All these are online, so you must be careful.
Are we saying anything bad?
So, speak, must be careful.
Yes, but we're not saying anything bad.
Bad.
Professor Aphane, did we say anything inappropriate?
No, we are expecting them.
Yeah.
Yes, so that is, we are sharing offices. So
Well, that I think is even maybe, it will make it even easier to set up an institute.
It'll be the best. We don't even have a postgraduate. Like even postgraduate, even anything regarding research in terms of facilities, so that at least even to conduct weekly seminars.
Is there land?
And it's huge. Huge.
So
they
if there is, let's get investors. Let's approach investors to set up Mathematics Institute at SMU.
That would be great. That would be something that would be
Good
like
project.
great.
Perfect project.
You mean like an Ames equivalent?
Maybe AIMS would want to help as well. Anything where it will be possible to have a space like this, where we can, where somebody can go there to give an intensive course, and this can be transmitted nationally for everybody to benefit.
That aims like this.
Now, that idea of setting up something at SMU, some kind of new structure, will be also feeding into the community engagement aspect, because there could be some portion of that structure which is dedicated to engaging with the school learners.
That would be great.
How far is this from Pretoria?
27 kilometers.
Sorry?
27 kilometers away from Pretoria.
27,
27.
It's not far from town.
no. But it's far from the airport, because
Airport in Pretoria. And far from Gautrain also.
From there.
and are there guest houses and hotels?
The guest houses are very nearby.
We don't have to set up a guest.
Because the guest house. Now, for now, we are interested in having resources for the department to the students. Yes, so that one will be very good.
Yeah, so we have to approach investors. I will talk about this with the director of DTEX, how we can do that. And let's do it. So DTEX offices at SMU.
Yes.
If maybe, yeah, I don't think NITEX will be able to fund themselves, because NITEX is for the whole country. But maybe we can have a project under NITEX that gets the investors buy into promoting SMU. Okay, so that's one other thing. And then you talked about postdoc appointments at SMU.
I was going to see.
So that's something that no, we're supposed to have a break, and I'm kind of wrapping up now. So the postdoc appointments at SMU, I don't know yet how to begin thinking about it. So let me still mark it, but maybe with a different color. This is something that I need to talk to the director of NITEX to see if NITEX postdocs can be exclusively allocated to SMU. I don't know that. But the overleaf subscription, that I'm sure we should be able to fund from our focus area. What do you think? For the entire focus area. At Stellenbosch, we recently got departmental subscription to overleaf, so anybody coming from Stellenbosch won't need it. No, we're not going to fund any institution. We're going to fund people's overleaf subscriptions.
Individual.
Yes, individuals.
That's much more expensive than.
No. It will be groups, but what I'm saying is that it will not be that we are funding specifically one university's overleaf. We're funding researchers that are actively involved in our focus area for their overleaf account. Whoever these are, and Professor Aphane is a co-coordinator, so she will have overleaf. I don't need, because I have one from Stellenbosch. I don't know if you have.
Yeah.
You also have. So many of us will not need, but those who need, we pay for their overleaf from our focus area funds. I don't see why we shouldn't. I think it's most appropriate to do that. Yeah. Yeah. Is every, yeah. I don't see a problem with that. I think we'll just go ahead and do it.
If we have subscriptions, we can share.
The students will have access to it through you. You will have an account which will be a group account. And so your colleagues and your students can also use it without having to go through your login.
How to get access.
And
So, sorry, Zurab,
yes,
we're just having a subgroup discussion here. Just about that overleaf.
Can I access overleaf subscription with my email?
sorry.
How does the overleaf?
Because I have Stellenbosch email, so is it automatically, can I
In
get?
my department, it's mathematics division
Okay.
specifically.
Oh, so it's not the
So I
whole
don't know if it's
university.
you have to check with applied mathematics division if they also do
Okay.
it.
Yeah.
If they have a subscription.
When I recently my Stellenbosch University email address there, it wasn't automatic.
No, it's only for staff members in the mathematics division.
It's by invitation actually.
Liam Baker is the one who is the main overleaf account holder and yeah, so, but we can bring this up in our division without you can bring it up with Professor Boxall, ask him.
Right.
And so you could also ask your division head about that. Okay, so integration of everyone who is at the workshop in the focus area, that we will definitely do. So, I mean, with the understanding that in the focus area, we're focusing on mathematical structures, but there's a lot of structures in everybody's work. So I think it's very easy to do the integration. What do you think, Dr. Abass? Yeah. Community engagement, we already talked about. This is something very serious. We very seriously want to follow up on this. I think Dr. Ratilal will be very happy with that. We can report to her later today. And so basically everything now except this postdoc appointments, but this is something that we'll have to see. So the focus area doesn't have postdoc funding. To what extent are you interested for other postdocs that are in the focus area to visit you every now and then?
No option of them in their full time. Because what we focus on is like, if the postdoc at the students benefit more.
But the postdoc's main job is research, not to benefit the students.
Yes, it's a research, but
Yeah.
it's supervising, remember?
Ah, that's
The
right,
honors- the
yeah,
honors
yeah,
project.
yeah.
And the actually, our policy, they take one position, so they do with that, they need the department.
But if there is a project, specific project, and you have a postdoc in mind, I think this can result from postdoc.
You think so? Can NITEX do it? Because NITEX postdocs are per hub. So we have to talk, we really have to talk about this with Professor Francesco Pichani.
Because SME funds are, that's. And we move from that to
Sorry, can we do what?
I think do we have a chance to pick and how that was to go? Because there's a new force that now that's how
Yes.
we can move.
Move what?
We choose the half where we want to go.
So should SMU take over from it? Let me
No,
say
we are
that.
going to take over from that. We want to change the hub. Belongs to SU, not the first hub.
The new hub.
Not the new hub, the existing hub.
The existing hub, every hub has a leader,
Yes,
and Pitso is currently the leader for that area.
yeah, for our end.
Yeah,
So we want to from that hub.
so that means take over.
No, we just
A
want.
hostile takeover.
Oh, you want to be this hub?
Yeah.
That's not possible. In fact, Stellenbosch University is not even part of the Western Cape hub. It's because the director is here. I think the recent pictures that I've seen in presentations of Professor Petriciane, because the director is here, Stellenbosch University is independent of all the hubs. Because it would have been unfair that where the director sits belongs to one of the hubs and other hubs don't have directors. So because of that, it's separate.
And then you can stand questions.
Yeah, the way it's more different.
No, well, the director is here and the university is investing a lot of money, like all this infrastructure that you see here. Large money was invested by the university.
Yeah, I think the whole process was quite a long one in terms of justifying the location, facilities, etc., etc. before they concluded.
Yeah. What about a postdoc that spends half of the time at SMU and half at Stellenbosch University?
It's still fun.
Split postdocs.
Yeah.
Because then maybe we can negotiate something at the level of our DVCs. They can agree to co-fund, create new postdoc positions. They co-fund. This is actually a good idea because this way we will be able to get more postdoc positions than we would have gotten otherwise, because we're adding value to it by the collaboration. Split postdocs. And maybe this is where we kind of, to make it more attractive, we could say with HDIs, between HDIs and non-HDIs. By the way, I would love, I'm going to say something very selfish now, but I personally would love and to come and spend 6 months at SMU.
Yeah, come.
And they are there, many.
Sorry?
They are there, many. The monkeys.
Which ones?
I'm going the monkeys, they are there.
Which monkeys?
At SMU.
Which ones?
Which one?
What is it? Small sugar monkeys? Is it the baboons? Is it the...
When I was in Durban, they were running all over the roads. It was very nice.
They saw me there and they thought I was the...
All right, colleagues and students. So we stole 15 minutes of the break time. So let's use the other 15 minutes before we resume. So now we break for 15 minutes. On my screen, I had this Infinity non-profit company that our colleague was telling us about. We can look into that at some point. Thank you very much for sharing that, Johnny. Great. I think I already responded to it.
That's the one.
Yeah. We should get back to Johnny at some point before the end of the workshop. Yeah. Let's see. I'm gonna open the.
Buongiorno. Yeah. I get confused about when to say. Like, buongiorno is, when do you say it? In the morning? Buongiorno is in the
You
morning.
can also say it
It's
in
1
the
hour.
afternoon.
Buongiorno just means, how are you? What? It's just
It's
Different
good
day.
day. Means good
Day lunch is from 1 to
it's like
5.
guten Tag in German. Buongiorno. What is
We are 1 hour from the map.
Ciao is like, ciao. That's in a movie yesterday, the other day. Anyway, so buongiorno is a good one.
There are plenty of great
What is what? This one?
common ones.
There is no fixed things when to start.
You don't have one like for good morning, good afternoon, like
We do have that,
like in
but
good morning, Spanish to say,
they are not that
Buenos
much
dias.
used.
oh, so buongiorno is the more.
So there is good morning, good afternoon, and so on. But usually people just say buongiorno. And if there are other ones.
Oh,
What do you think of?
They might take part, but maybe.
so ciao is not Bye. Ciao is just
Ciao is
Bye.
for both when you meet and when you say goodbye. It's less formal.
oh, it's like
If you want it more formal, you use buongiorno and arrivederci
Arrivederci.
when
You're going away. Arrivederci. Hey.
Yeah. Yeah. Boss,
Roybos.
where are we going?
I don't know. Wait.
I think you can make in the kitchen. I don't know.
It's a break.
Yes, by the way, the law is what we can.
What we can have done is actually, the first piece of the topics.
Okay.
That is,
Okay.
and that is not trivial to me, because to understand and people agree to supervise them on those topics.
Absolutely.
Because that's, although we allocated only 2 hours or something after the lunch, to meet with other people, we will be joining online. But I think the number of people who are joining is too little.
Not working.
It's just a
Cancel immediately when you. Tell me. This. Letter. Finish the letter. And then you start with.
I already opened Chemotexes.
I just still have the internet from this place from last week.
It's my account. It's valid everywhere in the Stellenbosch University. It's everywhere. It's everywhere in the Stellenbosch.
I thought I was special. They're not special.
Did you check the graph on the Chemotexes?
Power last night.
See.
Yeah, if that.
One graph. Second graph. This third non-zero. Zero.
Okay.
Yes.
Actually,
Every
it's converging.
it's converging, yeah.
I think.
Converging, but not both are converging. They have some intersection here, then they are subscribing. Both lesions. They have intersect. You know, intersection means they have solutions. They have common.
Any specific time, that's you and that's me. Yes, okay, that's what it is. It's not, no, it's not, It's not,
Solutions. These are the solutions of body. They,
so for example,
they
for
have intersection here. They have
psi equal to 3,
yeah. They have that yeah. Convergence means they are have so they have intersection.
no, not intersect. Convergence means they separately, they, just remember, you just put them. Respectively, this I think is divergent. Because they're all convergent. Convergent, that one's convergent.
It's already have converges to this.
Yeah, it's converging to that line. This one,
That line.
this one is convergent, of course.
So this is also connected.
Yeah.
Yeah, this one is one. And then I did there's that solutions, but the graphs are not very nice because this is exact solution. So I
That's numerical on the invariant solution, this one.
yes.
So it's this equation here.
I draw its graph. It was 3D, but it was just wave.
So it's not so interesting.
I just leave it.
So the 3D solutions are not interesting.
This doesn't. Trying to set something out.
This conservation law saying that, you know, why this is not interesting? Because U is just a plane.
It's flat.
It's just flat plane.
Yeah, yeah. No, that's not interesting.
And this is a wave. It's not.
So left is this.
Yeah.
The numerical.
No. Let me show you. Some more things are on the way.
Oh, so stupid door we need to solve. The little blocks.
I is your breakfast over there. Is this something?
Your words.
That time I went to. All right. This guy got back. Nice guy. I know even my shoe.
Nice.
Now I will find some
But no. First thing.
the point corresponding to these. Sorry.
The pay.
What did it?
Um,
Did you guys work out the color of the bay?
I think they forgot. They forgot, I think.
The question is, where can that happen?
That's the
question.
Leave a color.
The way.
Color is just a conclusion, but where is that process possible?
I want you to repeat the question because the.
90 degrees.
Right. Okay, let's see it in terms of east and west.
East.
So yours east is on.
Yeah, it's on my right side.
Right.
So I'm going first.
So you start here, that's home. You go east, you go north. Now you go south, same distance. But you're not here, you're there.
You are there.
But is this a 90 degree? But that's what they were. You said.
I said east.
East, then north.
North.
See? About the.
Your home is at the edge of the mountain.
Right.
You are going east. You are going up in the mountain, and then you are
It's exactly north, it's exactly in
direction. This direction.
Do you get it? It's exactly north and east.
Here.
Yes, no, I don't dispute it. It's exactly north.
Exactly east, one. Exactly north, one. And exactly south, one. But it doesn't end here, end there. But you need to think beyond the geometry. Or you have to think geometry. How can you go like that, come back the same distance?
Guys.
And there, but here. Where can that happen? Geometry. What is this? This looks like a makeup. I'll give you the answer now.
Okay.
Oh no.
Oh. East. Properly east. 1 kilometer. Prop. That's the pole. One. It's north.
I wanted to show here.
See how we're going? Now, when you're there, when you're in the North Pole, there are infinitely many ways to go 1 kilometer south. Every direction is south. You're here on the North Pole, south. You're going down, south. South Africa, Australia, they're all south. So I can go 1 kilometer there, 1 kilometer there, 1 kilometer there, 1 kilometer there. So where does this take place?
We move forward this one.
This is the Earth. Where is this?
We indicated the one.
North Pole. What's the color of the bear at the North Pole?
I remember there's a twist to it.
This is the twist. You can only do, you can't do it on flat space. You have to do it on curved space at the North Pole. Because the Earth is very curved at the top. This is the picture, not this. This is east, that is north, and there's many souths from there. This is the one of them. That is back home.
You must remember that when the guy is moving, when the guy is moving, especially if you're not far from it, like very close.
It's 1 kilometer.
That's it, 1 kilometer. By the time, so as you go up, it's okay. But the time we want to go back, the guy has moved this way. So when you come back,
He's an Inuit. He knows his place. He can just look at whatever he feels.
come back.
He's like
The guy, how is the color? Why?
I'm trying to find the south.
The color of the polar bear in north. The polar bear in north are white. Let me show you.
He knows that, well, even though there's many souths, my home is there.
Look at this.
They don't read the government.
They are white.
The point is, that's a point.
You should say it's
This is what.
brownish white.
It's a curved triangle.
It's white.
Not.
Applied math.
This is approximately.
East-military analysis.
Because it's locally.
Differential equations, differential geometry, algebra.
Yeah, it's what we were doing.
Yeah.
But you cannot do this, you cannot.
And I'm
In
postdoctorate.
this situation.
Postdoctorate fellow.
flat Space. Flat space.
I'm not teaching, but I'm supervising 2 PhD
I
students.
hear what you're saying.
The curve space, you take your ball. Here's a ball, aha, here's a ball. Right? Such a way. If you go.
I also supervised 1 honor student, and now I'm supervising 2 PhD from AIMS.
If you're curving.
I'm saying, do you know that in my students, maybe you're supervising or supervising?
Now you're going south.
Supervising actually.
So don't follow two south ways.
Not from honors. I supervised in the previous session. So maybe in this session, they did not start it yet. Yeah, once they start, hopefully maybe.
When it's the year on.
Honestly, I don't have one,
What you're saying.
but they are, yeah.
Was that why you came to see me? Yes. That's the picture.
Okay.
Because now, the website, they have final year or honors, I don't know how many students, 2, but they are not allowed, so. I'm
Where?
not sure whether.
In applied maths or maths.
He said maths. I wanted
No,
to
it must be applied. No, he's maths. Yeah, he's right. Yes, I was in applied maths now. Yeah.
So I wanted to ask about the applied maths side.
Yeah. I know, but not too much because I'm not from here. I'm from WITS.
From birds.
I'm just visiting the department.
Okay.
So what do you want to know?
No, I wanted to know from Prof if he's lecturing here or if he's just supervising students from.
No, he's a postdoc here.
I'm postdoc.
In applied maths. Yeah.
Applied maths.
So maybe you need to, if you want to do something in applied maths, speak to the applied maths people there. This side more or less for masters.
I'm doing my honors in time.
Do you need access to the Wi-Fi?
Okay, I broke my phone.
Access to the Wi-Fi?
You're saying this, currently I'm on my honors, I'm applied.
You're going to finish this year.
Yes, I'm going to finish.
So you want to do masters?
The Wi-Fi.
You could speak to the coordinator of the honors applied maths. You know, these courses are coordinators, like in WITS, there's a coordinator of honors, there's a coordinator of third year's coordinator. And then you can have a just chat with them, like what's the requirements, would they consider? Might want to know, see what topics you're doing in. But I think for masters, you also need to know what you want to do your masters in. You see, and then they will have to tell you, oh, look, we've got an expert in this, or we don't have it. Or maybe more or less, maybe you should try, you could try AIMS also.
Okay, because I was thinking, I heard that advice, I don't know how many modules.
I think we need to call it
honors
on
level you are doing, but I'm currently doing. I have 4 modules in research.
Once you do 7 topics,
Right.
right? And one
Is it strictly rooibos?
one is project counts
Strictly rooibos.
equivalent of 3, 4.
That's the ink, that's what.
50% the project,
Physics.
and then the 7 topics contribute 10, 10, 10.
10.
Yeah.
Okay, then I think that's all I wanted to.
I think it is generally like that everywhere. It's supposed to be like that in the country.
Thanks.
Zurab, does AIMS have its own NUTHEX? So their NUTHEX person, is there a,
AIMS is part of the NIFEX network, definitely.
so who would be the point, who would be the person?
So AIMS falls under the Western Cape Hub.
Which is UCT.
Point of contact, yeah, UCT is the leader of the Western Cape Hub. And point of contact there is Will Horowitz.
Yeah, so are you guys listening to? Yeah, just listen to us.
But why did I need contact?
No, we're talking about, he's an honest student, he's talking about the possibility of masters, and I said, well, for applied maths, you need to speak to the honors coordinator on the apply. And I just thought maybe another possibility would be to do a masters with AIMS, say. I don't know.
Yes.
And whether then the text kicks in or not.
Yes, but yeah, so if one isn't interested to do masters within the focus area, then definitely AIMS is another opportunity. And also you can also just look at the departments. You can look at people who are there and see
what's their expertise.
Yeah. But we are very selfish in this workshop. We want to recruit everybody in the focus area. No, but yeah, well.
Once they have a nice center there that you're talking about, which will be.
So is everyone here? I see that Mr. Goswami is still arriving.
Someone else needs access to the Wi-Fi.
Right here. So our next session, we're starting now 6 minutes late. Our next session is mapping of mathematical structures research at SMU. So the purpose of this session, since main guests are from SMU, the purpose of this session was basically to as an outcome of this session that we see how colleagues and students from SMU can be incorporated in the focus area. And so that's why we're doing mapping of mathematical structures research. We want to identify which mathematical structures underlie the work that is done at SMU, so that that can guide us on how the integration can take place. I'm going to start writing names of structures that I remember from the presentations, and then we can go into depth there. I think metric spaces are among these structures. Then Hilbert spaces in particular. I think this is where I start need some help. Who is working with groups at SMU? We need your help, Professor Kara. We had 2 presentations yesterday on Lie symmetries.
Yeah.
What would be corresponding mathematical structures for the area of Lie symmetry?
So I don't know. They obviously were doing differential equations. Who was it? 2? Right? So there's within that ambit, you talk about differential equations, you could talk about Lie groups, not Lie algebras, because Lie groups essentially was different from Lie algebras, but it's more the focus on Lie groups, right? So it's differential equations, Lie groups. I don't know the extent to which they look at the geometry of these things. As Professor Goswami knows that I like the geometry part, you know, the manifold and the geometry part, but I think they...
Professor Kara, do you mind if we ask you to give like a 5-minute presentation on mathematical structures in Lie symmetry? Just a very bird's eye view. You can use the whiteboard.
So, in what I think understanding of structures are, I have a problem with the structure, not with the... Sorry, we use your helmet as a representation of the Earth. You find this to be the North Pole. That's bad. Okay. And I think Ali can also help me to some extent because he looks at this specific aspect of it. So the thing about...
Can I wire you up? For the online.
What is online?
Yeah.
Yeah. Whole world can see you and hear you.
That's dangerous.
No, that's good.
You don't know me.
No, Ali told that nobody knows who is Professor Kara,
And you don't want to know for your own safety. Okay, so if I given a differential equation, I'll just use samples of differential equations. You know what? So if you're concentrating, say, on well, let's start with the basic part. If you're looking at ordinary differential equations, suppose y is a function of let's call it t, right? So this is your simple harmonic oscillator equation. If you were to find the symmetries are those 1-parameter Lie groups of transformations. There are transformations, we call them Lie symmetries and so on for technical reasons, but each of them separately would leave the differential equation invariant. Right? That is it. In other words, if I were to act or the symmetry on this, the form of this equation will remain the same. Right? So if I have my new variables are t and y. So t could be a function of, big T could be a function of t and y, big Y could be a function of t and y. So these could be functions of this, not of derivatives. And I use this to transform. So what I get is a Lie symmetry. A Lie symmetry essentially provides you with a transform variable. It will transform this equation in such a way that it is, I have to use a different dash, let's call it double dot. So you notice the form of the equation is the same, okay? This is in the old variables, this is in the new variables, okay? So the equation is left invariant, form invariant, okay? Now, this transformation was provided by what? By one single symmetry of the differential equation, one transformation that kept the differential equation invariant. But the differential equation does not have to use does not necessarily generate just one transformation, right? This differential equation, for example, is rich in symmetry, rich in Lie transformations. It generates an algebra of 8 symmetries. When I say algebra, they're forming a Lie algebra. So this differential equation, if I were to use my standard procedure to find all the transformations, the Lie symmetries that leave it invariant, I'll end up with 8 of these. Not only that, these 8 symmetries form an algebra and you classify it into a standard set of algebras. So this is gives you what is called an SL3R algebra. Okay. Now so you may want to say that one of the aspect of structures come in with algebras. There are algebras that have been classified by various people. The noted ones in recent times are Patera, Wintonitz. What they've done is they look at the classification of all the algebras and then classify the equations that would generate those particular algebras, the representative equation. So this would not be the only equation that, say, admits this particular algebra of symmetries. Another equation that also generates 8 symmetries with the same algebra is the free particle equation. Okay, so this one admits 8 obviously different symmetries from this one, but the algebra is the same. So this one also generates an algebra of symmetries where the structure of the algebra is SL3R, SL3R. And when two differential equations generate the same algebra, you can map the one differential equation to the other differential equation using the symmetries. Right? So you can classify, so you got this equation generates SL3R, another differential equation, SL3R, a fourth differential equation, SL3R, and it turns out that for second order ODEs, right, the only algebra of symmetries that would be generated, number 8 will be the SL3R. So all second order ordinary differential equations that admit 8 symmetries would be the SL3R. And they are all equivalent to each other. The differential equations can be mapped one to the other. So if I give you a complicated second order ODE, I'm looking at second order ODEs, and you find the algebra of symmetries, right? And it generates 8 symmetries. It would be a SL3R. And if it's complicated, you will want to map it to a less complicated differential equation. And what would you map it to? You'll map it to this one, preferably that one. So I'll take this complicated differential equation, I'll map it to this differential equation, solve that differential equation in the new variables, which is straightforward because this is just what? AT plus B, the solution, like little y, and then transform back to the complicated differential. Okay. Now, further problem classification. Some of this work has been done some time ago, but when I say some time ago, I mean relatively recently, not like 100 years ago. So when you get to differential second order ODEs that admit a 3-dimensional Lie algebra, now you don't only have one type of, like here you got just one type of 8-dimensional, but there's 3 or 4 different classes of, listen to this, 3 or 4 different classes of 3-dimensional Lie algebras. So it doesn't mean that if a differential equation, second order ODE, admits a 3-dimensional Lie algebra of symmetries, can be mapped to another one that also admits a 3-dimensional Lie algebra. You've got to see which algebra does it admit. Is there another differential equation that also admit that 3-dimensional algebra? So it's a class of algebras. And if they admit the same Lie algebra, you can map the one differential equation to the other differential. So, and this kind of classification work, that's really structures. For second order ODEs, the sense is done. So if I give you a second order ODE, you calculate the symmetries and you see, well, it generates 3 algebras, not only 3-dimensional, it is that particular 3-dimensional algebra. I look at the representative equation in that class, which is done. I can map it to that representative equation. Like this would be the representative equation in the 8-dimensional Lie algebra of symmetries for second order ODE. It's been done to some extent with third order, and fourth order too. The nth order one was started by Faisal, he supervised them, but it came to a point and I think it was halted because it became just too complicated. So that's about classification of second order ODEs and so on. There's been some work done for PDEs, but PDEs is really huge. I mean, because in fact, classification for PDEs can be done, but it's not worth the while. Because when you take a heat equation, now I'm getting to PDEs. When you take, for example, the heat equation, right? That's now an ODE, where U is a function of T and XA. You calculate your symmetries, your least symmetries in your standard procedure. You see, you end up with maybe 8 transformations or 6 transformations that leave the differential equation invariant. What would mean a differential equation invariant? I could take any one of these symmetries and I can rewrite this differential equation to have the same form in new variables. This is now, say, capital U. Like that. Okay. That's not what we do with it, but you could do that. What we do with these symmetries is the following. One of the things we do is take x1, d by dx, or a combination of x1 and x3, right? Find new variables and reduce the order of the differential equation. Order here means reducing the number of independent variables. But you still, so I can do that with each one, and I'll get a different solution related to the 6 different symmetries, 6 different transformations. One would, for example, be a time invariant solution. One could be the Galilean invariant. It depends if there's a physical interpretation to these transformations. You could take combinations. You could take, say, the d by dx and d by dt. Time translation, space translation. Combine those two. I'll take a linear combination to get a traveling wave solution. You can do all kinds of combinations. One of the combinations you could, and before I continue, talk about the next thing. The algebra, the symmetries that you find always give you a Lie algebra. Okay? They closed under that operation. The operation for these vector fields is the commutator, the Lie bracket. They close and they satisfy certain other properties like the Jacobian identity, etc., etc. They form a Lie algebra, closed Lie algebra. Always. The differential equation always admits an algebra of transformations. Right? One of the things the transformations do, it's an advantage, is it allows you to say, so suppose you take, is to study the subalgebra, okay? So you might get that x1 and x5 form a subalgebra, a closed subalgebra. If you were to find a solution using that subalgebra, you get a solution that is not just invariant under one transformation, but invariant under the subalgebra of transformations. That's the kind of work that Ali does to a large extent, where you look at different useful subalgebras. So maybe x1 and x3 form a subalgebra. Maybe x1, x2, and x3 forms a subalgebra. But you're looking for ideal subalgebras of this full algebra, called optimal algebras, optimal systems. That's what he does. That's his specialty. Okay? That kind of classification, finding optimal subalgebras, so that when you find the solutions, you don't only find the solution, say, under x1. You can do that. You don't find the solution only under x5. You can do that. But you find the solution under the subalgebra x1, x3, and x5s. A solution that comes from the subalgebra, say, of x1 and x2. So not only do you get the subalgebras, the algebra will also tell you how to reduce your differential equation. So if I get an algebra, it applies there, it applies there. If I have an algebra of 2 symmetries, whether it's subalgebra or algebra, you don't just start with x1 and then go on to x2. The relationship between x1 and x2 will tell you that I have to start with x1, reduce, and then go to x2, reduce further, and then I get a solution. Sometimes you have a subalgebra of x1 and x2, and you start off with x2, you cannot use x1. And I'll maybe for your sake, I'll just say that. So for example, suppose you have this differential equation. I know all I need is 2 vector fields, 2 transformations that will reduce this to a solution. Suppose this was some complicated equation. I've got 8, but I'm looking for the 2 ideal ones, or a two-dimensional subalgebra. So it turns out, suppose I have x1 and x2 form a subalgebra of vector fields that leave it invariant. Now I'm just taking 2. I just need 2. Because one will reduce it to order, first order, the other from first order to zero order solution. But just because I have x1, x2 doesn't mean I'll just say start with x1, then go to x2 and done. You've got to look at the relationship between x1 and x2. So it's a subalgebra, but what kind of a subalgebra? So if it turns out that if you take the commutator, this is the Lie bracket, right? So if you take the commutator of x1 and x2, if it is zero, then we have, if AB equals BA, what do we get?
The commutative one.
Commutative one. Yeah, it means if this is zero, I can start with x1, x2, no problem. But if x1, x2 is a multiple, say, of x1, then the theory tells me I have to start reducing with x1. So I'll go from second order to first order. Then the reduced equation inherits the other symmetry automatically. So I just reduce with x2 in the new variables, of course. And then I get a solution. But if I get x1, x2 is x1, and if I start with x2, the reduced equation need not, in fact, will not have x1 inherited. So all these kind of structures, algebraic structures, subalgebras, it's all essentially Lie algebras, Lie subalgebras, etc., is related to the reduction of. So when you're doing optimal systems, as you see, you're drawing the sketch, you're looking at reducing your underlying differential equation. So from a purely algebraic point of view, you're just looking at structures, but they're related to the procedure in which you get solutions and the kinds of solutions. Like I say, you may want a solution involving the subalgebra x1, x3, and x5. Right? So then you would take that subalgebra and start doing your reduction process of the same equation. You might have a subalgebra of an optimal subalgebra of, say, x1 and x2. So you just deal with x1 and x2, but it has to be closed. So the solution you get will be invariant. You say, just a term we use, it's invariant under the algebra x1, x2. If it's a closed subalgebra. In the case of PDEs, even in the case of ODEs, you could just use one at a time. That's fine. If you want, suppose there's a scaling transformation. For those of you that are not too familiar, suppose I have a vector field that looks like this, 2x dx, this is d by dx, t d by dt. I'm just giving you an example of one, minus u d by du. This is scaling. You notice it's x dx, t dt, u du. So we call this scaling. You're scaling your variables. If you use this, if it happens to be one of the vector fields, one of the transformations that leave it invariant, if you're using this one to reduce, and suppose you get a solution, you get a scaling invariant solution of your PD. But it's too much. I said 5 minutes, but it's hard to shut me up. You're going to tell me, shut up. Let's go dinner. Chup. Sorry, the Indian word for like chup.
Shut up. If we have a complicated second order equations.
OD, yeah.
Okay, ODs. And imagine that we know the solution space.
Right. Now, so now, okay, so yeah, carry on.
Okay. Does that solution space will generate some kind of algebra? Because the algebras are generated by these transformations, right?
Yes, they are, yeah, they basically, yeah.
By this transformation which is happening between the reductions of those equations.
Yes.
Those transformations themselves generates these Lie algebras, am I right?
Yeah. Yes. Yes. Yeah.
Right.
Yeah.
Does this algebraic structure generated by the transformation has any connections with the corresponding solution space?
I don't know. I'll be honest. Maybe I'm not understanding, so it's not my.
Because you know this solution spaces of differential equations.
Yes.
Say, imagine they forms a vector space or something, depending on what kind of view. So they themselves form sometimes the structure.
Yes, I see. Okay, I see what you're saying. You've got the algebra of the vector fields, the transformations,
right.
and now you've got the solution space of the solutions. Right. I suspect there must be. There's something for you.
Yes, it's lie in the tangent space. There's something like tangent space. For example, these are vector fields, and they're infinitesimals. these are vector fields and their infinitesimals has a vector, for example, xi, xi2, xi so on and eta. They form a vector at that point. And in the solution space, solutions actually generate a surface. So these vectors will lie in the tangent space of the space generated by the solutions. So I think something like this.
I think it's on the right track.
Yes.
That
So solution space is surface, and those vector fields will be in the tangent space of the surface generated by the solutions.
yeah. So okay, I'm not sure if this is the correct answer, but it's heading towards the
It's
following.
something
That
like this.
you have a space of solutions,
Yes.
right? These transformations, we write them not deliberately, but there's a reason why it's in that form. That's a vector field. It has the form of a vector field, right? Vector fields are just tangent vectors, right?
Of course,
Right?
of course.
So, and they are tangent vectors to the manifold.
Yes.
The manifold.
That's where
And that manifold might be.
That's where you got the Lie groups.
Yes.
And that's where you get the Lie algebra, because tangent space forms the Lie algebra.
Yes. You see, that's the thing. So I'm sure that if you delve deeper into that, there must be then the solutions themselves form a space. And that's depending on the nature of the space, these tangent vectors are related to that, I think.
Because by somehow these transformations seems to be related with the tangent space.
Yes, they are. They are in the tangent space.
Yes, because otherwise, how come they form this linear?
Exactly.
Okay,
Yeah.
okay.
One of the questions I had, by the way, so you should know that. And that's one of the things I mentioned in the talk there, that you got Lie groups.
Yeah.
And Lie algebras. And people think they're the same thing in terms of the axioms. Lie groups, there's a definition of Lie groups and there's a definition for Lie algebras. Right? And I, in one talk, and there was a differential geometry. Jesse Alt was in the talk, and I'm so thankful he was in the talk, because I said these two are different concepts. And then he, after the talk, said they're actually not. Because you've got you say the surface is the Lie algebra, and the Lie group was the tangent to the surface, something, but purely from a differential geometry argument, which I would have loved to have understood in what we discussed. They are related, but not. I thought they were completely just treat them separately, but they are actually.
But axiomatically, is one of them another enriched with additional structure?
Yes. So a Lie algebra has to satisfy one closure, but under the operator we use is the Lie bracket or the commutator. It has to satisfy the bilinearity property and the Jacobian identity.
Skew symmetric.
Yeah, the skew symmetric.
Which one of them has less structure?
No, that together they form the algebra. They define the Lie algebra. Like
so okay. We're talking about the algebra versus Lie group.
Okay, these two are different.
Different things.
None of them is the same.
Yeah. Take an algebra over a vector space. The normal algebra, as you know. Then put two conditions on that. One is Jacobian identity
and the bilinearity.
that will give this.
Carry on.
Okay, so let's come back to these discussions later. We will have more time later, because this session is mapping out the structures. And I just want to ask a primitive question. Do I put them one below each other or next to each other?
They are separate with each other, but they are.
I would say leave them separate.
Right.
But if you want a distance between the two, they have to be on a curved manifold.
Because every Hilbert space gives rise to metric space.
Yeah, so maybe in that.
But in that sense,
no.
Okay.
In terms of okay, to answer your question directly, in terms of the axiomatic.
Yeah.
Okay.
No.
Okay. Thank you.
Common connections will be manifolds.
Yes.
Thank you.
If you look at it purely from a manifold thing, then yeah. But in general, if I ask you, is a set a Lie algebra, you check for certain things. Is it a Lie group, you check for something else.
All right, great. Thank you very much. Thank you so much.
Sorry, that's
Mr.
5
Carroll,
minutes.
for that. Continuing with the mapping of structures.
Yeah, it's relativistic space-time.
We've got so far these 4 types of structures. What else should we put on the map?
It'll be in my picture.
Which ones?
Better to, I think, for the.
Where should it go? Should it go under,
Axiom.
it's a special kind of metric space or a special kind of Hilbert space?
Then. You have a definition of.
Could you remind me the spelling, please?
Oh, sorry.
JTA. Can we present this properly? Actually, this is.
Oh, you know the story of Hadamat? A small, can I give you a 2-minute story? But you know, with me, 2 minutes will be 5 minutes. I have to tell you the story.
Later.
So
Professor
no,
Khan.
quickly. So the story was told to me by some guy in a library at the New York City University. The guy was actually working there. He says Hadamat came from Europe. He was famous by then, but not so much famous, not so famous in the US. Came to the US and he applied for a job there. So they asked him, well, who are you? You know, I mean, what's your claim to fame? So he pointed to a lot of pictures of mathematicians. He pointed a picture there. He says, that is me. It doesn't have to say anything. That's me. You know what they did? They took down the picture.
All right. So then there were another kind of metric spaces. I remember for one of the presentations. It was called CAT. It's also a special metric space, right?
Fine.
Was like this, right?
Yes.
I'm gonna make these smaller because they're kind of specialized directions of metric spaces.
Metric spaces, quasi-metric spaces, right? One of you.
Quasi-metric space was actually a generalization, wasn't it?
Yeah.
Yes.
Of a metric space. That was quite interesting. Yeah.
And also a metric space, is it also generalizations of metric space? Yes. Both of them. The quasi is the general most among all these three, am I right?
Yes.
And then a metric space.
Consideration. Still under consideration.
Okay, so between quasi and metric.
So
Yeah.
I think there was only one on a metric spaces also.
Yeah, but it's, if you're talking about now, it's now generalizing. It's, so it's fine with the person.
Okay, great. What other spaces do we have? Banach spaces. Banach space is a special kind of Hilbert. No, which one?
Which one?
More general than Hilbert. Yeah, of course, yeah. I would really like to make this list complete. So if you know of other structures that either in your work or your colleagues' work or other students are interested in. So, manifolds. Graphs. Why aren't we listing graphs here? Graphs. Graphs.
Which one? These solutions are very nice.
Going to class. What other structures can we put here?
Of those who are working on this financial mathematics, where you use these Lee symmetries, there are some stochastic structures, right?
Yeah, there's mostly, I think we use the ones that uses a bit of measure theory.
So it's a probability space.
Probability space. Yeah. Some Hilbert spaces as well.
What space?
I think Hilbert already
Yeah.
mentioned.
I think all of them will cover by the probability space, the moment.
Yes, exactly.
But there are lots of mathematical structures in finance, like for example, a market is a mathematical structure. A market, financial market is a mathematical. There are lots of structures there. I don't know much of it, but just
so mostly like, let's say it was all what needs was sigma algebra that captures information, with respect to type. So everything is like model in terms of, let's say, the information is model in terms of sigma algebra. So whereby something that's increasing in an increasing way. So the information in time now is on a certain like set, then the next time another one. So obviously the other one will be containing the information that I have tomorrow should be containing the information that I have today. And so on. So definitely that's where we need a lot of those structures. And the integration part as well, but it's already inside, I think.
And Professor Aphane, what about in your work? What other structures arise in your work?
I think that's all is covered here. Maybe the one that is the fuzzy matrix spaces, which is in the
It's kind of connecting point between probability.
Yeah. So I think everything is covered.
Fuzzy should we not say fuzzy metric spaces here?
Yeah, we should be the first.
All right, so what we can do next is to take our names and put them on the map in terms of how close we are to which structures, all of us. Anyway, let's start. Yeah, let's. So we're now focusing on the ones that come from our guests from SMU. We can still put others can also put our names if we fit into this framework. So let's begin.
This is good point. First, we associate the students to the structure.
That's what I'm doing. So we're gonna put names. Let me begin with Dr. Abass. Would it be correct to put your name somewhere here? Somewhere here? Yeah. Okay, great. What about you? Ladies, this territory is yours, right? You also have Hilbert spaces.
In between quasi and quasi metric.
You don't work that much with Hilbert spaces?
Hilbert, yeah, but it put me there.
So maybe I'll move this a bit to the right. I'll move this a bit to the left, and I'm going to put in a center there.
Yeah.
I think you should move this metaphor towards in the middle between the group cellular. That will be.
Well, it relates to Hilbert spaces also, right? So
what we can do, we can make a table. And then
I prefer geometric. I prefer a map. Okay, so please remind me your surname. More. A bit louder.
Khensani.
Okay.
H-E-N-S.
Where can we put you? Next to
Professor Aphane.
But you also work with Hilbert spaces?
By the Hilbert spaces. Just below the
Hilbert spaces. Yeah.
Right, here, okay. You work with Banach spaces? I'm gonna put you there.
Yeah.
You only work with metric spaces so far?
And Hilbert spaces.
Yeah, yeah. Great. Actually, sorry, I want to make we use different color for student or yeah. I think know how to delete. Sorry, could you please remind me your surname?
My surname is Thoriso, just spelling. Everything like THOMPRIS. THOMIISO.
Banach spaces? Do you work in Banach spaces?
No,
Just Hilbert. Then I'll put you under Hilbert. Your turn. Quasi-metric spaces. Do you only work with quasi-metric spaces, or do you also work with metric spaces? Also metric spaces. What about Cat0 and Hadamard? No. Okay, then I'll put you between these. For you, I use blue because you, yeah. Yes. Please remind me your surname. Sorry.
Surname.
Yeah.
Fatla TLANE. Grass.
And you don't work with metric spaces, Hilbert spaces now. Are graphs the only structures you work with, or are there other structures also that comes the way? Only graphs. Of course, there are different kinds of graphs. Okay, great, thank you.
Yeah, Claude Moutsinda, in the probability spaces there, that's it.
Please remind me.
I think MOU?
MT?
MOU? No, MOU.
Sorry.
TSI? NGA.
So the blue is supposed to be the same blue, I just didn't pick the right blue. Yeah, I know. It's not supposed to be different, I just didn't really pick the right color, I think it's fine.
There are times we can also interfere. Both probability space can sometimes interfere with Hilbert spaces also.
Also Hilbert spaces sometimes, and I'll put you here.
Something.
Yeah. Let me actually move this a bit closer than in that case. There. But not Banach at all, just
yeah. It's an LP space, LP.
Yeah.
Strictly.
Okay.
Aphane.
Please remind me your surname. Abdul. That A. Sorry, my hearing isn't perfect, so that's why I Prof. Are you supervising Kim?
Sikelela.
S, right?
Yes, SIKELNA.
Ella.
All the E's.
Sorry? And here.
E groups, the algebras.
The groups.
The groups, the algebras. Do you work with manifolds?
I'm not sure.
You actually don't explicitly work with the structures yet, right? But it's just that the topic.
Yes.
Yeah. Okay, fantastic. Professor Kara.
Yeah.
So if somebody is trying to work out least symmetry method in solving differential equations, are manifolds already important there, or manifolds is like something slightly different directions? So Lie algebras and Lie groups are important, but what about manifolds?
So when get into the nitty-gritty of the calculations and so on, the notion of manifolds to most people, almost everyone, falls away. The manifold thing is within the definition of the Lie group. Lie group includes, by definition, the notion of manifolds.
I see, because it's acting on the manifold.
Everything is a Lie group is a manifold with extra properties. I don't want to get into details.
I see. I'm not sure if we should have manifold as a separate structure, maybe. But
For other purposes, it might be a separate structure.
For other purposes, but nobody here works on manifolds.
So he works on Hadamard manifolds explicitly, right?
Cool.
He
You work on manifolds.
Yeah.
Sorry.
he has last 3 papers on
Of course. Yeah.
So I think one of the
Is it the same
definition is
Hadamard and Hadamard spaces, by the way?
Yes,
Same one.
yes.
Great, thank you so much.
Is there anyone here that's specifically in differential geometry? I don't think so, but I didn't get it.
So, next.
Tape. Thapelo.
H-A?
P-E-L-O.
P-E-L-O. Where?
yeah, let me send you that.
Prof. Remind me your surname, please.
Machabe.
M?
M-A-C-H-A-B-E.
Have it. And
P-I-T-S-O. Props.
Yeah, I remember them. Great. Now I'm going to put on the map where our lead researchers in the focus area, where more or less they fit on the map. And let me use a different color for that as well.
Right.
Pink. Okay, so Professor Goswami, I need your help. And also with the postdocs as well. So where do we put you? I don't think you study any of this explicitly. But on which edge of the screen do we put you?
Towards right corner.
Towards right corner. Yeah.
I love algebra.
Yeah, because Lie algebras and Lie groups kind of link with ring theory there, right? So Professor Goswami is not on this territory at the moment, he's somewhere here. You're using pink for okay. Great. Now I have a very specific question to you. Are you interested to either supervise or co-supervise a student who is going to combine Lie algebra Lie groups with whatever you're interested in your project in the focus area, the ideals and ring theory, kind of overlap of these.
Okay, between the ideas, then it will not be Lie groups, it will be only Lie algebras.
Okay, Lie algebra. Okay.
Explicitly Lie algebras.
Like studying ideals for Lie algebras.
Yeah.
Is that something that you might potentially interested
He's
in?
already done quite a lot. But point is that is better.
Potentially, yes.
Potentially,
Okay. Yeah, we will discuss more details about this later. So I just want to, yeah. Okay, fantastic. Then let me also put myself somewhere here. I think I'm going to be on several edges. So I'm quite interested. I'm not an expert in metric spaces, but I am interested in metric spaces. You know what? So in terms of my expertise, I think I don't fit in the picture, but like Professor Goswami, I could fit under somewhere here. But also on the other side, because I do have one paper about it's not far from graphs, but maybe not quite. Okay, maybe somewhere here. But in terms of future work, I'm interested in all of this. So I have one paper, a couple of papers actually, myself and Kishan, we have in metric spaces. I have some papers in combinatorics that are very closely related to graphs. I'm very much interested in supervising. I'm actually very strongly interested in supervising the student in theory from the algebra perspective. There's a lot of links of that with category theory as well. So I'm very interested in that. And I'm also there's a lot of category theory in Hilbert spaces. I never told you what category theory is. I hope I will still have an opportunity to do that. But category theory basically is mathematics of mathematics. If you're a category theorist, you'll be interested in any area of mathematics, because in every area of mathematics you can find some category theory that is useful. So so even though I'm on the edge, I'm actually interested in everything. Next.
But graphs are actually quite close.
Yeah, so yeah, that's what, yeah, so yeah. Okay, so next, Sirin Ratilal is doing connectivity in topology. So she would probably be kind of somewhere at the bottom here with linking to manifolds in kind of through the geometry topology perspective, right? Oh, actually, metric space, no, here, yeah, here, it's more here, yeah. Doesn't work directly with metric spaces, but she works with.
There's a lot of point-free metric.
Yeah, exactly. Yeah. Of course. Sorry. Professor Dr. Kuo, Wenchi Kuo, she works in functional analysis, so she would fall.
And probability space.
Right, so she would fall somewhere here.
More towards probability space rather than so it should be reached balance space and so
Isn't the read space is it the balance space or a Hilbert space? It has no norm. I see. Okay.
I'm sorry,
Pro is here. Well, so Eric, Argentiana,
interesting.
Ross.
Now we can go for 4 researchers, right?
I'm fixing these. I hope I'm getting his surname spelled correctly. Argentiana. He's working in graph theory, so he's actually quite explicit in graphs. And do we have all the lead researchers here? There should be 5 of them. Okay. 4 researchers. We could, but yeah. Let's do that. Professor Moshoko is probably working not far from where you are, right?
All the metric motion,
but also Hilbert, right? Fuzzy also. Maybe somewhere here also next to you.
I think he covers the left-hand side 4, right? Metric and metric.
Yeah. I see.
And
Metric and fast.
So we move up a little bit.
Solid oscillation to find the control here.
Why up?
Because it's more in the class 3, quasi-metric, metric, and
But also Hilbert space. Then we have Gosh.
with more topology.
So Gosh is probably more, but Gosh recently started becoming interested in graph theory, right?
Yeah, category of graphs.
Yeah, I'm gonna put Gosh somewhere here. And then we have Brink van der Merwe, he's doing more on the algebra side of things. So probably go somewhere. Yeah, somewhere here. Now let's also put names of postdocs. We covered all the core researchers, right? Caviglia, Elena Caviglia. Elena, where would you like to place?
Because I do some geometry also because between graphs and
Here.
yeah.
The Y graphs.
Or
No.
Then they are incredibly close. I think it's more than.
then
No, but the problems are very different.
the right, but
Yeah.
it towards algebra.
Yeah, so maybe somewhere here.
It's true that the category theories different problems usually.
Yeah. So category theories are interested in everything. So
Understand the research graphs or
So
the student talks to you.
yeah. So Elena Caviglia and Luca Mesiti are also category theorists, and so they're also interested in everything. But we're just placing in terms of the past work done. Where do you want to go, Luca?
Don't know. I'm interested in graphs, in metric spaces.
Have you done any research on graphs?
What?
Have you done any research on? We're talking about past research. We are interested in everything.
Areas you submitted a paper or published a paper.
You can be next, but they can be more towards that. So I've done some algebra.
And then we have
yeah, but paper in 0.3 topology. Does it qualify me to go closer to my?
It does. So this is a surface of a sphere. This is not a flat thing. So it's sphere. Somebody on the bottom left corner will be close to somebody on the top. Bottom right will be close to somebody on the top left.
That was Abdul Karam's fair.
Yeah.
Because maybe I'm more interested in graphs and metric spaces than big groups, even if I'm interested also in big groups. So I don't know.
You want to go somewhere here?
I don't know. Put me where you want.
I think from the point of view of research done in the past.
Research done, not interested.
And then Dayaram, Kishan Dayaram is Hilbert spaces. He's doing some work on Hilbert spaces and he's doing algebra. So maybe I can put Kishan, and he's doing a bit of categories there as well. So maybe I can put. He's not really D, so maybe here. Okay. Great. So we will later use this map for making specific plans of steps. As you can see, each of, especially the students, right? Each of you have so for each of you there is somebody as a lead researcher or co-researcher and postdocs as well that will be very happy to work with you, talk about the students. And this will also be a nice way for the current lead researchers of the focus area to also step out from what they're currently doing. Also go towards your direction. So a nice collaboration. including the staff members as well, in terms of collaborations. So we're done, Professor Aphane, we're done with the mapping. We've mapped everybody, not everybody who is here, guests from SMU and lead and core researchers and postdocs from focus area. And this is how the map looks like. And we'll then use this map for the next step, our next discussions. So the session, I think, has been successfully completed.
In the next session, we definitely need Professor Kara to be here because that will be interactive sessions along
That
with.
would be very helpful if he
Yeah,
can
Professor
be here.
Kara, will you kindly be here after the lunch as well with us because we really need to be added here.
So what is next is lunch in LC, and if you haven't already gotten electronic voucher from me, I think it's our guest from University of Cape Town, right? Yeah. So you're also invited to join us for lunch. I can give you the voucher, and you can buy whatever you'd like to eat in the Nielsen Student Center. And also Professor Kara and also Dr. Ali are invited for us as well. I think I did put you on the WhatsApp group of workshop, right? So you have the electronic file. Yeah, thank you all. So we will resume according to the program. We will resume at 2:30. If I'm not mistaken. We resume at 2:30.
So there are so many vouchers to that. Which one we are supposed to be?
Any.
Start from the first, every time you run south, you move to.
Ah, I see.
There are two of them, and you can use one. Each of them are 900 rand, so it's 1,800 together. It's enough for everyone. And please don't be reserved. If you want to take 2 drinks, take 2 drinks. Eat as much as you want. Yeah.
Five wines from 1965, just buy.
Can ask, but you might be.
No, except Spar, more or less all other shops there actually accept.
I mean, the vouchers.
Yeah, the vouchers, but Spar does not. But otherwise, more or less everybody accepts.
It's organized by French.
Okay. The same group that does the physics. Yes.
So I don't know, it's in Chris Harden.
Just that looking one of the presentation. Just another presentation, a different. What is your name? Somehow, no,
That's for your masters.
For my honors.
Tell it. First things first. Going to the double X.
Right, for you. You go to the next one.
If it finishes, just go to him and tell. No. Use this one. And if the shop says, no, this is finished.
Another voucher.
There is another
The
one.
others.
If there is another one.
You start with the first.
If check one of these two, okay? One is finished, this is try the other, there are two given. So better run now, so that if the second one is also finished, tell him that I don't have money, give me money and he will give.
You're welcome to leave things here. That's quite safe.
Thank you.
Don't worry, that's fine. I wrote it for myself. And he wrote it.
Not super cool or not. But
But we use the board in big class. Both. In Johnson, big class.
There's not one.
Yeah.
I don't know. Because I see the bodies there. I see the bodies there.
Because that one is strong enough, it's like Goswami.
It's like,
It's like Goswami.
yes, it's
And it does the what do you call it? Blending. No, no one is using it. Just there, somebody is hiding.
That's the thing.
Nobody wants to give it away. No, one time. Something is not right. That's what I was talking about.
Because I was asking myself, say that, he's a bot. And I think of faith for all these smart things.
Everything. It does. It does. That's very cool.
You've seen it working before.
It's not the one.
That one.
Not that one. No.
I don't think there's anyone who's seen that one working.
And those, they are even touched, Papa. You touch them.
I thought that we did that.
You did. That came there. Everything is well positioned.
Just put your notes there.
That thing is going to expire. Whether it's expiring, and next thing will look for maintenance. Maintenance, nobody knows. It's a long way before. This one now, don't now.
I cannot see my things.
Now, something like this. If somebody takes it, let's say to the head and says, "You guys are telling us that you're not giving equipment. How about we can just point it at and how about this? Have you used this? Why are you asking us?
You see, sometimes we try to avoid them because they don't want problem.
Even they themselves, the guys are not because I've never used them. I've never seen them use it. I pass them.
You see that sometimes
I pass them.
you go to ICT, you carry your problem there, and the person you meet there with look at over yourself. It's like I can't solve this. It's more than that. So another thing that I said, the only thing you need to do is take 2 people from that department, teach them. Those ones we teach the remaining. But we use it.
No, it means no, these things have some problem. No, it's not some problem. There are some key features or maybe some passwords or something like that. That are held by somebody somewhere. And then no one knows about it, no one dares to look for it. Everybody just, no one takes responsibility. But there's someone that knows information. There's someone that does information. And the guy is there, or the guy or the lady.
And when you push too much, you're in trouble.
And
Just leave it.
some people know that this is the person who has it.
See that I don't go to when I only go to research office. They know me. I don't want to know.
Like this is incentive. They should send the thing. Nobody's responding. Yeah, they'll be saying something about it. There is something there about the incentive for the when you graduate, masters of PhD on record.
Yeah, they know. They know.
No.
I thought it was.
And meanwhile, Who's getting that? Where's the money? Because one of the point why
nice.
Welcome back, everybody. We did a bit of planning, so we're starting a bit late. The plan for this session is that we're going to have several short presentations and questions so that those who haven't yet spoken about what they're interested in and what they do can have a chance to do so. We've grouped ourselves as well. There is a categories group, there is ideals group, there is Lie algebras group, there is probability spaces group, and there is, I guess, metric spaces group from Professor Aphane. So, camera switch, yes. And we should also wait for Professor Aphane. Yeah. Let's see. Sorry, Elena, for not telling you in advance a few weeks to meet with it.
No. You can also come on the board.
It's listening to two people together, which
There's
is
not enough
fine.
space on the board.
There is one.
Online, who would like to present? Do they have a prepared presentation or a prepared one? So rather let's do that later because we won't have time now for the prepared presentation.
Dar un motivo per studiare.
Elena, you start.
I start?
Absolutely.
So I'm going to tell you a little bit what categories are. So you can think of categories as mathematical abilities. So we can think as of categories as universes. So every category has some objects or elements that we usually write as like letters. So maybe A, B, C. We can have a few of them. We can have a finite number, but very big. We can have infinitely many. But other than objects, we are also interested in how these objects talk to each other, whether they are related or not, and if we can go from one object to another somehow. So we have objects, but we also have what we call arrows between the objects, and we usually write with small letters. So I can have this arrow from A to B, and I can call it F. But I can also have maybe more than one arrow between B and C, maybe G and H. And I can even have an arrow from B to B itself. And we can think of these arrows as relations between the objects. And other than that, we want also a way to compose these arrows. So if we have the arrow A that goes from A to B and the arrow G that goes from B to C, we want a way to put them together to get an arrow from A to C. We just take F, we do F, and then we do G. And what we get is an arrow from A to C, and we write G composed with F. So we always have a way to compose these paths between objects. And we also have a very special arrow for every object. So given an object A, we have a special arrow from A to A that we call identity of A. So you can think of it as the arrow that does nothing, more or less. So what are examples of categories? With this concept, we can capture very, very different things. So one simple example is that of sets. So we now can consider a category that is called set. And objects of this category are sets. So now our A, B, and C are sets. And our arrows between sets are functions. So we all know that if we have a function from a set A to a set B and another function from B to C, we can compose them to get a function from A to C. This is something we do also in calculus or in other contexts. We also know that we have an identity function that does nothing. So it sends every element in a set to itself. And these data form a category. So we can study sets with category theory. But we can also study groups, for example, with category theory. So now our objects are groups. And what are our arrows? They are the right kind of functions between groups. So they are group homomorphisms. And there are many other examples similar to this. So we can study vector spaces, for example, and all other mathematical structures.
Can we do quasi and metric spaces?
We can. We just have to understand which is the right notion of arrow between quasi and metric spaces. which I don't know, but yeah. But there are also other examples that are a bit of a different flavor. So for example, we can consider a single poset, partially ordered set. Do you know what a partially ordered set is? So let's just take a specific one. We take the real numbers and we use the less or equal relation. So if I now give you two real numbers, A and B, in R, say -5 and 7, you can tell that -5 is less or equal than 7. So when we write -5 is less or equal than 7, in the category represented by this poset, we are saying that there is an arrow from -5 to 7. So we also have a way to encode posets and many other different things. And now that we can encode all these mathematical structures with categories, we can also compare them, and we can use category theory to maybe relate some concepts in different mathematical areas that seems very far apart, but they are really the same concepts if you look at them using category theory. And this is what has been done, for example, with algebraic topology. So algebraic topologists use algebraic objects to study topological spaces, for example. So they will use the category of groups and the category of topological spaces and relate them somehow to study topology in this case. How much time do I have?
No more time left.
Okay, then it's good.
Now there's a question, time for the questions, 5 minutes for questions.
What is algebraic topology?
How does it differ from the normal topology? How does it differ from the normal topology?
Like in general topology, you just try to study topological spaces. So maybe homeomorphism between spaces and things like that. While in algebraic topology, you associate to every topological space an algebraic object that, for example, can be a group. So you construct this group from the topological space, and this group gives you some information about the topological space. So, for example, if now I have two different topological spaces, but this procedure associates to both of them the same group, this means that they have similar topological properties somehow.
Okay.
The ones that are studied by this group. That's the idea.
Okay.
But it's not what I'm doing, so.
Yeah, okay.
We can actually also turn a topological space into a category, which would be something similar to how you turn topological space into a group. You take any point, let's say, in your space, that's point is A, for instance, another point is B, and F is a continuous path that takes you from A to B in your space. You have a continuous path, particle moving from spot A to spot B, another one from B to C, then you can combine them. So you can turn any topological space into a category. In fact, it will be a two-dimensional category, or even three-dimensional, or five-dimensional, which is something even more advanced than Elena explained. Algebraic topology studies these categories.
I have a question.
Yes,
I wanted to ask how the category theory differ from a group and field theory, because I saw that you mentioned about the groups, isomorphism, and all the mapping and stuff. So how does that differ?
Like in group theory, you live inside the category of groups. So you like live in this universe and you study that. You study groups, right? So in category theory, you study all the universes together and how they talk to each other. So you are like outside, living in space and looking at all the mathematical planets. While in group theory, you are inside the group planet, or in topology, you are inside the topological spaces planet. Does it make sense?
Is a group field an example of a category?
Yes.
It's one group, you mean, or
A group field is an example of a category field. Prof is very unfair.
yes.
All groups, whatever written here.
Yeah.
Almost all of them individually and examples of categories with their corresponding structure developing maps, all of them.
Well, you can make a category of graphs, you can make a category of manifolds, you can make a category of Hilbert spaces,
All of
make a category of balance spaces, you can make a category of fuzzy metric spaces, and so on. All of them.
That's why Zurab is everywhere.
That's why it's every, and then
Yes, it is.
in terms of the point-free topology,
Yes.
where does it fit now?
Point-free topology is somewhere here, and you can make category of point-free spaces. But
But also
but
every point free space is
is also itself a category. That's true. The point-free topology is when you're studying in a topological space, you have points, right? And then you have open sets. In point-free topology, you only have open sets. You don't know what their points are. You have open sets as abstract objects, and you know when one open set is inside another one. But that's what point-free topology is. These things are called frames. Sometimes
Oh, yeah, the frame.
frames. And you can make the category of frames as well. And actually, in point-free topology, oftentimes they do that because it's useful.
But what is a frame?
A frame is abstraction of a topological space where open sets are viewed as the basic ingredient. So you don't decompose open set further into points. You have a class of objects that you know when one is less than the other, that's when one open set is contained in the another. So you have it's actually what
like this.
Elena wrote here. It's a set with a partially ordered relations of comparing two elements. The comparison is when one open set is inside another.
Yeah.
So move from the sets.
In a frame, yes.
So one is continuity.
Yeah.
And does it have some real life applications? The
Category theory. Yeah, there are lots of real life applications. Well, there are lots of applications. I don't know how real life they are, but a lot of computer science often relies on applications of category theory. A lot of computer programming languages are based on the ideas coming from category theory. One of them is called Haskell. I don't know if you've heard of Haskell. Functional programming languages, because in functional programming language is about functions, so it's basically that's what these arrows are.
But it's also category theory is quite new as a subject, so
Yeah.
there will be more applications as time.
I read that this category theorem module is related to graph. How's that related to
Graphs. Oh, okay. Because you can see these as a graph, as a special type of graph.
That graph.
Directed graph. So these are your vertices and these are your edges. But now your edges have a direction. So it's not just there is an edge between A and B, the edge goes from A to B. And then you ask additional properties, not just a graph, it's a special one because you can always compose edges to get a bigger edge, for example. So there are rules that say this graph is a category, this other is not. They are special graphs.
So in graph theory, we can say that now A is adjacent to B.
Yes.
If in category theory,
So we say there is an arrow from A to B. We don't use the word adjacent, but
A may be what I would say in category theory.
we are saying that there is a way to go from A to B.
Mathematical. So I want you to say it mathematical.
That depends on the specific category. It means a different thing in every category. Right? In the category of sets, it means there is a function that goes from the set A to the set B. In the category of this poset, it means one number is less or equal than the other. So the specific meaning depends on the category.
Okay, for this one, you can say
This is just an abstract category, so I cannot say more than F is an arrow from A to B.
F, to B, F, and map B, F.
It depends.
It
depends what you choose.
Yeah.
Yes. See, A, B, C, they are set. We are picking those F and G as a function. F maps A to B. But now, if A is another thing, if it's another thing, I can say F maps A. Depends on what A, B, C are. It depends on the structure. That's when you know the name given to F and G. You get? So if A is a house, I don't know, and B is a house, there is a name you tell us that this house is connected to this house. We don't know what to call it. You get it now? It depends on the structure of those A, B's. You get it?
The same with graphs, right? That two nodes can be connected with an edge, and the specific meaning of the edge depends on the graph you are considering.
Okay, so with those arrows, right, it's from A to B, then from B to C, right? So is it possible for you to use G and H, combining it with maybe the F to find the pathway to C, or you only study the one path, with not combining it with any other path, since B has two paths to C?
No, you can, so since B has G and H to C, you have F composed with G, but you also have F composed with H, right? And they are two paths from A to C, and they are different, or they can be different.
Also, you can have both of them at the same time.
Yes, you can have as many of them as you want.
But then it's interesting to ask when the two paths are the same, actually.
Yes.
It can tell you a lot of information.
Yeah, in category theory, we use a lot what is called commutative diagrams that are like, if you have maybe see something like this, so you have maybe squares or other shapes. They are made of arrows. I don't know, I'm giving with names. And when we write this square, we mean that the arrow A and then B is equal to the arrow C and then D. So there are two ways to go from A to D, and they are the same. They are equal if we write square.
Where do you meet category? At the honors level, masters?
So I
learned it, my father taught me when I was in grade 9.
It is the modules that they don't know.
You
That's
can
why.
learn it at any age.
That's why they're asking lots of questions. So
I met the definition of category and the first things during my undergrad in topology. But then I actually studied category theory only from the PhD.
for honors, you don't have a category theory module.
There was no category.
It depends on the university. Some
In South Africa,
universities have them, some other ones no. Because it's a relatively new subject, so not all universities have these modules.
Yeah, we are one.
I think it's very useful, and if you learn it in the first years of your undergraduate studies, then it's really helpful also for other modules as well.
For the undergrad, it's going to be difficult to introduce it. But for honors, it might be possible because we have got the elective modules. And you can only have elective modules if you've got somebody specializing in that. So you can't put a modules that you don't have anyone to teach it.
We also do it at honors at Stellenbosch. We introduce it at honors level.
But I think it's also useful even if you don't want to work in category theory, but you want to work maybe algebra,
To
geometry.
understand the other modules better.
It helps you to, because we see now category, it is now covering almost everything there.
Yes, yes.
There are 4 universities in South Africa to best.
Okay.
There are only 4 universities in South Africa, to best of my knowledge, where there is a course in category theory. Stellenbosch, UCT, Limpopo University, and University of South Africa. I taught
At UL, who's teaching category theory?
Mark Matlaviana.
But what
Mark
about
is teaching?
Edward in Yangala?
Yes, before he moved now.
Because he's probably teaching wherever he moved. Where did he move?
He moved to South Africa. Last time when I talked, he did nothing there. But
Any case, time is up. We can come back to category with another point. Thank you very much.
But before she goes, Prof, do you think is modules that we can propose to have?
Of course, yeah. We would be very keen to help you with developing the modules.
Okay.
Yeah, we used to have at SMU.
Category.
Our challenge was we didn't have
What did you teach?
specializing who can even teach the module because I
Is it-
did the module in honors.
Oh, really?
Yes.
Who was teaching it?
It was a
guy from UP.
From UP. So he was teaching in UP, but contracted to teach us the module. So we always had to struggle with somebody.
But you see, now with NITEX, we can overcome that because I teach category theory almost every year as a NITEX course, online course. So we can overcome these challenges. And there's already 30 lecture material restarting from the scratch 3 times. That's what you can find on my YouTube channel. In fact, it's basic. You don't need to know anything in mathematics to start understanding it. So there's already a lot of material online, but one can also teach it live online. And as I said before, we're also happy to come and visit you. So yeah, that's a great idea.
And then how will the assessment be conducted if it's online? How you are currently doing?
They can write locally the paper and then the lecturer can examine them wherever they are. Take pictures of them.
Oh, so that's what is currently happening.
Currently, the NITEX courses are not necessarily have to be assessed. They don't have to be assessed. So usually when I teach, I don't assess. It's more interaction. But if it's part of an official honors program, then of course there will be assessment as well.
So do we pay for the NITEX online courses?
Right?
We have to pay for the.
No, it's
absolutely.
free.
This is 100% free.
Free.
Okay, next. Probability space.
Thank you so much.
All right, go on, so just go with it.
Yes.
Mostly what I'm currently doing. I can, do I have to?
Yes, otherwise,
Okay.
online people can't hear you.
All right. Okay, so currently I'm working on numerical methods instead of the probability spaces. So even though I'm touching probability spaces, but I'm not deep, we're not getting like deeper into that. So what we do is we have financial problems. Whatever the financial problem is, we use the mathematical machinery, especially to model information and so on. And then most of the time you end up with differential equations. And that's where we come in. That's where we start. So we have differential equations that we know, like partial differential equation, let's say, like the ET equation that you just mentioned, which is a very famous one, especially the Black-Scholes. So let's say you have a UT, and then this one, as simple as this. What we try to get is that most of the time, those equations, we can't get exact solutions. So it's complicated to get exact solutions. So we get into, we use numerics. So in the numerics, myself, I'm working much more, we're working on 2 types of methods so far that we try to modify all the time. The class number 1 is the class of finite differences. So what we do essentially in the finite difference is just that we approximate basically your solution. Take your solution and then we approximate it by some finite differences whereby the derivative is just substituted by, let's say, just a difference
an approximation of that difference, whether the first derivative or second derivatives. Let's say this one, we approximate it at each point. So basically what I'm saying is that, so supposing your solution will be something of this type. So since we cannot get an exact solution of this, we're going to discretize your problem, on this point, and then we make sure that we write the same equation at each point here, all over. And then provided that we have some boundary conditions, initial conditions over there, with those initial conditions, starting from there, we start generating sequences of points that will be approximating. That's where the functional analysis is coming in, because as we run the first, let's say some iterations, we can get a solution, an approximate solution. When you use this equation, we can get an approximation at each and every point. We can get, let's say, solution number one will be, for instance, like that's it. So we can have this type is the first solution. And when you run again, you get another solution, supposing something like this, that will come here, supposing that. So now the question, as you keep on running, the question will be, like, how good is your solution? What can we say? So we're generating basically this sequence of functions. These are sequence of functions. And from those sequential functions, then the idea of errors start popping in. So we want to see how best is your solution. So how far is one solution to another? That's the story of a distance that we heard yesterday. How do you compare the distance between two functions? How close is one to another? That's where we get into the error, we come into the convergences, and we bring in the mathematical machinery that comes in to assist us into that. So it can be, depending on the norm that we use, we use the L1 norm or L2 norm, and so on. There you are in the norm space. So we define a difference. And the second type of method that is also spent time is the spectral type of method. So basically in this spectral method, what happens is that we still have it's all about approximating, because you cannot get the exact solution. We all agree we cannot get the exact solution. So what we do is we approximate, we're going to write our solution, let's say the UP solution. You can write it as a sum, sum of, let's say, of test functions, of some polynomial functions, which have some very nice properties. And those properties, usually we take them on orthogonal spaces and so on. That's where you see we're getting into the Hilbert space that I've mentioned about. So as we get there, we have some nice properties of those functions, let's say alpha and then t of x or p of x, whatsoever they are, t, k, k starting from 0, let's say up there. So we approximate your solution with the exact solution. So this differentiation, we suppose the solution exists. And then we approximate by this type of series, where those functions here are test functions, very nice functions with some nice properties, in such a way that your problem that was complicated becomes, we move from this type of problem, we get into like, what do you call it? Like kind of system of equation just to solve. And the only issue will be now to just get those coefficients there, alpha, k, and so on. And in most cases, depending on your boundary conditions and so on, then we need to know which type of function to choose. So we have, what do you call, Fourier, we can have cosine functions here that can pop in. It can be Legendre polynomials that can pop in depending on your problem. So if your problem is, if your boundary conditions have some, let's say, periodicity, then you can bring in, let's say, Fourier series. Or if you have another type of surface, you can bring in maybe some Chebyshev polynomials here, just the whole idea is just about solving this problem in like over some points here. Now the story goes that in most cases, we have a problem with spectral method. It's very nice because you have fast convergence here.
So within few iterations, you're already there by the solutions almost. And it's very accurate. But the problem is that this guy is only working on like small interval. Is my time? Is
Yeah,
okay?
but you can.
Okay. This problem is that this guy is just working on, let's say, from interval, let's say 0 and 1. So that's where you have accuracy. But most of our problems, like the large interval. So how do we scale that thing? And how about when you move into higher dimension? So this is where I worked in, and most of the time the problem is what we do is, okay, we take your large interval like this, obviously, you break it like this, and then you apply your method over there. You can apply the method over here. You can apply the method there. But now the problem is here. See, we need to make sure that your solution, the smoothness that you're getting here should also take place this side, so that you can just taking this solution and then like put them together like almost like the train, like one couch here, another couch here, and this whole thing must be a very nice train. So basically that's the story. But here, in most of the time, we have problems, and that's where we work on, depending on the type of polynomials that we're dealing with. So roughly speaking, it's almost, this is what I've been working on. And then extending this into various type of differential equations. But all of those equations are taking place in finance. So we started up from a normal financial, like measure theory stuff. Then we kind of leave that area and then we fall here this side. So and then we compare which of the method basically will be appropriate to apply into some different type of differential equation that we're facing into the finance. And why should we choose this method? Why should you consider the other ones? So that's basically what we do, roughly. Thank you.
Thank you.
Questions or
any clarity? I was maybe too abstract.
So in the finite difference method,
yes.
What initial conditions are the most compatible one or most appropriate one you use to find the solutions, numerical solutions?
Like the initial, let's say in finance, most of the time our conditions are at the end, like they're not initial valued, so they usually take place at the end. So we know, for instance, this is a time t0 here, and we know what we expect the deal. Let's say you strike a deal here, but you expect some result this side. This, let's say, certain payoff that will taking place at a certain capital T. So to be much more specific, for instance, we have our farmers that are here, we have those crops and so on. And then the guy says, okay, somewhere in January, my crops are going to be available, but then you need to sell all these crops somewhere in that January. So in January here, that is what you're expecting as a deal. So we know what we want here. Let's say the profit in January. So we have those boundary conditions. But now the price, the question is going to be, what should be the price at any time capital T somewhere here? So basically you go work, like kind of backward. You'll be working backward. The backward, for instance, in terms of finite difference, will be appropriate, can be appropriate. But now depending also on how some of us backward method can degenerate, and most of the time we prefer the central one, central finite difference. But now depending, because of those conditions here, sometimes the central one we can.
Yeah. For example, I saw some people who are finding numerical solutions using the famous initial conditions like means Gaussian initial conditions or Newman initial conditions.
Yes, Newman conditions. Yes.
So means we can use those initial conditions for Those initial conditions are more appropriate.
Yeah, the Newman conditions, like those ones are taking place usually this site, that's at origin. In finance, you may not know this is what you want to get here. You may not know, let's say, the derivatives here, like the Newman conditions. You're looking at the derivatives here at that time. You may not be interested into that. What we're looking at is here. What is the deal? The striking whatsoever you want to get deal here at that time capital T. So it's like kind of not really Dirichlet condition, like boundary conditions, but at a certain point in the future time, and then from there we use let's say martingale properties like what we call the measure theory and so on, the machinery, the expected values and so on to know what is happening here. That's the pricing, theoretical pricing. And from this side, that's where we bring in the numerical method to solve the problem. Because at that level right now, we might be moving now from the financial world into now the physical world. So that's the thing. And yeah.
Doc, you spoke about the problems that you encounter at different points in between your differential equations. How do you then account for those problems? And also, if you have different, or let me ask my question this way. At every interval, do you have different differential equations that you're applying onto it?
Yeah, no, it's the same differential. Is this the same differential equation, for instance? Yeah, is this differential equation that you're applying at each point? You apply the differential equation here, you apply it here, you apply it there. At the end of the day, you'll end up with something like this, in a system like this, at each and every point, something that can be huge to solve. But now, depending on how big, the number of points, some of those methods you'll hear something like curse of dimensionality. So which means as you increase the number of points so that you can get better accuracy, but then this one to be solved becomes a problem. So that is why the spectral method comes in to deal with that one. I mean, it does some wonderful results. And plus, if I even some variant of myself, like the one I worked on, it was much more, not only the differentiation metrics that I've used, but I went a bit further into looking at the space of coefficients. So you look at those, because all what you need in the spectral method is those coefficients. So then you move from what we call the physical space, whereby you have these things with a coefficient, with the polynomials. You kind of get rid of those coefficients, those polynomials. Those coefficients here becomes like kind of like vectors. And then for each solution, for instance, you have, let's say, this vector of coefficient. Another solution, another vector of coefficient. Now you look at the space of those vectors of coefficients. So now you are moved, you are in another, what we call the frequency space. There, things get far much better to solve.
What kind of spaces are they? Vector spaces or?
Yeah, it's vector spaces. Vector spaces, most of the time, vector spaces. And things are getting so nice there because of those properties. So solving this type of problems, there sometimes you can even end up with a diagonal matrix, which is just like a one-way traffic to solve. And then once you have that solution, or even whatever you want to do, let's say integration, sometimes this equation like this can be complicated. So what we do, we take the integral somewhere, okay, maybe not this one, you start integrating here, and the integral operator in that space becomes just a matrix. And then so this product.
Sorry, I need to interrupt you. Sorry, yes. we are over time.
Okay, yes, that's fake. All right. No. Okay. Thank you.
Thank you. So remember, 7-minute presentation, 5 minutes per question. Okay.
We should give like 7 minutes. For 20.
It's fine.
Okay. Good afternoon, everyone. My name is Dr. Ali Raza, and I'm a postdoctorate fellow here in Stellenbosch University Applied Math Department. So I'm working in an area of the group study of the group study early symmetry analysis of the differential equations. So for what I will just show the richness of the method, means where we can apply the method to solve the objects, mathematical objects. And then I will start with the basic definitions to present the basic idea of symmetry. And then I will extend it to the group of transformations and one parameter Lie group of transformation. Okay, so one thing is, for example, I will start with the word Lie symmetries. Okay, so Lie symmetries initially discovered by Sophus Lie. He was trying to build the analogous theory related analogous to the Galois theory for the differential equations. That is for algebraic equations, the Galois theory. But he was trying to build a theory analogous to Galois theory for the differential equations. But at the end of the day, end up constructing the theory which is called the Lie symmetry analysis of the differential equations. Okay, so before Lie symmetry, I would like to ask, what is actually symmetry? Start from very basic object. What is actually symmetry? So symmetry is, you can say that, a change or a transformation which actually leaves the object apparently unchanged or invariant. For example, we can start with the symmetries of the triangle. So symmetries of the triangles, they are, for example, have the rotations and reflections, right? So the symmetries of the triangles form a group of transformations, right? So the second thing is, first is symmetries, they are object. What are these objects? These are transformations, right? And once we have transformations, they form a structures. What are kind of structures? First basic structure is they form group. For example, it has three rotation, for example, R1, R2, and the third is identity actually, right? The third rotation. And then it has a reflection, three reflection, R1, R2, and R3. And they form a set of group. How they form a set of group? So let's talk about the symmetry and the group structure. First property is closure. If it's a symmetry, so this set of two symmetry is a symmetry, right? So it is closure property, right? What is the identity? The unchanged symmetry is identity, right? No change, for example. So that is identity, right? And then we have associative property. So associative property is actually, for example, if we have two symmetry, right? And then the combination of two symmetry and with the another symmetry, and then if you means other way around, you can means have the associative property for these symmetries. And what is inverse property? For example, if we have a symmetry, a change, you can undo the action by applying the symmetries from here to here. So as a very basic idea, symmetry are invertible, right? And they have associative property, they have identity, they satisfy the closure property. So symmetry, in the very basic idea, they form a group structures. For example, these are the symmetries of the triangle, they form a group structures, right? So basic idea. Now, the second thing is group of transformations. For example, just like these symmetries, I will define the symmetries in this way. For example, we have xi, let's say, and let's represent it by f, which is a function, and we have x here, and with respect to parameters. So what is actually this thing? So this element represents the symmetries, right? So this is first element, and we can transform this element to this element by function f, right? So this X element belongs to R raised to power n, right? Where X belongs to, let's write in this way, X belongs to the subset of D, X is an element of D. This is a region, and this region is a part of Rn, right? And then we have parameter. Parameter is actually a element belongs to set S, and this set is a subset of real number R, right? What are these actually? These are the transformation. All the F for the transformation, which mapping this point to the transformed point. And this is actually a symmetry, F. In some book, they are writing it like in this way, xi, x with respect to parameter, right? They satisfy some property, right? The first property is identity. For example, x is equal to x bar when the parameter is actually identity, right? Because the parameter is actually controlling the transformation. This F is transforming this point to this point with a parameter epsilon. If the epsilon is identity, the point is unchanged, the identity, right? Here, which is very important thing, which I forgot to mention, is the law of composition, right? So we have this property, the parameter is a continuous parameter. And then we have another property, S, from where we are picking the epsilon, forms a group with respect to the law of composition, epsilon and delta. And delta is another parameter, right? This is, epsilon is continuous, S forms a group of transformation, and then we have identity property. For example, if this transformation...
Sorry, Ali, you ran out of time for that presentation.
Oh. Okay.
Now question.
But this is actually a very good introduction to the structure of a group. We didn't get to the groups, but
okay, maybe next time. Okay. Yes.
Questions?
This thing is set, right?
Sorry?
This one.
Yes.
Is it set, right?
It's a
set.
It's a set, yeah.
Which satisfy the certain axioms, right?
We satisfy certain axioms, they form a transformation, set of group of transformation.
So can I call it a space?
Space.
Because a space is a set that satisfy a certain axiom.
So they form a group.
This one is in pair, right?
Yes. These are the transformations.
And then comes from a set. And we satisfy a certain axiom.
Which satisfy some properties.
So can I call it a space?
Okay, so one more thing.
I really
Okay,
like the
yeah.
question. I like the
So
question.
yes, the question is,
Call it the mathematical structure.
all these, yes, listen.
With information satisfying axiom.
So these are the set of transformation. Every set of transformations, xi, is equivalent to the symmetries of the symmetries, right? Which are the symmetries of the functions and differential equations. So by the first fundamental theorem of Lee, all these set of transformations are equivalent to the symmetries. And these symmetries form a structure of Lie algebra. And Lie, what is actually Lie algebra? So Lie algebra is actually a vector space with a bilinear product form a Lie algebra structure, which is actually a richer structure than vector space. So you can call it, yeah.
Other questions?
From this structure.
Sorry?
If x equals to x bar.
X equal to?
This one.
Yeah.
And this epsilon there is an identity.
Yes.
This is not.
Yes.
What of if that epsilon is another thing entirely? Maybe an impact. How do will you get? Will you be able to get symmetry back? Because I can see that x bar.
Yes.
From that structure now.
Yes.
That is an identity.
Yes. So this will unchange, right?
So if you are changing that epsilon there, that.
Yes, exactly.
Another center.
Yes.
You able to get that X bar.
So actually, you can say that epsilon is actually controlling the transformation. So let's say it's a controlling the transformation. So we change the parameters to get the transformations.
So if you are changing it to something else apart from the identity, will you be able to get the transformation?
Yes.
Like give me an instance of something you can change it.
Professor Kara actually presented the very rotational transformation. What is actually cos?
It's x cosine
X
epsilon.
cos epsilon. Let's say epsilon minus y sine epsilon, and then we have another y bar is actually x sine epsilon plus y cos epsilon. So here, this is the actually rotations. So these transformations actually represent the rotations in XY space.
Thank you very much.
Yeah.
Bafana, would you like to?
Yeah. Mine will be quick.
Right?
Yeah. Okay. Good afternoon, everyone. I think we all know what is a metric space.
Yeah.
And from the metric space, you've got your set equipped with your D, and then your D has got the properties. Yeah? Now, from the metric space, you can define Cauchy, convergence, continuity, metrization, fixed point, Banach. Yeah? Now, my interest was from the metric space, when you remove the first property, you are getting a new space. And then if you remove the second one, you're also getting a new space. The last one, the triangle inequality, you're getting the new spaces. So now, those type of spaces, because they are now new, we can have a pseudo-metric space, you can have a symmetric space, you can have a quasi-pseudo-metric spaces. There are various spaces that you can get when you eliminate some of the properties from the metric space. So the interest was, since from the metric setting, you can define convergence, Cauchy, completeness, metrization, uniform continuity. Now, if you have removed one property, how do those definition come into that new structure? How do they look like? So if you remove the triangle inequality, how do you get those uniform continuity, the metrization? Not only removing some of the property from the metric setting, we also have got some other structures where they are now adding on top of the metric spaces. Like for example, the M metric spaces, the fuzzy metric spaces, the fuzzy quasi. So there are various spaces that you can look into, and if you're interested in fixed point, so you are now going to look at the fixed point based on that new structures. So they are busy introducing some new structures. We've got partial metric spaces. Now we just came across the new one, that is now we are working on the best proximity. So you look at from the original structure, if I've got these properties, now from the new structure that is given, how are these things related? How can I expand? How can I get the new result? If you are interested on the topological part, you can go for the topological part. If you are interested in the fixed point, then you can do that part. That's how I can summarize.
Wow.
Yeah, how?
No, this covers everything, actually.
So with the 7 minutes,
So I have a question.
Yes, Prof.
So why don't we write for our focus area a little kind of two-page note with a catalog of all the different metric spaces that you made, also others have considered, different generalizations or modifications. Like a survey.
We can do that one. We will also even show the connection that the metric space, and then you've got the bigger structure, you've got this one. you indicate that this one implies that, it implies that one, it implies that one, but the converse mostly does not hold. So I can.
Then I have a suggestion for a specific research question, which we started solving for metric spaces with Kishan and Sirin also. But this question will be useful for all the other spaces as well.
Is it? What is that question?
We will have time to discuss it. I don't want
Okay.
to, yeah.
Nice, fine.
But yeah, thank you so much.
Okay,
Any questions for Professor Aphane?
Can I ask?
Yes.
Okay, Prof, you mentioned that on a metric space, there are properties, right? And then
Yes. You've got your set, you've got your set is equipped with the D, which has got those, which has to fulfill all these properties.
and you can remove some properties.
Yes, and then you get a new structure.
You can
Remove-
add.
Yes, you can add.
You get another space.
Yes.
So when you remove properties and when you add, what happens to the space? Does it becomes bigger, or how does it change?
The metric space is the smallest. It has got more restriction.
Yes, and then when I add, does it become?
Yes, when you add as well, it becomes a bigger structure. So for example, you can have your fuzzy metric space. Then if this is my fuzzy metric space, if now I have the fuzzy quasi metric space, the fuzzy quasi now is bigger than this one.
Yes, and then if I remove, it becomes more and more smaller.
If you remove
now the properties.
And remember, from the metric setting, when you remove the triangle inequality, the structures that you get is now bigger than the metric space. Because the metric space, because of this property, it makes this one small.
Okay. So the terminology that you use, you say you remove axiom, your space becomes bigger. Space doesn't become bigger. The category of spaces becomes bigger.
Thank you.
Because you're not changing spaces, you're adding more spaces to the ones you're considering.
Yes.
Yes. It's very interesting. Maybe you have already thought about this, to ask when you remove some properties that which one of those generalized metric spaces still give topological spaces? Or which properties those topological spaces?
Okay. For the quasi setting, you will get the bitopological spaces. Because even the Cauchy is not just a normal Cauchy. You've got the left and the right Cauchy. So those notions, they are defined based on the new structure. So the metrizability as well, the metrizability of the metric setting. Then you look, how is the metrizability in the metric setting? Now let me investigate the metrizability on the symmetric structure, the metrizability on the fuzzy metric or the M metric spaces. So you investigate those type of things. But at least you have got where to start, where to get this basic notion, knowing that from here, when I build up, where am I going to find myself? So it's not like if everything holds here, then it's going to be just automatic to that.
Yes.
Okay.
That's very interesting.
Okay. I think I was the only one who managed to make it on 10.
Even earlier than that.
Yeah.
Thank you very much.
That's how I could summarize.
And if not for that, Amartya would have continued to say. But now he can't because we have exactly 15 minutes left.
Okay. So Zurab told that we should present what we are currently doing, right? That's the whole idea. What I'm currently doing is something about ideals. What is an ideal? Yesterday you heard what is a ring, right? Probably you still remember what is a ring. Let's take a simplest example of a ring. Ring is set of integers. Okay?
You know all of what is integers, right? 1, 2, 3, 4, -3, -5, but not 3/2. Okay. And we have addition, multiplication, we have 0, we have 1, and then it forms a ring. Now, who are the ideals here? 2z, 3z, 4z. Okay. Which are the z's? Any z with integer. 2z, 3z, any z. Any nz will be an ideal. Okay. So what is the property of these people? Very simple. If we have a ring, a subset of this ring is called ideal if it itself is a form of commutative group with respect to addition. Okay. So what is that property? So I should form an abelian group, which we have heard yesterday with respect to addition, and then it absorbs elements from outside. That means if I have an element from our ring, and if I have an element from this set, when I multiply, I can multiply because it's a ring, right? So when I multiply, then Ri should be here. And if my multiplication is commutative, of course, I don't need to multiply from the other side. But if it is not commutative, then I have to multiply on the other side. That's it. So an ideal is just a subset of my ring, which is an abelian group with respect to addition, and it absorbs everywhere. Now, why is this interesting? Okay, first of all, let's see in ring. You have seen this congruent modulo, right, in your first year courses, like Z2, Z3, right? You remember they do this and they put a circle for the new operations and you do the congruent. How I get this one from here? That's the question. I cut it, or rather quotient it, by this animal. So you see, this congruent things, what you learned intuitively was actually you were doing ring theory there. But they didn't tell you were doing ring theory. You were doing add, multiplication, and first you add there, then you bring here, you divide, and then you do the same thing. But you were actually doing, you cut this by quotient, 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 Z2, Z3, Z3, all this. So what we understood, these kind of animals is absolutely essential to do the quotient in my ring. Okay, now this is a general ideals, but there are how many types of ideals? Oh, you can't believe. If you Google, and you know how many alphabets in English? How many alphabets are there? 26. 26. Once I search in the internet, for each of these alphabet, there is a class of ideals called A ideal, B ideal, C ideal, D ideal, like that.
You mean how many letters in the alphabet?
Yeah. How many letters? No, in each of the alphabet, there is a kind of ideals. Like it's called A ideal, B ideal, like that.
Z ideals.
Each of them, Z ideal even.
Greek letters, alpha ideas.
And then they do combination, MN ideal, AIZ ideal, right? And at some point in time, I was exhausted to see, and then there are many words like maximal ideal, primary ideal, minimal ideal. I mean, and every 15 minutes in the world, somebody is bringing a new kind of ideal, almost like that. So ideally, it's an ideal world to study ideals. There is no ideal time for that. And so, but this is all about rings. And many of these ideas are very important. For example, there is something called prime ideal, which is very easy to define. If product of two people are there, then one of them is there. As simple as this. Very simple. Take 3z. If the product are there, then one of them will be there. Now, why this type of ideal is important? There is an area of research called algebraic geometry. This whole algebraic geometry starts with a prime ideal. If you remove prime ideal, whole algebraic geometry will collapse. It's so important there. Okay, but there are many other type of ideals, as I said, apart from alphabet ideals, there are many ideals. But all I said about the rings. But what about other mathematical structures? Yesterday I mentioned many mathematical structures, right? So can we do the same thing? Of course. So where ideals we can study? Okay, I started ring. Semi-ring. Monoid. Semi-group. Lie algebras. But there are functional analysis people, right? I should bring something new, right? Banach algebra. Sister algebra. Boolean algebra. What other structures you know? Tell me. Huh? Hadamard algebra. Of course, it will work. Tell me another one. Topological algebra. Of course, it will work. Okay, tell me another one. Okay, you are run out of your stock. Very good. But then she will say, wait, I don't work on algebra, metric spaces, right? Or say quasi-metric spaces. Then what should I do? I don't have ideals there. Well, the theory what I am studying is not restricted with the ideals. It's restricted in some sense with the substructure. So instead of taking these ideals, you can work with sub-algebras, subspaces, submodules. And then Professor Aphane is with me because I can talk about sub-metric spaces, sub-topological spaces, sub-M-metric spaces, sub-Hadamard spaces, right? And those all spaces, subspaces itself forms a very nice structure. And remember, when you do the quotient, you do it by that subspaces, right? When you do have a topological space, you do the quotient things. So these substructures, in some sense, this ideals is also a substructure of ring, or any one of these, equally the substructures in the any one of these ways is still equally one. So you can do it in any algebraic structures, algebra geometry structures, algebra functional analysis structures, any kind of thing. But what about the some people who works on lattice theory, like these point-free people? They work on lattices, right? Which is now there is no make sense to do the quotient like that way, right? Because it's a lattice. You don't do the quotient. What we do, we pick up specific type of elements who behaves like the corresponding type of ideals. Okay, so let's take very simple example. I said that times up. Okay, good. So you can also work on various type of lattices. So everywhere you can work. Good, done.
That is from fruit and vegetable.
Even fruit and vegetables.
Ideals run rings around you.
Yes, Ali.
When the ring is a wedding ring, so what will be the ideals in the
sorry?
If the ring is wedding ring, what are the most suitable ideals in those rings?
That depends whether it's a married ring or unmarried ring. Ideally,
You should have prepared the answer to that question before you asked your wife to marry you.
Yes.
I see semi-graph, semi. So does it, are you applying it on a smaller space since you are working mostly on the semi-part, or is it a big rather space built from small parts from different aspects of spaces?
You mean this semi-group, semi-ring? It's the same example what she said. She said if we have a metric space which has 1, 2, 3. If you drop 1, you get a bigger classes of space. Okay? If you drop 2, you get further bigger. Right? That's what she said. So you get quasi, pseudo, like this. More you drop axioms, more you get bigger classes. Not the space is getting bigger, as Professor Janelidze mentioned, but you get more of these, right? Exactly the same. I start with ring, I drop something, little bit. Now I get bigger classes. Not ring is getting bigger. So every ring is a semi-ring, but of course every semi-ring is not a ring. Exactly the same way. This one way is true, but the other is not true because you are dropping something. So every metric space is contained in every quasi-metric space.
You're making it less restrictive.
Yeah.
So when you make things less restrictive, more things enjoy those privileges.
So it is something like, I shouldn't write subset, but something like that. It's content, but not in a literary sense. Okay. But it can go above this, like algebra, these things. You see, Lie algebra already contains ring structure. So this is a richer structure. That's exactly what she said. It's similar. You have a metric space, then he put geodesics. There's more. Then you can put more. So you are reaching it on the upper. So the same ideal theory work. Ring is somewhere ideally in the middle space. You can go down, dropping it, or you can go up, adding. Like C-star algebra will be much more structured. So ring, and then you have this vector space, and then you have a norm, then you have a completeness, all these things. You have an inner product, lots of structures is there. So this kind of study you can both do up, down, algebraically, topologically, all of them.
But you need to start somewhere and understand the literature.
Yeah.
Time is up.
We still have a couple of minutes. Maybe I want to say something about Professor Goswami. So your PhD was actually in
mathematical biology.
And then you switched to pure mathematics. So you can see that's why he knows more than all of us, because
no, that's not true.
He knows both pure mathematics and applied mathematics.
This is great. We have students who are in mathematical biology, but they didn't come.
But are they interested in pure mathematics like he was?
It's very dangerous to let them meet Professor Collen, because they will immediately study ideals after that, which is not bad.
Just not ideal.
But then they are good students to meet. I will connect you with those.
There is also Professor Karen Howell, who is mathematics director at ACE. She's also in our focus area. She's not a lead researcher, but she's a member of the group, and she is exploring algebraic biology, which is applications of algebra to biology. Now, in our focus area, we don't do the applied side of things, but there is also a lot of pure mathematics you can do inspired by biology. And she actually wanted to come and present, but in the end, she didn't have time to do that. So those students that you mentioned that you have in biology, mathematical biology, they might also want to talk to her. And in fact, we have a chair, a Sarchi chair, Ken Kui, in biology, in mathematical biology, who is very keen on abstract mathematical aspects of biology as well. It often has lots of money also for students. Postdocs. Of course, not infinite, so he has to select. But
Dr. Magagula from Eswatini. Remember, he was there during the mathematics center.
Yes.
Is it part of NIFEX?
I don't know.
Because he's supervising some of the mathematical biology students.
Definitely not in our focus area. It's not in our focus. But Professor Ken Kui also has coordinates focus area.
I didn't include you in my list, but you know this probability space comes from sigma algebra. There is also something called sigma ring.
Yes.
And there is also a notion of sigma ideal.
Yes. Oh.
Yes. So
the ideas are everywhere.
I mean, you can Google. I mean, you will see that in measure theory, this ideal also plays a role. The sigma algebras, and then you can actually define, because this definition is so simple. You can almost any mathematical structure you can introduce that. If you have a group, take normal subgroups. It will work exactly like that.
And one other thing I wanted to say about Professor Goswami is that because we mentioned the remarkable output of Dr. Abass, and so since he switched to pure mathematics, you should look at his the growth of his publication record. It's quite exemplary. I know, Professor Aphane, that you also, like your supervisor, you also have very good publication. Many papers. So you see, if anybody wants to work with Professor Goswami for master's or PhD, he will make you write lots of papers. Okay. Thank you very much.
Thank you.
We now have break. We now have a break. The break is going to be for half an hour. After the break, after the half an hour, we have the engagement with the other lead researchers in the focus area. But the first half an hour, from 4:30 to 5, we will use that time for the online presentation from your colleague. Let's see, where is he?
Shafi. Yeah,
Shafi.
It's
Hi, Shafi. Would you like to say hi to us? We might be able to see you. Hello.
This is one of our.
Hello.
Let me turn the camera around so you can also see us.
All right. Good afternoon. My name is Mohammed Shafi Abubakar, and I'm a doctoral student here at the Department of Mathematics and Applied Mathematics in Sefako Mahato University. Hello.
So we're going to have now a half an hour rooibos break, and
All
at
right.
half we come back and we will ask you to present. So your time for presentation will be 20 minutes for the presentation and then 10 minutes for questions.
All right. Thank you very much.
You have slides that you prepared, right?
Yes, I do have a slide.
Yeah. Okay. Do you think this time is fine?
Yeah, it is. It is fine.
Okay, great. Thank you very much. Look forward.
All right. Yes.
So he postponed.
Welcome back, everyone. I see that we already have online two core researchers from the mathematical structures focus area, Professor Setuti Moshoko and Professor Partha Pratin-Ghosh, and also actually three, and also Dr. Sirin Ratilal, who is one of the lead researchers as well. Colleagues, would you like to say hi just for a minute, and then I'll tell you what we're going to do next.
Sure. Hi, everyone. It's a pleasure to join you in this hybrid way, and I look forward to engaging.
Sure. Thank you. It's a pleasure to join here in this hybrid way. I look forward to your lectures any further. Thank you.
Deputy, your microphone is muted.
Professor Moshoko, your microphone is on mute at the moment. Maybe he's struggling to unmute. Let me see if I can unmute. I did so. Maybe he will rejoin. Just a quick scheduling question. How long are each of you able to stay, colleagues? Could you please indicate that?
So I'm able to stay for about 40 minutes.
Okay.
Yeah, I think I'll be able to stay until the end today. Thank you.
Thank you. So the plan is, well, let me very briefly tell you what we've been doing so far. You can see the screen, right?
Yes.
So it has been so far an extremely productive meeting. I think we're all quite happy with everything. You would have seen the program, what we did, and everything that was done in those slots in the program was very, very exciting. One of the things we did was to make a map of mathematical structures that underlie research of our friends from SMU, students as well as academics. You can see the
made a little bigger, please. Ah, it's tiny. Yeah. Okay.
I'm sharing the screen. Are you able to see my screen that's shared?
Yes.
No. I can see all of you along with yourself and the screen a little bit. Yeah.
So perhaps if you can see the shared screen, not through the camera, but rather through this. Let me actually switch off the camera for a moment.
Okay. Yeah.
Can you see nothing now, or can you see the screen?
Now I can see the Nitex emblem only. Yeah.
But Sirin, you can see the screen, right?
Yes, I think he just needs to flip through his screens. What device is he using? I'm using an iPad and I had to actually change screens to view it.
Did you hear that, Partha?
Do I do it? It's share.
No.
Apps.
You need to scroll through the options, and maybe one of the options is the shared screen.
The shared. There's something called shared, but that I believe.
So what device are you using?
It's the Zoom app on. Oh, I'm here.
All right, I'm going to read out what's on the map.
Okay.
You can see the map of structures and where where the people are positioned in relation to what they do. We've got quasi-M metric spaces in the top left, then metric spaces, then cat0 spaces, and Hammard spaces, which are special kinds of metric spaces. And on the top right, we have fuzzy metric spaces. Then towards the center, we have probability spaces, Banach spaces, and Hilbert spaces. To the left, we have graphs. To the right, bottom right, we have Lie groups and Lie algebras. And below that, we have manifolds. So these are the main structures that underlie the research from our colleagues from SMU, as it was presented during the workshop so far. And we also put names of individual presenters. These are students as well as academics. The names appearing in green are students who are very keen to be recruited in our focus area. And so by the end of the workshop, we will be identifying who could potentially supervise or co-supervise these students and in which areas. The names in light and dark blue, they're meant to be the same type of blue. They are academics from SMU. And the names in pink, these are the core researchers in the focus area. As you can see, only Kuo and Moshoko are really work on things that are directly related to the research interests currently at SMU. But there are also other relations. For example, we pointed out that Dr. Ratilal, who works in point-free topology, that's quite close to metric spaces. And Gosh works in category theory and topology, so it's close to a bit to metric space, but also in his recent work investigates the category of graphs, so it's kind of close to graphs as well, and so on. So this is how the map should be read. And this map eventually will guide us to identify topics where we want to go. And I see that Professor Moshoko has rejoined. Would you like to say hi, Situti? The microphone is again muted, though, if you're able to unmute.
Hi, colleagues. Good afternoon. Situti Moshoko here, and I'm happy to join you. Thank you.
Thank you very much. So the plan of this session is to do a few things. One of them being a presentation from SMU that is going to be an online presentation from one of the PhD students in graph theory who is going to be joining us from SMU. Our lead researcher in graph theory isn't online yet. I think it will be best, if it's possible, that his presentation will appear when Eric will join. So then we can also take advantage of the fact that we are moving that presentation, maybe begin with Dr. Ratilal to talk to us, especially that she can only stay for 40 minutes. But before that, let me quickly ask Professor Moshoko, how long are you able to stay, Situti? It's muted again.
Hi, Zurab.
Yes.
I can stay for about 20 minutes.
20 minutes, all right.
Yes.
In that case, why don't we, if it's all right with you, Sirin, why don't we first have a discussion with Professor Moshoko, and then we'll have a discussion with you, Dr. Ratilal. Are you fine with that?
Yes, I'm happy.
Fantastic. I'm going to make your video bigger now, Situti, on our side, so we can see you well.
We can't see you anymore.
I'm going to fix that as well. Just give me a minute. Let me also reposition the camera. So we are currently in the new offices of NITEX. These offices have been inaugurated last week. Our workshop is the first ever workshop after the inauguration. Historical day or week. I think everything disappeared now, right? So let me try to fix it again. No, this is a wrong, and there are two cameras, so this is, I now picked the wrong one. Go back to the one where, I think at this stage, what we might want to do is to simply wave hi to Professor Moshoko. And let the discussion begin. So I've got a microphone here. Anybody who wants to ask him a question can come to the front and do so. But maybe before that, has you already met your students, or is it the first meeting?
No, you didn't.
Okay, so maybe
the Abass, not on. You guys speak.
So Professor Aphane will now introduce Professor Moshoko, and then the discussion can start after that.
Okay.
Okay, it's this one working. This is not working.
No, it's on.
Okay, thank you very much. Good afternoon, everyone. Prof. Moshoko, welcome to our session. SMU is currently at Stellenbosch. And
you are next to the ocean.
yes, Prof, we are next to the ocean with the students. So in total, we are 12, is 4 staff members and 80 students, honors and 2 master's students. To everyone in the house, Prof. Moshoko is the HOD for mathematics and statistics at TUT, and he was my supervisor for master's and PhD. So now we're gonna join him as a co-researcher. So which means the students you'll be trained by the person who trained me. So Prof, the floor is yours.
So
Well,
yes. You're most welcome to address us for 2 or 3 minutes, and then after that we will ask you questions.
Okay. I don't know what to say, but it is really a good environment where we see students. I'm not good about being conflicted. I mean, it is of interest for the country's interest that we can have this number of students that want to pursue their careers. You can hear me, right?
Yes.
Yes.
Yeah, because I'm using my cell phone, not my laptop, but I am in front of my laptop. So I was saying that it is good to have this kind of students trying to pursue their postgraduate studies in such a very conducive environment, and that I'm really available and also eager to put my efforts where it is necessary. And of course, they can ask questions if they have got any questions. But yeah, I think from my side, I can wish them all for the best. And I'll pause for now, yes, and open for the floor, yeah.
Thank you very much. So I'm going to raise your hand. I'm going to come to you and give you the microphone, so it's maybe quicker that way.
Okay.
Okay.
Okay, this is your excellent chance to talk with Professor Moshoko exactly similar fields when you are working and you have any questions, anything about research topics, feel free at home, as you were talking from yesterday. Anybody?
We're not experiencing this.
Yes, please.
Hello, Professor. What I will say or I will suggest is maybe if he can give us maybe the topics that he can assist us on, or rather that he can he may be available on to maybe to supervise or to co-supervise as, I don't know.
Did you hear that, Professor Mashaka?
Yes, I did hear that. Well, my work it's more similar to what your supervisor, Professor Aphane, is working on. But basically, I work on distant spaces, and I look at the issue of convergence, in terms of sequences from the internal structure, not necessarily categorically. And then from your spaces, convergence, and then we look at completions of such spaces, or more generally, extensions of such spaces. If you've got a space and then you find that there's still conditions that don't work in that space, the question is, can you extend such a space, but in a way, very profound way, such that the bigger space will have the necessary properties that you are looking for. And if you go back, you look at the completion of a metric space. That if the space is not complete, you can extend it via the class of Cauchy sequences, and then you obtain a bigger space, and then such a bigger space can have some nice properties. And of course, such spaces where they've got these properties, you can look at, for instance, your fixed point theorem issues in such bigger spaces that will have nicer properties, like a space that is not complete. But not only that, now you also look at, as I've mentioned, you look at distant spaces which are bigger than necessarily metric spaces. And of course, in the literature, you'll find that there are so many spaces or distant spaces that are being introduced. But I look at topological properties of the spaces as well as non-topological properties of the spaces, whether the extensions that one gets, are they of interest in the sense that they must be connected to the classical theory in mathematical analysis. So that's one thing that I also look at. I also look at metrizability of such spaces. Now, if you've got such a space, you generate a topological space. Now, the question is whether such a topological space is metrizable or not. I use this, the idea of uniformities, quasi-uniformities, to look at such properties for those spaces. And even beyond that, now I look at other properties, but related to distant spaces, as well as some of the applications of a fixed point theorem, but from a topological point of view. I hope I've tried to address what I work on.
Yes, Professor Mashaka,
but if there are any questions, I'm happy to address them. Yeah. And then maybe let me also add that, no, not necessarily in metric space. Hello, can you hear me?
Yes, we can.
Yes, we can
Zurab?
hear you.
Yeah, just to add a little bit that, yeah, I also look at distance spaces here also include normed spaces. So any space with a distance around that space, that is my interest to look at what kind of nice properties can one look at in terms of the internal structure of sequences and extensions of such spaces. Thank you.
So basically,
Thank you very much. Any other questions?
Any other questions So basically what I understood that various types of metric spaces also generalized, as well as now he said norm spaces. So it's very wide classes of spaces.
Correct.
Do you have any other questions for Mashaka?
Good afternoon, Prof. My question is simple. What are the real life applications that can be looked into from the work that you are currently busy with? Are there the applications that we can try to look into, try to solve certain things, to apply rather your work, in simple terms, to apply your work into a real life problem?
Okay, that's a very nice question. But generally, let me start by saying that usually mathematicians, when they look at structures, they don't necessarily look at immediate applications. of those structures. And I don't want to say a lot of advantages of that, but we know that the real applications that we see today in cryptography, in coding theory, etc., those kind of applications, actually, they were found some years ago. But the main aim then was not to look at applications. Now, if one has got a mathematical structure, for example, just one scale, application of this. I don't know if you are aware of a fractal geometry or fractals. Let me call them fractals. Now, yes, with fractals,
He's not
if
aware.
you've got, he's not aware. Yes,
They have
okay.
not.
All right. So if you just take your just one of the applications, because there could be many, some of them I don't necessarily be knowing them. If you take a metric space and then you take a collection of subsets in that, let's say X, you take a collection of subsets, and then on that subsets, you define what we call a Hausdorff metric. This is basically one of the work that I did when I was doing my master's degree. Once you've got a metric on the space of the collection of subsets, and from there you take contractions from your initial structure, and then you take a collection of these contractions. And now you've got your function you've got a set valued map from the Hausdorff metric space into a Hausdorff metric space. And then from there you obtain a construction which is obtained via the class of contractions that was first in the underlying space, the initial space. And then you look at the fixed point of that. The fixed point of that are no longer points, but sets. In general, these are referred to as fractals. Such sets are very much important because if you look at, for example, at the shape of a tumor, a cancerous, swelling of a body, the shape of that is not necessarily a geometric figure that you are aware of. That shape is actually what is referred to as a fractal. So there are many, many applications to that. And also looking at the fixed points related to financial markets, etc., etc. But then you need applications or the usage of computer in calculations or for those kind of applications. But generally, I don't look at such applications, but those applications are there.
Is it satisfactory?
Yeah.
Thank you.
But yeah, just look at the fractals from the Hausdorff metric, then you'll have some idea of how your classical theory for metric spaces can be extended to more structures where your fixed points are now sets and not a point.
Thank you. Another question?
Good day, Prof. I
Yes.
heard that you are working on the metric spaces and the fixed point. This is the also space that I'm working on, but I'm working on a quasi-metric spaces and then on a fixed point, but extending that fixed point to a non-self mapping, so which we call a best proximity point. So can I ask if can I collaborate with you in terms of supervision?
Yeah, we can look at those possibilities. But yeah, we can look at those possibilities. But what I'm also interested is if you look at your code, you call them what? Quasi-metric spaces.
Yes, it's an extension of a metric spaces.
Yeah, well, one has to look at whether such an extension is interesting or not. But I'll tell you why I mean interesting or not. As I've mentioned earlier on, there are many, many generalizations of metric spaces, but in some sense, those extensions or generalizations are not necessarily generalizations. If you get what I'm saying.
Yes, I'm interested because you are working on a fixed point. I'm also working on a fixed point, but extending it on non-self mapping.
Yes. Yeah, we can look at that. We can look at that.
So is there a way of, can we collaborate or?
Let's first look at the commonalities.
Okay,
you are in SMU?
Yes.
Are you in SMU?
Yes.
Yeah, no, you can arrange for a meeting and then we can meet via Prof. Aphane.
Okay, thank you.
All right, no problem.
Let me correct. Yes, Prof, the English there is not our mother tongue. He's still a student, he's still doing honors degree. So it will not, yes, it will be a supervision or a co-supervision for masters. But currently he's working on best proximity point under the supervision of Professor Naim and myself. So you are more than welcome. Okay, thank you.
Yeah, we'll have some discussions on the proximity points in those kind of structures. I think also coincident problems. Yeah, we can look at those things. No problem. Yeah.
Thank you very much. Thank you very much, Professor Moshoko.
Okay, you're welcome.
Input. Let me also add to what Professor Aphane said. So our main goal of this workshop, right? Our main goal is to recruit all of the students who are here, to recruit them in our focus area.
Mm-hmm.
And in some cases, they might indeed want to have co-supervisors from other universities. One of the core researchers of our focus area could then be such. As you know, Professor Aphane is our deputy coordinator for the focus area as well.
Yeah.
And in some other cases, they might actually want to move to a different university, so while still maybe being co-supervised by the local current supervisors, but then move to a different university as well. So these are the main things we're deliberating. But in addition to that, we also made a very exciting list of other projects we want to do immediately after the workshop, and it's been very successful so far. And I will report to you exactly what we did to all of you in the focus area once the workshop is done.
Okay.
Thank you so much for joining us.
You're welcome.
I would like to now, let's make a clap for. I would now like to invite Dr. Sirin Ratilal to engage with us a bit. Sirin, over to you.
Sure. I hope everyone can hear me.
Yes, we can.
Perfect. So, hi everyone. I am based at the University of KwaZulu-Natal. I work in topology. I have done my previous studies in general topology, as well as later on in my PhD in point-free topology. So if you have some background in general topology, then you could view point-free topology as a generalization of it. The idea is that we will no longer refer to points of a given space, and rather we would instead work with the open sets of the topological space. The idea here is that when you take any given topological space and you take the collection of all open sets of it, then that collection of open sets of a given topological space, together with intersection and union, that actually forms a lattice. In fact, it forms a complete lattice that satisfies a very special property, which we call an infinite distributivity law. So this mathematical structure, this special lattice that I'm referring to, is termed a frame or a locale. And this structure is basically what one studies when they do point-free topology. So one could study the category of frames versus the category of topological spaces and so forth. So if one has to deal with a metric in topological spaces, of course, there a metric is now assessing the distance between points. But in the frame setting, we no longer have points. So we cannot talk about the distance between points. When we generalize this, what we get is a map. And this map is actually assessing the diameter of the open subsets. So I saw on the slides that were shared in that map that you all had put in metric spaces. And so those of you who are interested in understanding metric spaces could perhaps consider a project where you could study the metric on a frame or a locale. So frame and locale are terms that we use interchangeably. They are the same mathematical structure, except if we thought about it categorically, the arrows would then change. So this is something we could do. I am also interested in studying connectedness properties of frames or in topological spaces in general. So connectedness, disconnectedness, local connectedness. And if you want to study connectedness pertaining to metric structures, so a metric frame, for example, then there's a special property that one could look at, and that is called property S. And so I'm happy to engage with you further on any of these topics if this is something that interests you.
Thank you very much, Dr. Attilal. We would now like to ask you some questions, if we may.
Good evening, Doctor. My name is Khensani. Now, I wanted to ask me, do you think you can extend yourself to like Keto spaces and Hadamard spaces as well?
Well, we could discuss and we could see if there is a problem that one could work on. So I'm open to engaging. If in particular you want to look at metrics in specific instances.
Okay.
But we
So,
need, yeah.
These are special kinds of metric spaces that I learned about from the student who is asking the question. And one of the interesting questions might be to see if they have a localic version.
Oh, okay.
So
I'd be happy to engage with you. Is it Khensani, right?
Yes, it's Khensani. Okay. I don't know how this is it gonna. Should she type something now or should I?
Sorry?
Okay. Thank you.
Thank you.
Any other questions for Dr. Attilal? Any clarification or anything?
Good evening, Doc.
Hello.
Can I just get a clarification because I didn't quite get the definition for point-free topology and how is it different from general topology?
Sure. So in point-free topology, the mathematical structure that we work with is called a frame. A frame is simply a lattice. So of course you start off with a partially ordered set, and you have meets and joins, so supremums and infimums. And so the property that one...
Sorry to interrupt, Sirin.
Yeah?
So we learned today that they're not necessarily familiar with what a partially ordered set is. We had a little discussion about it, but just take that into account. Thanks.
Sure. So when you have a pose set, you start off with a set together with a relation on it, and it needs to be reflexive, anti-symmetric, and transitive. So in addition to this, we have supremums and infimums that one can now take onto the set. So hopefully you're trying to write something down on the board to help me. So
yeah, we are writing actually, as you are saying. Yeah, please continue.
And so if we start off with this this arbitrary pose set that has this special relation on it, we then define what an infimum and a supremum is. We normally denote this by a meet and a join symbol. The infimum is simply the greatest lower bound of a set of elements that you would consider, and the supremum is the least upper bound, if one has to unpack what that means. So in order for a pose set to become a lattice, we require that given that for any two elements that you pick, we must have that the meet of the two elements exists and the join of the two elements exist. All right. And so that's a lattice. But beyond just having a lattice, this mathematical structure that we require needs to be a complete lattice. So what is a complete lattice? A complete lattice is simply a lattice that satisfies the property that whenever you take an arbitrary subset of the lattice, that its supremum exists, or equivalently, the infimum of that arbitrary subset would exist. So one or the other. You simply need one of them, and if that is satisfied, then what we then have is a complete lattice. Now, once you have the complete lattice, if this complete lattice satisfies an infinite distributivity law. Now, what does this mean? So remember, I've told you we've got these two operations, the meet and the join on the lattice, which is respectively the infimum and the supremum. So if we have that finite meets distribute over arbitrary join, then we say that this complete lattice satisfies the infinite distributivity law. And so this, which I have now described, is what we call a frame or a locale. And as I explained earlier, an example of this would be to take any topological space and take the collection of all open subsets of the topological space. This collection of the open sets from a topological space actually ends up being a frame. And you can check that under meet and intersection, all these properties that I have just explained to you is actually satisfied.
Is this good enough? Actually, Professor Janelidze is writing all the terminologies what Dr. Ratilal just mentioned.
So that's completely different from a topological space.
Yeah, no, you take a topological space, you take all open sets of the topological space, okay? And that open set itself forms that new mathematical structure, what Dr. Ratilal mentioned is frame. Because if you take those X, Y, I, what wrote Professor Janelidze on the board, those are your open sets. And they will satisfy that equality, what he wrote. And that's what Dr. Ratilal mentioned, infinite distributive property. So the frame is a general version of a topological space. So open sets is an example of a frame, very special case. And what she was suggesting, according to his suggestion, that the special type of matrix spaces, that can be also think in a point-free way, like this way. So that's what she said, that she will be also interested to be engaged. So look for nice questions on the special type of Hadamard spaces, C0 spaces, and that kind of thing. Any further follow-up questions?
Yeah, I think it's
okay. Sure. Thank you.
We'll probably have some time tomorrow, Dr. Ratilal, to engage more about this question, and we will explain what a post set is, what a lattice is, and what a frame is.
Sure.
Do that tomorrow.
Any other questions or remarks, or you need clarification? Feel free, because this is why we are here. It's not performance. Please completely feel free to engage. Please.
Hello. So I was just thinking on this partially ordered set, and I wanted to ask if they are like in category theory, there are arrows that map objects to other objects. Are they like arrows, or let me say in terms of sets, like functions in this posets that you can have, from one poset into another one that maps. And I wanted to know how that looks like, because with the axioms they have here, I can see that they do use the the inequality sign, to really relate all these sets in the poset. Yes, so I want to know would you describe the possible functions or errors there? And yeah, thank you.
So we certainly have maps on posets. So you want to talk about that, or the maps on the frames? Sorry?
He wanted to know these morphisms in the category of
frames.
Yeah.
Okay, so yes, in the category of frames, we certainly do have these corresponding maps. We call them frame homomorphisms. And these maps, they're also special, and they satisfy properties that must respect these operations that I mentioned to you, this meet and the join. So the properties that must be satisfied here is that this map must preserve finite meet in a frame. And secondly, it must preserve arbitrary join. But if you're preserving finite meet and arbitrary join, a consequence of each of those things is that also you would end up preserving the bottom element of a frame. So that's one thing we could have also explored together when we looked at the definition initially. The frame, since it is complete, it's a complete lattice, means that it will always be bounded, which means it always has a bottom element and it has a top element. So this frame homomorphism will also preserve the bottom element. It will map the bottom element from the first frame into the bottom element of the second frame, meaning through which we're mapping from and to. And similarly, it will preserve the top element. It will map the top element to the top element.
These are the 4 properties what just you mentioned. So it will preserve the binary meets. So you can think like an intersection. This meets in a set. The meet is like an intersection when you move to the sets. And with respect to the join, don't need to necessarily 2, it can be arbitrary. Okay? And then as a special case of these 2, one can also need to consider that the top element and the bottom element. So top element is 1, which is the top one of this lattice, because it's a complete lattice. And this is the bottom element. So bottom element will be also preserved. No, absolutely not. L prime, none of them need to be finite. It can be any, as long as it forms a. So this L and L prime, according to this definition, what she said. So L and L prime are these frames. And your question was, what kind of maps? We talk about that, like sets, as Dr. Caviglia was mentioning, any function is map, right, in a category sense. So your question was, if this is my category, who are the map? Like there's arrows. And now Dr. Ratilal just mentioned, those functions between such frames will be mapped in that category, which satisfy these 1, 2, 3, 4 properties. Yes.
So I also heard that you mentioned that the set must be bounded. So it's also, so is the set, so the set must be also continuous or not?
Prof. Goswami, can you repeat the last part of the question? I didn't hear it.
Like a set is continuous, because this is not anymore a topological space. It's just a lattice.
Yes.
And it's bounded. Why? Because you have 0 and 1. So that's why it's bounded. So when continuity only makes sense when you have a topological space. So now we are outside of topological space. So it's just a lattice which has these structural properties. So as such, continuity in a sense of topology will not make sense unless you wanted to mean something else.
And so the term homomorphism, that's why I also mentioned the continuity.
Okay. Homomorphism is a very general term, which means structure preserving map. Just like what Dr. Ratilal mentioned, it preserves the structure. If you remember yesterday when I was telling group, ring, fields, all this, each of them has a structure preserving map. Like here, So yesterday when we talked about semi-group, group, rings, each has his structure preserving map. What does it mean by structure preserving? Whatever the operations you have on the left-hand side, it should be preserved on the right-hand side. Now, what Dr. Ratilal mentioned and what Professor Janelidze wrote, it's a lattice, so it has these 2 structures, join and meet. These are the operations, okay? So it need to be preserved. And that's, you see, this one is in this side, but this one is on this side. So that's how it preserves. So any kind of categories you consider, whatever we talked yesterday and whatever just wrote here, each of them is an example of a category, and the structure preserving maps are in general in category 3 is called morphism. And in algebra, it's called generally homomorphisms. But morphism is the most general term which can be applied for any kind of mathematical structures you can come up or whatever wrote on that map in what we present. Does this clarify anything? Okay.
We'll definitely come back to these
we'll
mathematical questions tomorrow, and we'll explain everything that is not been fully explained.
Yes, absolutely. Yeah.
Short session.
Yeah. Siri, please.
Yes, so if it's okay, I actually do need to excuse myself now, but
Yeah,
I look forward to engaging with the students, etc., going forward.
Thank you so much, Siri.
Okay.
Thank you very much.
Thank you. Bye-bye.
Bye.
Now, Dr. Ghosh, right? Yes, because Winchi will join from.
I would suggest that now we, because Dr. Ghosh can stay to the end.
And is Eric here?
Not yet, but nevertheless, he will join in half an hour.
Okay.
So he will join halfway in the presentation, because also Wenchi can only join the same time as Eric.
Yes,
I
absolutely.
would suggest that we start with the presentation that we planned from SMU in graph theory. Eric is actually here. That's wonderful. Eric, would you like to say hi to us?
Hello everyone, I just joined now. I'm not sure at what stage of the meeting is this, but hi from Rhodes University.
You've joined at a perfect time, Professor Dantiana. I'm going to, in 2 minutes, I'm going to tell you where we are in the workshop, and then after that, we will proceed. So it's been a very successful workshop so far. We have one fixed goal among many, but one of them is most important, which is that by the end of the workshop, all of the students from SMU that are here will be recruited in our focus area. And this is very exciting both for us and for the students. Now, the way the recruitment will happen is that some of them could possibly stay at SMU and maybe have one of the core researchers in our focus area to co-supervise their further studies. Others could move to a different university. For example, somebody might want to come to your university, and then they could be supervised by you. In light of the pandisciplinary nature of our focus area, we might even want our core researchers to join together in co-supervising students on projects that are really pandisciplinary, based on mathematical structures and pandisciplinary. In your case, for instance, this would be supervising projects about graphs, but not necessarily restricted to combinatorics, because graphs really arrive everywhere, and there are many applications as well of graph theory. So in light of that, one of the things we did was a mapping. Do you see the screen?
Yes, I see.
We made a map of mathematical structures that currently are involved in the work that the students and other academics at SMU do. You can see there are quasi-metric spaces, metric spaces, fuzzy metric spaces, and so on. The black text refers to mathematical structures they work with. And then the green text is names of students. Some of them are honors, others are master students. Names of students who work with these mathematical structures already now. And then blue refers to academics from SMU. And so everybody is positioned according to how close they are to given mathematical structures. You will see that in graph theory, there are, you will see your name there as well. And so we have 4 colleagues, students from graph theory present, and one more who is online, who is now keen to give a presentation on their work. But before we give him a chance to do that, I'd like to ask you, for how long do you think you'll be able to stay?
I'm happy to stay up to be 6:30.
Oh, that's fantastic news. Because in that case, what we're going to do is to ask the colleague from SMU who is joining us online to give their presentation on their work in graph theory. And then maybe after that, you could give some feedback on that work. And then we will ask you some questions to you personally after that as well, if that's all right with you.
All good, yeah.
Fantastic. Thank you very much. Then let me ask, what's his name? Let me ask Mohammed Shafi to perhaps turn his camera on and share the screen for the presentation.
Yeah, good evening, everyone.
Hi again, Mohammed.
Yeah, hello.
Hi.
Yeah, my name is Mohammed Shafi Abubakar. I'm from the Department of Mathematics and Applied Mathematics, Sefako Mahato University. And I work in the areas of computational graph theory and network science. My PhD work presently focuses on the intersection between networks and biology. So it's a beautiful application. So I'm going to be sharing my screen now. Can you see my screen?
Yes, we can.
Yeah. This is a review article. It's a review report I wrote for my PhD in literature review. So it is titled Pairwise Network Models in Epidemiology, a review of approximations, dynamics, and applications. So as we all know, networks are defined as structures that are composed of, interconnected entities called nodes, and these nodes are normally linked by edges. So, these networks are classified according to, various structures, according to their structural complexity, according to their applications and generation mechanism. So we have some networks, examples of some networks such as random networks, such as the heterogeneous network, the scale-free networks, small world networks, the regular or lattice networks, community or the modular networks, and the multilayer or the multiplex networks. So these are some of the common types of networks we use for representation of real world scenarios. And then, as you can see, most of these networks are usually used to represent social interaction among humans. So I have a small simulation here for a scale-free network and a small world networks. On the left-hand side, you can see the scale-free network. The scale-free network is a kind of network that is characterized, by the concept of preferential attachment, whereby you have few nodes in the network that tend to have, a very high degree, a very high, level of connectivity or high degree. So, and this scale-free networks was introduced by Albert Laszlo Barabasi and Reka Albert some, I think, decades ago. And these networks are very, very important when we want to model, real-world social interaction. And on the right-hand side, I have the small world networks. The small world networks is characterized by the presence of clustering and very short average path lengths. So, and now coming into the idea of pairwise model itself, the pairwise model is a concept that was, conceptualized by Levin and Payne in their article, which discussed about local interaction and spatial structure. And although their article did not really, discuss in detail the modalities of these pairwise models, but later on we had other researchers such as Rand, Killing, and Bouch, Chris Bouch, and the rest of them who came around the between 1996 to year 2000, that brought in this idea of pairwise models, and then they tried to see how they can apply them to infectious diseases, such as extending the classical SIR models, representing them in terms of pairwise models. So as we all know, in mathematical modeling, the classical deterministic models, often assume random or well-mixed population. But if you look at it, in reality, the human, population is not well-mixed. So if we represent these humans in terms of networks, we are able to, understand the number of humans who are infected, or those humans that are infected, and the kind of correlation that forms, which leads to large-scale epidemic, and also how to control this epidemic. So what this pairwise model does is that it helps to track the number of susceptible, infected, quarantined, or whatever state the individuals are at that particular time, and also it also helps to track the pair that forms during the early phases of the epidemic. So due to these correlations that form, there are two types of higher order correlation that we normally experience whenever humans are connecting with each other. For example, we can have a pair between node A and node B, whereby node A is susceptible and then node B is susceptible. We can also have another pair between node A and node B, where node A is susceptible and node B is infected. That is a pair. So, but we can also have a triple. A triple is a situation where we have three nodes. For example, we have A, B, and C. We have node A connected to node B and node B connected to node C. So these are higher order pairs, and it is called a triple. And then we also have the triangle, or otherwise known in this direction as cluster. So the triangle is just an extension of the triple, where you have a situation of closeness, where node A is connected to node B is connected to node C, and node C is connected back to node A. So the belief is that during epidemic, or during the formation of epidemic in a population, these are the type of interactions that form. First, we have a pair, then we can have a triple, and then we can have a triangle. So, and each of these relations, each of these interactions, social interactions, they have their impact on the spread and control of diseases. So, for example, if you look at the triangle, it is believed that the formation of triangle helps to, reduce or slow the pace at which, these diseases form. So these triangles, henceforth, I'll be calling it clusters. So it is believed that these clusters, helps to, reduce the pace at which, diseases can, spread across the entire network. So one of the things we do in pairwise network modeling is that whenever we have formation of higher order interaction, what we try to do is to, approximate them in terms of pair. For example, if you have a triple, we try to approximate the triples in terms of pair. And if we also have a cluster, we try to approximate that cluster, in terms of pair. By the time we do these approximations, two things, we are able to do. Number one, we are able to get an analytically tractable system. And then number two, we are able to see the formation of this, of these higher order interactions clearer. So the network model itself is based on two assumptions. Number one, we have our homogeneous degree network assumption, and we have the heterogeneous degree network assumption. So in homogeneous degree network assumptions, what we do is that we assume that the every node in the network have an average degree, or have an equal degree, a kind of a regular lattice, or a regular network. But in the heterogeneous degree, the assumption is that each node in the network, or each individual in the network, have its own degree. For example, node A can have degree L, node B can have degree K, and node C can have degree M, and so on and so forth. So in heterogeneous degree network, each node has different degrees. So depending on the type of network you are modeling, and also depending on the disease you are modeling. And then also the reason why we assume homogeneous degree in most cases is that if we want to obtain a very simple system that is analytically tractable, sometimes we first solve it with the homogeneous degree assumption before we now extend to the heterogeneous case. So there were some types of approximations that were initially introduced between the years 1995 to this moment. And then one of the few introduced approximation for triples and clusters was by Sato, Matsuda, and Sasaki. So their approximation was known as the improved pair approximation. So, and what this improved pair approximation is saying is that the expected number of the expected number of SI edges that is connected to an infected node, can be approximated using, the equation we have there, where we have 1 plus Q minus 1 over Q times IS. Here, Q is the average node degree of the network, I is our infected pair, and S is the susceptible, I is our infected node, and S is the susceptible node, which can further, so this Q into IS can further, be represented as SI over S, where this is the average number of, susceptible nodes per infected neighbor. And then the same assumption also follows for the case of QISS, where we have the expected number of, susceptible neighbors per infected node. So if you have that kind of triple, it can be approximated using the second equation. So, but one of the disadvantages of this improved pair approximation was that it only approximated triple. It didn't take into account, or it didn't take into consideration the case of the clusters, whereby you have, a closed triple case. So this particular shortfall was improved upon by Morris in his PhD thesis, I think in 1998 or so. So Morris was able to introduce the triangular pair approximation. His triangular pair approximation was able to incorporate clustering into the triple approximation. So if you look at equation one is saying that the expected number of ABC, expected number of triple in a network, can be approximated as Q minus 1 over Q. Q is the average node degree, and then the pair AB times the pair BC divided by B. So here now B is the center node, A and C are its neighbors. So so this is how you approximate a triple. And then 1 minus phi is the probability that there is no cluster. But if you now add the second part, that is plus phi times n times pair AB divided by Q times expected number of A nodes times expected number of C nodes, we now have the clustered considered. So here, that particular part is now considering the cluster. N is the total number of nodes in the network. AC is our pair AC. That is, AC now is the formation of pair between the node A and node C. That is existence of edge between them. And remember, that is what closes a triple pair. So so adding that part now contribute to approximating a higher order interaction in terms of a cluster. Now this cluster, he defined it in equation 2, whereby we have summation of for summation of total number, expected number of triangles in the network divided by the summation of expected number of triples in the network. So one of the disadvantages of this triangular pair approximation was that it was, number one, it was quite suitable for small networks, and also it requires explicit counting, of the triangles and the triples in the network, which may not really be suitable for very large networks. So we had other types of approximation. For example, the one by Rand. I think this one was introduced in the year 2001. I'm not very sure. So the one by Rand is almost the same as that of the one by Morris. But the difference is that here, he added some kappa, which is an estimated correction factor, which it's it's a value that is usually assumed from the simulations or whatever data we are modeling. So he gave the triple approximation in equation 3 and also the clustered case in equation 4. So now coming to the work of Killing, the work of Killing in 1999 was one of the earliest work that brought in a very good that brought in a lot of interest in this direction of pairwise modeling. So what Killing did was that he extended the classical SIR model, that is susceptible, infected, recovered model by Carmack and McKendry. He extended it to the case of networks. So what he's saying here, if you look at the first network on the left, it is a network of single individuals. First, you have the S individual, and then you have the infected individual, and then you have the recovered individual. So what he's saying is that initially, if an individual is susceptible, for that individual to become infected, definitely that individual, there must be an edge between that individual and an infected individual. So, and that is modeled with the rate of tau times the per SI. So once that individual, if there is an edge linking a susceptible individual to an infected individual, then the individual becomes infected. And when the individual becomes infected, naturally he becomes recovered at the rate of gamma. So, but for the case of pair, pair formation in the network, he's saying that if you have a pair of susceptible individual, for any of these individuals to become infected, there must be a higher order interaction that must have happened. That is a triple, must have happened, or a cluster in whatever case. So for any of these SS individuals to become infected, they must have an infected neighbor at the rate of tau. So you can see that we now have tau times the triple ISS. So now once they have this edge with an infected neighbor, then one of the susceptible individuals can become infected, and eventually both of them can become infected, or one of the newly infected individual can become recovered at the rate of gamma, and so on and so forth. So this was the logic behind the pairwise network model flow diagram. So, and then when he introduced this flow diagram, he also came up with it as with its approximation. So the approximation was, if you look at it, is similar to that of Morris and Rand, but here it has a quite different clustering coefficient. So what he's saying, if you look at equation 5 says, okay, if you have a case of triple, A connected to B, B connected to C, you can approximate them in terms of pair, where you now have n minus 1 over n times AB times the pair AB times the pair BC divided by B, where B is the center node. And also, if you want to include clustering or clusters, if you want to model the clustering in the network, you can use equation 6. The equation 6 has an extra term which accounts for these clusters. So, but Killing defined this clustering coefficient as the number of triangles divided by the number of triples. Here, the number of triangles is modeled by the trace of the cube of the adjacency matrix. Here, G is the adjacency matrix. So when you take the cube of the adjacency matrix and then you compute the trace, you are going to have the number of triples, or the number of triangles rather. But in order to compute the number of triples, you need to take the norm of the squared adjacency matrix minus the trace of the squared adjacency matrix. So here the norm of the squared adjacency matrix is simply the summation of all the entries in the adjacency, in the squared adjacency matrix. So so incorporating this cluster into equation 6, you'll be able to model the number of clustering, or the proportion of clustering that exists in the network. And according to Killing, he said these values ranges from 0 to 5. So when you compute a clustering coefficient for a network and it happens to, let's say, fall below 0.5, let's say it is 0.1 or 0.0 something, it shows that that network has a very low cluster. But if the value falls maybe from 0.4, 0.5, 0.6, and so on, it shows that the network has a very high, clustering. And that was what I showed in this network that was depicted here in, I think, figure 2. Yeah. So in figure 2, if you look in figure 2, you see we have a network with 100 nodes. So the first network in the left-hand side has a clustering coefficient of 0.189. You can see that the clusters are not very visible. Rather, the label and the edge labeling rather looks rather random. But in the second graph, you see that graph has a kind of a better clustering because the clustering coefficient there is 0.438. So and the belief is that these clustered networks they help in slowing down the spread of diseases in the network. And then also additionally, when a network is clustered, we are able to identify the pair correlations, especially between susceptible individuals and infected individuals that form in the network. So we will know how to attack the network and how to eliminate the epidemic. So after
sorry to interrupt you, Mohammed.
Okay.
It is a very interesting presentation.
All right.
We are just a bit limited in time in this session.
Oh.
You had 20 minutes, I think. So you already talked for 20 minutes.
Oh.
It would be nice if we can maybe interrupt it here, and if you'd like to continue, definitely we can bring you back tomorrow, or if you'd like to continue your presentation tomorrow. But for now, we have still a lot to do in this session, and is it all right if I interrupt you? Maybe with just 1 or 2 sentences, you can summarize the overall bigger picture of your work.
Oh, okay. So one of the things we are trying to do, particularly in my work, is to extend, this concept of pairwise modeling into zoonotic ecology, where we have, diseases that are that infect the human population, coming from the, animal, population. So when we represent this on a network, we want to see the kind of higher order interactions that form, how we can approximate these interactions. And also, we want to see how the clustering coefficient is going to look. Of course, the network is mixed. We have humans, we have animals interacting. So, the clustering is going to look somewhat associative, whereby we have to group humans first and then, rodents that side. So these are some of the, general framework that I'm trying to, look at for my PhD. Thank you.
Thank you very much.
Yeah.
I'm now going to hand it over to Professor Andrantiana.
I mean, the talk was nice, and I learned a few things about it. It's a different type of graph theory than what I work with. So what I see there is that you have the population and the situation, and you model it as a graph. And now that it is a graph, you do several calculation, and depending on calculation, you might be able to tell about the graph and then tell something about the situation. Somewhere in this, it's actually still on the screen now. Equation number 7 is probably where we get a little bit closer. What I do is also involve a lot about trace of adjacency matrices, but in a little bit more general setting than just a power 3. We play with a power k, because a trace of g to the k is actually counting number of closed walks in a graph. And this g to the power 2 is actually counting number of walk of length 2. G3 was closed walk of length 3, and that's why it's related to the triangle. It says number of triangle equal to trace of G3. There might be a little bit of step in between those two, but it's not exactly the number of triangle. I would say this trace has to be divided by 6. There is some factor 6, which I'm happy to discuss if someone is interested. But the formula is sound, and I think it's one interesting aspect of graph theory.
Thank you very much, Eric. Let me thank Mohammed for his presentation. Thank you very much once again, Mohammed. And I apologize that I had to interrupt you halfway of your presentation, but thank you so much.
Thank you, sir.
So as the next step, we're now going to engage a little bit with Professor Andrantiana. Eric, would you like to say just a couple of words about yourself or your work, and then we will be asking you some questions from the floor.
Yeah, I can try. Thank you. I did not prepare a slide, but I can write on the screen and talk along the way. And feel free to interrupt me at any stage if necessary. Yeah. So I am Eric Andrantiana. As mentioned, I work at Rhodes University. It's been 10 years now. You probably see my screen now.
We do.
Yeah. And I studied in Stellenbosch. You probably at Stellenbosch now. I spent my whole postgraduate study there.
These are new offices of NITEX that were inaugurated last week. So we are in Stellenbosch. It's in the basement of the first floor of the physics building, facing the mathematical sciences building. It's a lovely place, very nice place. Next time you will visit here, you'll see how nice it is.
I think I have an idea of what you're describing. Yeah. Yeah. So for me, I work in graph theory. Just a second. I've not activated this. So I work in graph theory, and what I do in graph theory is counting, essentially. So I'm somewhere in between the intersection of graph theory and combinatoric. Okay. And I do use linear algebra quite a lot. That's why I like that trace of G3 in the presentation recently. That's something I do use. So I'm not sure how to describe it now, but linear algebra is come very often. And then so to be precise about what I do, I work on a field that is called extremal graph theory. Okay. So what is extremal graph theory? That is when you will choose a certain set of graphs. So we don't do like modeling one situation and get one graph and play with that one graph. What we do is we have a bag of graphs, lots of, possibly infinitely many of them. But there are many graphs here, G1, Gn, all the way, many graphs. And then there is a parameter. I can say sigma G, something like this, that we define. And the question is usually which one of those has the max and which one of them has the mean? Or is there a way, if somebody give us a Gi and a Gj, is there an easy way to compare the sigma of those, Gi and Gj? So now, depending on what sigma is, the application will be. So so most of what I do so far, sigma is some graph invariant that is provided by chemistry. Yeah. So they for some reason in chemistry they have some parameter and they describe and define it, and we bring it in graph theory, and we now try to figure out what kind of structure of a graph has the largest and what kind of structure has the smallest. So the guy, I mean, I might take long, but as I said, feel free to interrupt me. In the world of graph theory, there is the graph here, graph, okay. As the guys say, graphs are just sets of dots, some of which may be connected, okay, something like that. I'm providing a very simple, small graph here, unlike what he provided, complicated and lovely, colorful graph. But essentially, that's what graph is. And initially we use sets to describe those, set theory. So if we provide the names to those, okay, then we can actually describe a graph with sets by putting the set of vertices as the V1, V2, and all the way to Vn, which will be V4 here, and then set of edges, which will be describing the lines. But those, we need 2 points. So this is going to be V2, V3, and then V3, V4 for our case. So our graph is now defined as VE. This is how you describe a graph with set theory. But with sets, it's a little bit limited operation and useful operation, and it becomes more interesting if you describe it in terms of matrices. As mentioned in the presentation earlier, you talk about adjacency matrices. How do you do it? If this is still our graph, you create a matrix associated to it. And you can put here V1, V2, V3, V4, and here is V1, V2, V3, V4. And you answer a question, is Vi connected to Vj? So for this one, is V1 connected to V1? That's a no, you put a 0. V1 connected to V2, 0. Well, V1 is actually isolated. We're going to get 0 all the way. And then similarly, V2 connected to V1, still 0. To V2, 0. But to V3, a 1. Okay, and then 0. So that's how you create the matrix. And then you get the nice AG, how we usually call it. Yeah. So one of the very well-known graph invariant that I've worked on a lot, and it's very popular in chemical graph theory, is what is called energy of the graph. And by the sound of it, of course, a graph does not have energy, but coming from where the application is, it's related to energy of molecules. That's why it's called energy. And that will be the sum of the absolute value of the eigenvalue of that adjacency matrix that we take. Yeah, yeah. So that's what we call energy. And as I said earlier, what we do is we want to, given a certain set of graphs, we would like to know what structure maximize this energy of a graph. And because it comes from chemistry, initially people work on chemical graph, graph that can molecular graph, molecular graph that can model molecules. So in organic chemistry, those are molecules of carbon, hydrogen, oxygen. And is this, what's the name of this in English? Is this a nitrogen now? N. Yeah. Yeah, so, but those things, this guys only have degree 4. This hydrogen is going to be just a degree 1. Oxygen, degree 2 usually. And N, I think it's 3. I hope my chemistry is not that good. Might be 3, probably. Yeah, but so if you limit yourself
from the room
to,
that it's 3.
Yeah, I think so. When you play with a molecular graph, you're going to be limited with those kind of degrees. It is already interesting enough. Imagine try to find out the possible molecules that has 100 atoms. And then you want to find out which structure maximize the energy and which structure minimize the energy. A little bit of motivation why are those important is what happened is when for example the pharmacy design the medicine that we usually buy from clicks and all of those, they have to try a lot of many molecules, and trying those in a lab is costly and time consuming, because you have to mix it with some expensive solution, and then so to reduce that cost and to reduce the time, imagine the case when there was COVID. We have to get the vaccine quick. So time is very important. Yeah, so to reduce the cost and reduce the time, this is why it's important mathematician comes in so that they can just write on the paper, study those parameters, and will be able to describe that if you're looking for a molecule with large energy, this is the kind of structure you should expect. And that helped the chemist. So that's how the connection is about. Yeah. At the moment, it's not, I've not mentioned much yet how it is connected to combinatorics, but there is actually an alternative formula of this that involve counting number of independent subset. And once you get that formula, if you don't like linear algebra, you can throw away linear algebra a little bit and now just apply recursive formula and counting techniques, and you will be able to get some answer, some result in the energy. But time is short. Energy is just one of them. There is what is called the Wiener index, which is a different type. There is the Estrada index, which is also related to lambda, but in a little bit different way. And I wish I had 1 hour or something to explain those in detail to you. Yeah, but I might probably
Eric,
stop there.
Eric, if you're available tomorrow, we can definitely ask you to give a longer presentation. This session is just for more human interaction rather than mathematics. Probably there will be some mathematical questions nevertheless. So if you'd like to, and if you're available tomorrow, we could slot in your presentation if you'd like to, of course. But for
I have a whole morning meeting up to 2 o'clock. So if the session, the event still on around 3, I will be happy to give about an hour presentation for from 3 to 4 or something. Yeah, I'm not sure.
That's fantastic. Maybe 1 hour is too long because we will have to move around things in the schedule. But what about half an hour?
Half an hour is already, I mean, it's better than nothing. So I'm happy to use half an hour. I will reduce. Yeah, it's already something.
Okay, great, thank you. So we will now engage with you a little bit, and then after that we will chat with Wenqi. So any questions for Eric? If you'd like to turn on your camera, that will be nice. We will make it bigger on the screen on our side.
Okay, can I ask a question?
Yes.
Okay, Prof. I also work in the area of chemical graph theory. And then so I just wanted to ask, sometimes when you, in your study of these graph energies, especially, let's say if you are applying them to chemical structures, do you do predictions? Because we do a lot of predictions over here.
I mean, it depends on what you call prediction. So what we will do, the kind of prediction we do will be about if you tell me a set of graphs that you are interested, what kind of graph, something like trees or a regular graph, as you say. I might be the prediction we will be able to tell is to give you a characterization of which of those type of graph will have high or low energy. That's the kind of prediction we do. Yeah.
Oh, okay. The kind of prediction I was actually talking about is, for example, if you have, let's say, let's say isomers of alkanes. So when you have isomers of alkanes, and then you compute their energy, you know, sometimes you can use, you know, this statistical analysis, linear regression, and the rest of them to predict the total pi electron energy of this alkane isomer. So do you work in that direction?
Yeah, the pi electron energy is actually where the name energy come from.
Yeah.
Again, what's going on is if you compute that sum of absolute value, it doesn't give you exactly the pi electron energy, but there is some alpha coefficient and some beta to be adjusted for it to get the pi electron energy. Yeah. So in that way, yes, the energy that we're calculating actually predict the pi electron energy of the molecule. Yeah.
Oh, okay, that's good. Thank you, Prof.
Thank you, Mohammed, for the question. Any questions from the floor? A comment from the floor. We actually had, Eric, very nice presentations in graph theory. One of them was about graphs of molecules.
Good evening, Prof.
Hello.
Okay. It's good to know that actually you could use energy of graphs to predict, because normally what we are using is degree-based topological indices, and sometimes also distance-based. So it's good to know that, it's good to know that we can usually actually use the energy of graphs to do some predictions. So maybe there might be some work, if not now, in the future, that we can be looking at. Because at this time, as much as I'm a staff member, I'm also a student. So still trying to complete my PhD as well.
With this energy of a graph, I was just picking one case to illustrate, given the small amount of time. But what you're saying are actually one thing that I've been working on, like distance-based, the Wiener index and the Harari index, and those now are the spectral-based, which goes with the energy and the Estrada index. And there are the degree-based. Yeah, those are the different types. So yeah, I'm glad there are people in the event that have some background around this. But tomorrow I will present one or two or maybe three discuss about those parameters. Yeah, with the 30-minute.
That will be a good idea tomorrow.
Thank you very much. Thank you very much, Eric. We will then see you again tomorrow.
All right.
I'm going to now, let's thank Eric. And I'm now going to hand over to invite Dr. Kuo to join us. I see that Professor Watson is also there. Hi, Bruce.
Hi. I'm just trying to switch devices quickly to a device which is a bit easier to use. Okay. Can I log off on the first device now? There we go.
So is it going to be Professor Watson?
Okay.
Dr. Kuo. All right.
Can you hear me?
Yes, we can hear you. So everybody's a bit surprised to see you because they were expecting Wenqi, but let me explain to everyone that it's actually today Wenqi's birthday. And so we pass on congratulations for the birthday. And her husband, Professor Bruce Watson, who is in fact director of Center of Excellence of Mathematical and Statistical Sciences, will talk to us instead of Dr. Kuo. Bruce, I want to just give you a very brief summary of where we are so far, so that then we can maybe ask you some questions and then you can understand the context from which the questions come.
Okay, that sounds great.
So basically, there are many exciting things we discussed, but there is one very specific goal we have towards the end of the workshop, which is to recruit all the students from SMU that are here, to recruit them in the focus area so that they can continue their studies, postgraduate studies, with one of the core researchers of the focus area. So what we've done to help us identify these directions is to create a map. We created a map of various mathematical structures that they already work with and are familiar with. And I'm going to now share this map with you. If you can see it on the screen, are you able to see it on the screen? Can you see the screen, Professor Watson? Can you see the screen, Professor Watson?
Yes, I can. Sorry, I was just changing, so I have a headset on. That's far better.
Sure. So we made here a map of mathematical structures that our colleagues and students from SMU work with. You will see them in black text. These are the mathematical structures they work with. And then we've positioned students and colleagues according to the proximity of the work to those structures. So the green ones are the students. Most of them are honor students and some of them are master students. The blue ones, light and dark blue ones, they are academic staff at SMU. And the pink ones are the core researchers in the focus area. And as you will see, there is quite a lot of interest around Hilbert spaces and Banach spaces and probability spaces. And maybe in just a few sentences, you could say a little bit about the functional analysis as represented through the structures in our focus area, and then we'll be asking you some questions.
Okay, sure. Well, I would like to firstly say that the area that Dr. Kua and I work in is one of the areas is vector lattices, and we look at it with its in particular with its connection to stochastic processes, probability, and such structures. And if you like, to be facetious, just as Serene was talking about pointless topology, we talk about measureless measure theory and probabilityless probability theory. So, but that's being a little bit facetious about it. But a whole lot of probability theory and stochastic processes really hinges around the interaction of two different types of families of projections on vector lattices. The first is what are called band projections, and the other one, which everyone who's done probability knows about, are called conditional expectation operators. And the band projections in an LP space or Lebesgue space look like multiplication by a characteristic function of a measurable set. So those give you one family of projections, and your conditional expectation operators give you another family of projections. And in essence, stochastic processes is the study of the interaction of these two families of projections and how they, when you have families of the one type of projection, how do they interact with another family of the other type of projection, etc. And with this structure, you can take ergodic theory, martingale theory, stochastic process theory, mixing theory, through to the setting of vector lattices. Now, on the other side of the story, Serene was talking about a structure that gave rise to a lattice. Now, just as you start, when you start in measure theory, you start off with sigma algebra, and you can build the characteristic functions over that, and you can start building your structure from that. Those characteristic functions, again, form a lattice. That lattice interacts directly with the structure Serene was talking about. And she came by it via an entirely different direction, but they are linked. And once you have the lattice, you can build a vector space structure over it, and you can build a vector lattice, and thereby you can work with stochastic processes in this generalized setting. And it has many interesting aspects. It enables one to build and solve some problems not solvable using classical stochastic process and probability theory. It has yielded some quite amazing new results. It obviously has as a subset classical stochastic process and probability theory.
Thank you very much. So we will now ask you some questions from the floor.
Sure.
It is very interesting to see how now lattices suddenly come up in vector space theory, because we previously saw, as you remarked, lattices in the context of topology, of general topology, and now you see that they're also related to probability and to vector space theory.
Any questions or
clarification? In fact, there is a closer connection between sober spaces and sober measurable spaces. Well, I studied it in one of my papers with DAMS, and this adjunction and isomorphism, adjunction and equivalent subspaces have been established there. Yes, as you say, there are very neat connections between them, real compact spaces, and so on. Yes. Thank you.
Who was speaking? He didn't introduce himself. He didn't introduce himself. He just going.
any question or anything you would like to ask, Professor Watson? Yes.
Good evening, Prof. My question is not related to anything you just talked about now. Now, I wanted to confirm something. Are you the CEO of CIOMAS?
I am the director of CIEMAS and co-director of IMSA. I'm also a NETHEX associate, and my wife, Dr. Kuo, is a PI with NETHEX.
No, because I think I've seen you in some of our conferences. I think at SMU. I think it was online or something. So no, I thought I'm seeing many things there. Thank you, sir.
Great.
Oh, sure.
Good evening, Prof.
Evening.
Prof, what I want to ask, I heard you talk about the spaces and the stochastic process. So are you saying you are using those matrices to solve the stochastic process? What are you doing with the matrix on the stochastic process exactly?
We don't in general use matrices, we use projections. Obviously, you can, if you restrict yourself to small spaces, you can model these objects through matrices. But in general, these are infinite dimensional spaces, so one's looking at abstract projections, just as one does in measure theory.
Okay, so is the abstract projection the best way to solve the stochastic process? Because I hear that some people are using least symmetries on stochastic process as well. So I want to know what is special about the one that you are using.
Well, let me tell you what the Lie symmetry side will do. The Lie symmetry assumes that you've already studied something which is sufficiently special that you can pose it as a stochastic differential equation, and that you can use Ito's lemma on it to reduce it to a classical differential equation. And then you apply symmetry methods to solve the classical differential equation. That is how symmetry methods are used in stochastics. They are not directly attacking the stochastic process. They are dealing with it via Ito's lemma, which takes you from a stochastic differential equation to a classical equation. Okay.
Okay. One more question, Bruce.
Good evening, Prof. Mine is,
Evening.
I don't know how to structure the question, but structurally, right, looking at stochastics, then mathematics, how can we then bring the relationship in between the two to also try to structurally put something in how well to the end point is to try maybe to incorporate structurally that into maybe the Black-Scholes equation, for an example. How can one try to navigate through such? I'm not sure if you understood correctly.
Well, the Black-Scholes model is a very special model of a martingale process. Okay, so it makes a large number of assumptions, and it is very specific, and it puts you into classical measure theory. You can easily pose problems in stochastic processes which are not Black-Scholes compatible. So the Black-Scholes model is a very, very specific model of a particular type of martingale process. So there are many other problems, and there are many other interesting results which are not Black-Scholes problems, and many others that relate to stochastic differential equations. So some of them are reformulatable into a Black-Scholes type model, some are not. Okay.
Does that answer your question? Okay. Any further questions or research problem as you were asking other people like co-supervision or your area, his area, or you? Any clarification? Yeah, sure.
Good afternoon, Prof.
Good afternoon.
I heard on your talk mentioning stochastic process theory. And what I know is that stochastic process theory deals with randomness, and this is what usually happens in the financial market. So I want to ask, is it your field applicable into financial markets?
I am a functional analyst. Dr. Kuo has actually worked in the banking and finance sector. Both of us have a maths and functional analysis background. I worked in spectral theory, and I still do some work in spectral theory, and then got involved in vector lattices and stochastic processes in this setting. Dr. Kuo has a maths and actuarial background. She worked for the credit bureau and various of the banks, doing stochastic models and credit models and all of that for them, and then came back to academia. So as far as the applications to finance goes, that is not my area. You'd have to actually drop Dr. Kuo an email on that. I'm an abstract mathematician. Does that answer your question?
Yeah. So we will share Dr. Kuo's email address to everybody, and you can, of course, write to her. And by the way, Bruce, is it possible for Wenchi to be available tomorrow at some point of time? In case.
What time tomorrow are you looking at?
Zurab, when Eric also wanted to be available, can we fix something?
So maybe at either at 2 o'clock or at 4:30.
Let me just ask her.
Just for questions, no need for a presentation.
Yeah, I mean,
her day is very busy tomorrow because she has a whole lot of executive meetings and things in the school. So if you drop her an email, I'm sure she can answer on email, because the executive meetings in our maths department can ramble on forever, and she's on the executives. So, but I would suggest just emailing her, sharing her email address, and if people have questions, she can get back to them.
Thank you very much.
Thank you, Bruce.
Great.
Okay.
Thank you very much once again.
Thank you.
Okay, thanks. Bye.
Bye. I would now like to invite Dr. Partha Pratim Ghosh. Would you like to turn on your camera, Partha?
Yes. Yes, thank you. I'm Partha. Hello?
You already seen the map, right? Or were you able to?
Yeah. I've seen the map now. Yes.
So basically, the idea is to is for us to have a chance to talk to you about your interests and also your possible availability for cost of provision. But you can maybe in 1 or 2 sentences tell us about yourself, and then we will be asking some questions. We do not have plenty of time left. We have to end soon, but I don't want to rush this either. So over to you.
Yes. Oh, should I put the video on? Okay.
Yes, please. Thank you.
Well, I'm Partha Pratim Ghosh from UNISA. My general interest lies in the structural aspects of. So I will, as someone already told about the structural aspects of networks, which I will consider as graphs, and somebody also spoke about some spatiality. So my interest lies in about trying to address the issue of spatiality in a general category. And also that's one of my interests. The other interest is obviously in trying to look into directed graphs as algebraic structures by themselves. So trying to look into, say, what are the projective objects, what are the generators for a kind of graphs. If you give me a class of graphs, to find what are its generators, and such general questions as usually studied, say, in a course in groups or rings. So such ideas, parallel of such ideas in the case of graphs. So that is a very broad and a very loose way to describe my interests without going into the details. I would also not scare you at the end of this day with all the details that I would need to give for this. But more or less, it is around the study of structural aspects of graphs and spatial things which have spatial properties. They could be understood as measurable spaces, or topological spaces, or metric spaces, and so on and so forth. I'll stop here, and then I'll take in some questions.
Thank you very much.
Okay, as you heard from Dr. Ghosh that his research area includes metric spaces, topological spaces, graphs, more generally also in category theory. So any specific question for Dr. Ghosh you would like to clarify or wanted to know from him, please.
Afternoon, Prof. Could you please just clarify on did you say you also do work on directed graphs?
Yes, I'm trying to look into directed graphs, but from an algebraic perspective, the collection of all graphs and graph homomorphisms make a structure which is known as algebraic structure. It is very much similar to, say, the structure of groups with group homomorphisms, or rings with ring homomorphisms, and many others. So therefore, one can make a similar study of, as you do in groups or rings in case of graphs, which I don't find anywhere in the literature. So those are the things of interest to me also.
Okay, so if you don't mind, could you just maybe give us an idea of like what you have been looking into, on like what have you found so far, like on your research on directed graphs? Maybe if you could share the properties you have found on directed graphs. What are directed graphs?
Well, a directed graph is, if you take a graph, it is a set along with a set of unordered pairs, right? But if a directed graph is a set along with a set of ordered pairs. So each ordered pair denotes a path from one vertex to another vertex. So that's the difference. If you take, this could be understood as a relation also, but it can be made much more general. Yeah.
Okay, thank you, sir.
Partho, his first question was what type of properties you so far?
Yes. So for instance, given any set, can you give me a free directed graph on that set? Okay. Or given any directed graph, can you tell me what are all the quotient graphs of that directed graph? Yeah. So such questions like this are of interest to me.
So basically, Dr. Ghosh is trying to say what we are describing yesterday and today about these homomorphisms, quotient, product of these various algebraic structures. The same thing one can do with these graphs, which is not quite easily to find. And that he's treating graphs as one of those mathematical structures like what we discussed, and do the similar kind of properties which may not be studied in a combinatorial graph theory way. So am I right, Partho, what you are trying to say?
Yes, exactly. Yes.
Okay.
Let me also add there that there is a subject called algebraic
graph theory.
Algebraic graph theory.
Yes.
What that subject does, it looks for graphs in algebraic structures. Like, for example, ideals will form a graph as well for a suitable notion of edge between ideals.
Yeah.
Now, what Dr. Ghosh does is kind of the other way around. He's looking for algebra in graph theory rather than graphs in algebra.
Yes, correct.
Any other questions or clarifications? You wanted to know some projects, whether he will be interested, you will be interested. Please feel free. That's why we are here. Are you sure? Okay. No other questions? No.
Well, we are right on time.
Yeah.
It's now 6:30, which is the end of the session. Thank you so much, Dr. Ghosh, for your contribution.
Thank you.
And thank you everyone who was also joined us online. So this this session is now ended, the hybrid engagement with NITEX mathematical structures community. And we have a little surprise. Everybody's tired, of course, but the idea is to rest, not to get more tired before dinner. But if you are so tired that you don't even want to rest, we don't have to do it. So, but maybe Elena and Luca can tell us what the surprise is.
No, you can tell.
Luca, would you like to say?
It's your job.
Even I don't know what the surprise is. Okay, let me say something from my part. Let me say something from my part before I pass it on to Elena and Luca.
You need microphone because there are still some people online.
One of the things, one of the, no, this is not going to be for online participants. So for online participants, the session is done. Okay. It's end of the day. We will resume tomorrow. But for those who are here, before eating dinner, we have a suggestion. But before the suggestion, I want to give you a context. So one of the things that we are trying to do in the focus area is to apply mathematics to make money. Okay, this is a bit of a joke, but the idea is to create mathematical games which could be useful for building mathematical skills, for having fun with mathematics, for relaxing with mathematics. Let me show you what I have in mind. There is, for instance, this game that I'm going to turn off.